Right.
which means looking at the electromagnetic spectrum.
Okay, so the EM spectrum. These are synchronized oscillations of electric and magnetic fields, and they operate with a transverse wave geometry.
Yeah, transverse. So if you want to visualize that, just think about tying a rope to a doorknob and shaking it up and down.
Like making a wave travel down the rope.
Exactly. The wave itself moves forward toward the door, but the rope is just oscillating up and down. That is what's happening with EM waves. The electric and magnetic fields oscillate perpendicular to the actual direction the wave is propagating.
That makes sense. And to really grasp how this works, the sources highlight one core mathematical rule. The golden equation. Frequency multiplied by wavelength equals the speed of light. So lambda times nu equals c.
That equation is everything. It dictates this strict inverse relationship. Because, the speed of light is a constant, right?
Right.
So if your frequency goes up, meaning the waves are oscillating faster, your wavelength physically has to go down. They're permanently locked together like that.
And just for context, visible light, the stuff you and I actually see, is sitting in this tiny narrow band between 400 and 700 nanometers.
Yeah, just a sliver. But for military comms, we're exploiting the spectrum way beyond that.
So let's rattle off the radio bands, because the scale here is just wild. Starting at the very bottom, we've got extremely low frequency, or ELF.
Which is less than 3 kilohertz.
Right, and the wavelengths are massive, greater than 100 kilometers long. I like to think of ELF like a deep, slow bass beat at a concert. You know how you can feel that thumping bass from miles away?
Oh, absolutely. Just pushes right through walls.
Exactly.
And that is exactly why navies use ELF to talk to submarines. The wave is so long it practically ignores the ocean, so it reaches subs running in deep stealth mode.
But the data rate is painfully slow, right?
Oh yeah, like a few characters a minute.
Wow. Okay, so moving on. Next is very low frequency, VLF, from 3 to 30 kilohertz. Then low frequency LF at 30 to 300 kilohertz. And medium frequency, MF, from 300 kilohertz to 3 megahertz.
And then we hit high frequency, HF, that's 3 to 30 megahertz, with wavelengths shrinking down to between 10 and 100 meters. This is the absolute workhorse for long-distance ground comms.
We'll get to why in a second. Continuing the climb, we have very high frequency, VHF, at 30 to 300 megahertz. Ultra high frequency, UHF, is 300 megahertz to 3 gigahertz.
Yeah.
Super high frequency, SHF, 3 to 30 gigahertz.
Yep.
And finally, extremely high frequency, EHF, which is 30 to 300 gigahertz. Wavelengths here are tiny, like 1 millimeter to 1 centimeter. So if ELF was the slow bass beat, EHF is like a hyperfast dog whistle.
That's a great analogy. It carries a massive fire hose of data, but only over very short, localized distances.
Right.
Because of how these waves interact with the environment. There are 3 main interactions: reflection, refraction, and diffraction. Basically bouncing off stuff, bending through mediums, and scattering around sharp edges.
And militaries use 3 specific modes of propagation to exploit this. First is ground wave.
Right, which uses lower frequencies. Ground waves actually hug the curvature of the Earth. Highly reliable, but short range because the ground absorbs the energy.
Then there's space wave propagation. This is straight line of sight. SATCOM, VHF, UHF.
Yeah, you shoot straight. But if there's a mountain in the way, it's useless.
Which brings us to the really clever one, skywave propagation.
This is where it gets fascinating. Instead of fighting the Earth's curve, we use the atmosphere as a mirror, specifically the ionosphere.
The layer that gets ionized by solar radiation.
Exactly. It refracts or bends those HF waves back down to Earth. So you shoot a signal up, and it bounces back down miles past the horizon.
But there's a catch, right? The skip zone.
A huge tactical headache. The skip zone is this dead area between where your ground wave fades out and where your bouncing skywave finally lands.
Because the skywave has a minimum skip distance, it has to travel.
Right, so imagine you're a commander in a steep mountain valley. You can't use ground waves, the mountains block them. You can't use skywaves because the enemy in the next valley is sitting right inside your skip zone. The signal bounces right over their heads.
So what do?
You use NVIS, Near Vertical Incident Skywave, NVIS. It is brilliant. You take your HF antenna and you literally point it almost straight up into the sky.
Like a 70 to 90 degree angle?
Yeah. You blast the ionosphere directly above you. It refracts and rains straight back down like an umbrella, filling that entire 0 to 650 kilometer skip zone.
Oh, wow.
You take a massive tactical disadvantage, a valley blocking your signal, and turn it into a secure, localized communication bubble.
Because the same mountain blocking your radio is now blocking the enemy from intercepting your NVIS umbrella.
Precisely.
That is incredible. And the sources also mention some totally exotic tactics for extreme range, like meteor scatter.
Oh, yeah.
Which is literally bouncing burst data off the ionized trails of shooting stars.
It sounds like sci-fi, but it works.
Or transequatorial propagation, TEPP, crossing the magnetic equator for ranges over 5,000 kilometers. And moon bounce, or Earth-mooner.
Literally using the moon as a reflector. High path loss and a lot of delay, but you can reach the other side of the planet.
Okay, so we have the physical pathways, but how do we actually put data onto those waves?
That is modulation. You take a raw, empty carrier wave and modify it to hold your data.
Right. We have analog AM, FM, PM. The sources note FM has much better noise immunity than AM.
True, but militaries use digital modulation almost exclusively now. Amplitude shift keying, ASK, frequency shift keying, FSK, and phase shift keying, PSK.
How does shift keying differ from normal AM or FM?
It uses discrete states. Instead of a smooth analog wave, it snaps between specific states to represent ones and zeros. So for ASK, the wave gets suddenly taller for a 1, shorter for a 0. For PSK, you literally shift the starting phase of the wave mid-cycle.
And the receiver reads that abrupt shift.
Exactly. It gives you extreme noise immunity, better bandwidth efficiency, and most importantly, yes, you can scramble digital ones and zeros easily. Try doing that securely with a smooth analog voice wave.
Right. So if modulation is packing in the car, multiplexing is sharing the highway. MUX and DMUX hardware. FDM gives everyone their own frequency lane. TDM uses time slots.
And for optical systems, there's WDM wavelength division multiplexing, sending different colors of light down the same glass tube.
And CDM, code division multiplexing. Everyone transmits at the same time on the same frequency, but each signal has a unique digital spread code.
The receiver just filters for the matching code.
Now, when we talk about satellite access, it's a bit different. FDMA gives out dedicated frequency lanes, but it's wasteful. If I'm not talking, my lane sits empty.
Say with PAMA, pre-assigned multiple access, fixed channels, which is why modern networks use DAMA, demand-assigned multiple access.
I love the analogy for this. DAMA is like a dynamic carpool lane. Instead of keeping a lane open for an empty car, DAMA pools the lanes and only opens one when a user actually demands access.
It is incredibly efficient, conserves frequency, optimizes bandwidth, especially in a hub-and-spoke topology where a central hub talks to dozens of remote spoke terminals.
And if they need a massive data dump,
they switch to SCPC, single channel per carrier. dedicated point-to-point link.
Okay, so we're optimizing bandwidth, but we still have noise. External noise is obvious, like weather. But internal noise, this is generated by the hardware itself.
Yeah, engineers have to fight this constantly. Thermal agitation noise happens because electrons jiggle around from ambient heat. Shot noise is from current fluctuations.
Transit time noise happens at super high frequencies when electrons take too long to cross microscopic gaps in transistors.
Right. And then you have quantization noise in digital systems. When you convert a smooth analog wave into rigid digital steps, you lose information.
The rough edges of those digital stairs physically create audio noise.
Exactly.
So wireless is great, but it can be intercepted. When a military needs absolute security and massive data on the ground, they use physical wires. Optical fiber cable, OFC.
Pulses of light through glass, over 100 megabits per second easily. It's built in layers. The core, the cladding to reflect the light, a plastic shield, Kevlar for strength, and an outer jacket.
There's single mode, using laser, which can go 100 kilometers with insane bandwidth, and multi-mode, using LEDs, which bounces light down a wider core, shorter range, like 2 kilometers, but better for field deployment.
And that brings us to TAC-OFC, tactical optical fiber cable, ruggedized, very low attenuation, just 0.2 decibels of loss per kilometer, so you can space repeaters 20 to 50 kilometers apart.
But the craziest part about TAC-OFC is that it has zero signal radiation.
This is huge for electronic warfare, EW. Normally, if you blast a radio signal, the enemy can triangulate you and jam you.
Right.
But if you're sending light down a shielded glass cable buried in the dirt, you are radiating nothing. They can't find you, and they can't jam what they can't see.
Invisible security. And all this data routes through switches, like the EPIVX, or for military grade, the secure SRAX Mark II.
But physical hubs are targets. If the SRAX gets bombed, the network dies.
Which is why cloud telephony is such a crucial strategic backup. It decentralizes the routing so governments and energy sectors can survive an attack on physical telecom.
But what if the ground lines are cut and the sky is jammed? You have to look up.
Space. Satellite architectures.
A satellite has a footprint, its coverage area. It carries payloads for relay, intel, or targeting. And the link is usually between a mobile terminal and a massive Earth station.
Let's compare the orbits. GEO, geostationary, these are 36,000 kilometers up. Fixed position, massive footprint, but the latency is awful. Like 477 milliseconds minimum.
Half a second delay is an eternity when you're tracking a hypersonic missile.
Right. So we move to LEO, low Earth orbit, just 400 to 800 kilometers up. They move fast, great for surveillance, and the latency drops to 25 to 35 milliseconds.
It's basically instantaneous. And depending on the mission, they use different bands. L-band for mobile and GPS, C-band because it resists rain fade, X-band for military radar, and Ka-band for precision targeting and huge data rates.
Which brings us to the mega constellations, the ILEO revolution. Starlink.
Total paradigm shift. Thousands of satellites at 340 to 570 kilometers altitude, 20 to 40 millisecond latency, pushing 50 to 250 megabits per second. They use phased array antennas.
But the really mind-blowing part is the ISL, optical intersatellite laser links.
Oh, yeah.
They're beaming data between the satellites using lasers at 200 gigabits per second. It's a high-speed fiber optic network, but instead of glass, it's a mesh of lasers in the vacuum of space.
Meaning data doesn't have to constantly bounce back down to vulnerable ground stations. It routes through space and drops exactly where it needs to go.
And the tech on these is crazy. Ion propulsion, star tracker sensors, visor sat to reduce brightness. And the V2 Mini uses the E-band at 60 to 90 gigahertz.
Launched in 2019, active in conflict zones by 2022, and now they have direct-to-cell service.
And obviously, the military wanted their own version, so we have Starshield.
Starshield is the hardened military version, 2 times the solar arrays, hosted classified payloads.
And it plugs right into the SDA, the Space Development Agency's 7-layer architecture.
All right, which handles battle management, missile tracking, hypersonic defense. It uses those narrowly focused, jam-resistant Starshield links.
So we've covered space. Let's bring it back to the dirt. Tactical battlefield tech. How does a soldier connect to all this?
Through terminals, VSS, LVSS, mobile satellite terminals, or MST manpacks that you carry on your back.
Also HMV-mounted, KBST, mobile satellite stations, or MSS and NFS, and they all use DAMA for bandwidth sharing.
Right. Look at Project Droop 2 for the Northern Operational Command. High-speed SCOM for extreme mountain terrain where normal radios just fail.
And none of this works without navigation. We have GPS, GLONASS, Galileo, Baidu, but relying on another country's GPS is risky.
They could just turn it off?
So India built Navik, or IRNSS, just 7 satellites, but it covers all of India plus 1,500 kilometers past the border. There's also Gagan, their GEO augmented system.
But if we're talking about the cutting edge of localized tactical data, we have to talk about Li-Fi.
Li-Fi, optical wireless using visible light, 400 to 800 terahertz.
It uses an LED light bulb that flickers faster than the eye can see, and a VLC visible light communication sensor reads the ones and zeros.
And the security aspect, Wi-Fi goes through walls. Li-Fi is literally just light, so it can't go through a wall. You put this in a secure command tent, close the door, and the network physically cannot leave the room.
It's totally contained.
And all these networks, Li-Fi, Starshield, tactical fiber, are managing modern drone warfare.
Over 23,000 active drone systems. High-res video streams straight to shooters. And it only works because LEO constellations provide that fast, low-latency backbone, even integrating with things like the AC-130 gunship.
It's an incredible system. So we've rapidly decoded everything from the EM spectrum equation to NDIS ionosphere bouncing modulation, TAC-OFC, LEO space lasers, and Li-Fi.
We covered it all.
So a final thought for you to mull over. We started with submarines using massive ELF waves. But if the future is local networks perfectly confined to light inside a closed room and global pipelines made of invisible space lasers, what does electronic warfare even look like tomorrow? How do you hack an enemy whose network is invisible and orbiting above the atmosphere? Moving to next chapter.
Welcome to the Chapter 2 revision module. Let's start.
Right, jumping right into the geometry of the airwaves. Cellular fundamentals. Networks are divided into regular hexagonal cell designs to guarantee bandwidth and optimal coverage.
Like a honeycomb.
Exactly like a honeycomb. And the core principle there is frequency reuse. Non-adjacent cells use the exact same frequencies to avoid co-channel interference while, maximizing users on a limited spectrum.
Okay, and when transferring an ongoing call between those cells, we have handoffs. or handovers. The hard handoff is break before make.
Yeah.
Basically like jumping from one moving train to another, it switches frequencies abruptly, which is good for VoIP and data.
Yeah, and then you have the soft handoff, which is make before break.
Right, like passing a baton in a relay race where both runners hold it for a split second to keep an uninterrupted link.
Precisely. And this all involves continuous signal monitoring and voice channel allocation to establish the call.
Okay, moving on to wireless evolution and WiMAX. From analog to all IP, 1G was just analog voice, and the basic network components were subscriber terminal devices, radio base stations, and the network switching infrastructure.
Yeah, but then GSM laid the real foundation. It uses TDMA, time division multiple access with 8 time slots.
And FDD, frequency division duplex, for separate uplink and downlink. I'll bring on 900, 1800, and 1900 megahertz bands, right? With data rates up to 270 kilobits per second.
Right. Then came the digital shift. GPRS made things packet-based and always on, and HSPA was the 3G improvement that pushed speeds up to 337 megabits per second.
Which led to LTE and 4G. Now, the source is called 4G and all IP network revolution. Does that basically mean our phones stopped acting like traditional radios and started acting exactly like computers plugged into a wall router?
That's a great way to put it, yeah. It used OFDM and MIMO antennas, pushing speeds from 100 megabits per second all the way to 1 gigabit per second. It supported high-speed mobility up to 500 kilometers per hour and peer-to-peer networking.
And for long distance, there's WiMAX, which uses a tower and receiver setup. The non-line of sight operates from 2 to 11 gigahertz for up to a 50-kilometer range.
While the line of sight version goes up to 66 gigahertz.
Okay, so segment 3, cutting the hardware cord. As things sped up, replacing physical hardware became too slow. Enter SDR, software-defined radio.
Right, SDR replaces traditional hardware functions like modulation, demodulation, and decoding with pure software-based signal processing.
The workflow is just raw signals moving through A to D, analog to digital, and D to A converters.
Yeah.
But tell me about the waveform concept. Why is that so revolutionary here?
Well, because entire physical layers are defined by software. It frees the communication infrastructure from being permanently trapped in outdated physical metal. You don't rebuild the tower, you just push an update.
So it's future-proof, multi-mode, multi-band, secure, and fully supports software updates and interoperability.
Exactly, which directly enables intelligent antennas, or IA. These use beamformation mechanisms to achieve ambient spatial reuse.
And the approaches there divide into full cognitive radio versus spectrum sensing, right? Across both licensed and unlicensed spectrums.
Right. And to manage that chaos, it runs the SEAT cycle, SEAT. Search and sense the spectrum, exchange and evaluate lists, access and allocate channels, and finally, transmit data or terminate.
Okay, segment 4, tactical tech in dynamic environments. Software-defined systems are perfect for unpredictable zones, which brings us to Manet's mobile ad hoc networks.
Yeah, Manet's feature dynamic topology and completely autonomous nodes.
The tactical components are normal nodes, like soldiers, gateway nodes like vehicles, and UAV relays like drones. But wait, if Manets rely on autonomous nodes constantly moving and forming dynamic topologies, doesn't that make them an absolute nightmare to secure compared to a fixed cellular tower?
Oh, absolutely. The text explicitly notes severe security vulnerabilities. Plus, they have massive bandwidth and energy limits.
Right, and to fix the multipath fading in those rough environments, they use MIMO multiple input, multiple output, using multiple antennas to fix the fading and literally double the data rates.
Which is heavily used in tactical SECOM, known as MOST, and massive MIMO is a huge part of 5G.
And to make it all run smoothly, you need an ADN, an application delivery network. The core components are the ADC, application delivery controller, and the WOC, WAN optimization controller.
Right, and their functions include dynamic app acceleration, load balancing, caching, compression, and running application firewalls.
Which brings us perfectly to segment 5, the ultimate digital fortress. Quantum and SAMD HAV. How do we secure this stuff? First, quantum communications.
Yeah, which uses photons for a physical layer alternative to traditional math-based encryption.
But for a practical, immediate indigenous ecosystem, there's SAMD HAV, Secure Army Mobile Barat version, built to mitigate data leakage and reduce foreign dependence via a CUG, a closed user group.
The architecture is incredibly strict, centralized admin, RBAC role-based access control, and fully India-based infrastructure.
And the physical hardening is intense. Hardened OS, app whitelisting, the indigenous M Sigma app, and physically restricted USB and data ports.
Plus the software security layers, block screen capture, end-to-end encryption, multi-layered auth, hardware-bound keys, and remote wipe capabilities.
But the best part is the integration. It's network agnostic. It rides on commercial operators like Airtel or Geo. It's 5G ready, ensures cyber sovereignty, C2 continuity, operator-assisted calling, auditing, and lifecycle management.
It's fascinating because it proves you don't need entirely new cell towers for a secure network. You just build a software and device fortress that rides safely on top of public networks.
Absolutely. Okay, final segment, the frontier of connectivity. 5G, 6G, and 7G. The general trend here is expanded coverage, massively increasing device density, and a transition to satellite networks.
Right. 5G launched in 2015, goes up to 100 gigahertz, speeds over 1 gigabit per second, 1 to 10 millisecond latency, and supports 1 million devices per square kilometer.
Then 6G, projected for 2030. Frequencies from 95 gigahertz up to 3 terahertz. Speeds around 11 gigabits per second with latency under 1 millisecond.
And that supports quantum and holographic services, AI-based networking, internet cognition, and 10 million devices per square kilometer.
Which is wild. But 7G in 2050 is the internet of everything. Over 11 gigabits per second, operating purely in the terahertz range. It supports space roaming, interplanetary communication, virtual space environments, and extremely realistic sensations through decreasing latency. Oh wait, it also says 1 trillion devices per square kilometer. You have to help me visualize that. What kind of devices are we even talking about if it's not just smartphones?
At 1 trillion per square kilometer, we're talking about microscopic smart dust. Sensors in the concrete, in your clothes, medical nanobots in your bloodstream. Everything becomes an active node.
Wow, we went from a 1G analog voice to 7G holographic interplanetary data.
Yeah, and it leaves you with a profound thought. If 6G brings holograms and 7G brings extremely realistic sensations in virtual space environments by 2050, you have to wonder, will the concept of physical travel or even physical presence become entirely obsolete in our lifetimes?
Moving to the next chapter.
Chapter 3, Revision Module. Let's begin.
Right, so diving straight into the physical foundation here. When you're revising data processing, you have to remember it's a strict sequence. It always goes aggregation, then decision-making, and finally data analysis.
Yeah, exactly. And, connected directly to that analysis phase are your data mining principles. For the exam, you need to firmly lock down its definitions and, well, its practical applications.
Right, because data mining isn't just like looking things up. You're trying to extract deep patterns.
Yeah.
But to even get to that point, the system performs 7 functions of data processing.
7 functions, right?
Yeah, but the core roles among those 7, the ones you really need to memorize, are storing data and retrieving data. And historically, that retrieval is strictly characterized by sequential access.
Which is a completely mechanical process. And that access characteristic is exactly how we differentiate storage mediums. Like if you look at tape storage, it uses physical magnetic particles, coated on a strip.
Yeah, the textbook definition of sequential access right there.
Exactly. I mean, think of it like, well, it's like fast forwarding a physical cassette tape. If you want the 5th song, you can't just skip to it. You have to physically wind past songs 1 through 4 to find it.
Which is why tape storage is highly suited for archival purposes. The mechanical latency is terrible, but for an archive, speed doesn't matter. You just need massive, stable storage.
Right. But obviously, that's terrible for an active network, which is why we contrast it with network-attached storage, or NAS.
Yeah, NAS operates as a file-level server.
A file-level server with networked access, right? And it has robust access control. So if tape storage is a cassette tape, NAS is basically a highly organized, instantly accessible digital filing cabinet for a whole office.
Oh, that's a perfect way to picture it. Anyone on the network, assuming they have the right robust access control permissions, can just instantly pull the exact file they need. Sequential access for network retrieval would literally cause the whole system to collapse from the latency.
Right, totally. So we have the storage down, but to actually manage all that hardware, you need an operating system. The OS is the primary software and hardware manager.
Yep, the ultimate boss of the system. And its key roles are you need to rattle these off coordination of tasks, memory allocation, storage management, and time sharing.
And that time sharing relies on time slices, right?
Exactly. The CPU divides its attention into these tiny microscopic time slices to juggle multiple things so fast that it just, looks like seamless multitasking to you.
So smart. And when we categorize OS architectures, you start with user systems. Those are your single-user platforms versus your multi-user platforms.
And multi-user platforms have a massive, strict requirement. They require user identification.
Right, because if you don't identify the users, the OS can't separate their memory or storage, and everything just cross-contaminates.
Precisely. Then, stepping away from standard user setups, you have your network and specialized systems, specifically distributed systems, which are completely linked computers acting as one single machine.
And on the totally opposite end, you have embedded systems. These are for highly specialized tasks, and they operate with extremely limited resources, like the computer inside a washing machine.
Right. Because of those limited resources, they commonly run embedded Linux or Android. They're just stripped completely down to the absolute bare minimum.
And speaking of specialized, we have to talk about real-time operating systems, RTOS. This is all about processing deadlines.
Yeah, and the division here is critical for your revision. You have hard RTOS and soft RTOS. A hard RTOS guarantees absolute zero delay. Missing a deadline by a millisecond is a total system failure. Think like an industrial pacemaker.
Wow, yeah. And then a soft RTOS, that accommodates non-critical constraints, right?
Exactly. It wants to hit the deadline, but if a video frame drops or audio stutters, the system doesn't catastrophically fail. It just accommodates it.
Okay, so then how does a batch OS fit into this? Because a batch OS groups similar non-urgent jobs together and processes them all at once. And it's heavily utilized in like finance and HR. But why?
Well, it has distinct operational advantages and disadvantages.
Right, but I mean, if we have real-time processing, why on earth do modern HR departments still use batch OS? I like to think of it like doing laundry. You wouldn't run the washing machine to wash a single dirty sock the second you take it off.
Oh yeah, that's a great analogy. You'd wait until you have a full load of darks, because the overhead of water and power for one sock is terribly inefficient.
Exactly. Real-time washes one sock instantly. Batch OS waits and washes everything together efficiently. That's why payroll uses batch OS. You group thousands of identical math equations to save CPU resources.
Yeah, you trade immediate responsiveness for maximum throughput. Now, transitioning from those back-end architectures, let's look at what you actually interact with: the desktop, laptop, and mobile OS platforms.
Right, which divides strictly into desktop environments and mobile environments. Under desktop and laptop, Microsoft Windows is obviously the big one. Make sure you note version 7, 8, and 10 for the exam.
And then there's Mac OS X, which is developed by Apple. The key term there is proprietary.
Proprietary, meaning they completely lock down the hardware and the software.
Right, it's totally closed. Unlike Linux, which is open source, anyone can view or modify it. And Linux has free distributions you need to know, specifically Ubuntu, Mint, and Fedora.
Got it. And for mobile OS platforms, you've got Apple iOS, Google Android, and Windows Phone. And all of these are completely specialized for mobile tasks, right?
Yeah, they manage touchscreen interfaces and battery constraints. But to connect this back, you really have to contrast all these commercial desktop and mobile platforms with the embedded systems and RTOS we just covered.
Oh, because Windows and iOS are generalists, right? They're multi-user platforms running a million time slices. They absolutely cannot guarantee zero delay like a hard RTOS can.
Exactly. You would never run an aircraft's flight controls on Windows 10.
Yeah.
Okay, so we've got the OS. Now, how do they communicate? This brings us to internet fundamentals and architecture.
Right. The internet is fundamentally a global network of networks. And historically, it originated from the ARPANET back in 1969 as a military experiment.
Yeah, designed to survive a nuclear strike by being decentralized. And physically, that network relies on the backbone.
The backbone! Those are the massive high-capacity trunk lines, right? Yeah. Bundles of fiber optic cables running under the oceans.
Exactly. But you don't connect straight to the backbone. There's an access architecture made up of 3 entities. First, the ISPs, or internet service providers, who actually own the host computers.
And then the clients, which are basically just our personal computers and mobile devices.
Right. And third are the servers, the actual service providers hosting the data. Now, to navigate all this, the system uses precise addressing systems. First up is IP addresses.
IP addresses formatted as dotted octets?
Yep, 4 blocks of numbers. It provides a numerical code that uniquely identifies every device.
But because humans can't memorize random numbers, we use DNS, the domain name system. That translates human-friendly names into those IP addresses.
Exactly.
So an IP address formatted as dotted octets is basically like exact GPS coordinates, right? Just raw math. math.
That's spot on.
And the DNS acts like the contacts app on your phone. You just type in mom or Google, and the system translates it into the messy numerical code behind the scenes.
Right. And sitting on top of that whole physical and addressing infrastructure is the World Wide Web, the WWW.
Which is specifically what utilizes hyperlinks, multimedia, and plugins to deliver content.
Yes. Now, because all that data is constantly traveling across the backbone, we have to protect it. So let's jump into cryptography principles. And we start by distinguishing actual cryptography from basic value mapping and encoding.
Right, encoding uses codebook access. Like, let's say the number 1 maps to male and the number 2 maps to female.
Exactly.
But wait, I want to be really clear on this for the revision. What is the fundamental difference between that simple value mapping and actual enciphering?
Well, value mapping is static. Anyone with a codebook can read it. But the cryptography process dynamically transforms plain text through a process called enciphering, using a mathematical key.
Ah, right. And that creates completely garbled ciphertext.
Exactly. And deciphering is the exact reverse process. It requires that specific key, which prevents unauthorized decryption by an intruder on the network.
And mechanically, these systems use a cipher alphabet, right? And they rely on substitution for character replacement.
They do. But for this to work, there are strict core requirements, specifically adhering to a reversibility constraint and consistency maintenance.
The reversibility constraint, meaning if you scramble a file into ciphertext with a key, the math has to guarantee you can perfectly unscramble it later.
Right. If it's not perfectly mathematically reversible, you didn't secure the data, you destroyed it. And consistency maintenance ensures the algorithm produces the exact same ciphertext every single time you use that specific plaintext and key combination.
Okay, that makes sense. So taking all of this OS platforms, network infrastructure, and cryptography, let's apply it to a real-world secure environment, data security, and the BALS OS.
But before we talk about BALS, remember that software and database integrity requires transaction management and structured updates.
Structured updates to achieve reduced redundancy.
Exactly. You have to ensure updates apply across the entire distributed system evenly or not at all. Now, applying all those integrity and cryptographic rules brings us to BIOS.
For operating system solutions.
Yes, it is an indigenous, free, open source Linux distribution.
So it builds right off that open source Linux architecture we talked about earlier.
Exactly. And you need to know its features. It has national certification, it supports over 18 Indian languages, and it boasts robust resistance to security threats and malware.
Right, which gives it massive advantages, like significant cost effectiveness because it's free. And it provides massive strategic advantages for the armed forces.
Yeah, because it's a sovereign OS.
Yeah.
They aren't relying on a proprietary foreign system for highly classified data.
And despite being so secure, it still has immense versatility. It actually runs Windows applications via virtualization.
Yeah, in a secure sandbox.
Yeah.
And it's deployed in both desktop and server versions, allowing for extensive customization across the board.
Moving to next chapter.
Welcome to the Chapter 4 revision module. You need rapid data collection on the battlefield to manage troop movements, so think of the Intervehicular Information System, or IVLIV, as the central nervous system keeping units alive while dispersed against threats.
Right, and to keep that nervous system alive, you have to feed it, rapid-fire facts from 4 specific types of surveillance assets. First, you've got geostationary satellites.
Yeah.
They provide continuous satellite surveillance. Second, you use UAVs, unmanned aerial vehicles. Those handle your tactical reconnaissance behind enemy lines.
Because they can fly into the clouds, right?
Exactly. Then third, you have BFSRs, which are ground-based surveillance radars. Those provide close-range monitoring of the battlefield.
Right.
And finally, you have UGS, unattended ground sensors. They deliver actionable local information with a direct link to controlling units.
Okay, but all those sensors require a highly reliable, cost-efficient physical backbone to transmit their data, right?
Yeah, absolutely. You need to know the network scales and physical building blocks. So you have LANs for local area, MANs for metropolitan area, WANs for wide area, and WLANs for wireless LAN.
And the physical cables carrying all that are twisted pair, coaxial, and fiber optic.
Spot on. But how you arrange them physically is just as important.
Right. The 4 network topologies. Let me just rattle these off. First is the star topology. That's a central hub or switch, sort of like a wheel with spokes.
Yeah.
Second is the ring topology. That's a continuous circle for neighbor-to-neighbor data transfer.
Correct.
Third is the bus topology, which uses a single common cable as a backbone, usually with an end server or controller. And fourth is the mesh topology, where all nodes are interconnected.
Right.
But mesh offers the high reliability needed for a battlefield, but the trade-off is complex management, right?
Oh yeah, it's a massive logistical headache. But once that physical network is built, the data flowing through it has to be directed, compressed, and heavily protected.
So how do we direct it?
The key network functions. You've got routing, bridging, and flow control.
Okay, and for protection.
Security protocols. You absolutely need authentication, passive monitoring, and the IDS, the intrusion detection system.
And the IDS uses specific techniques to find threats, right?
Yeah, 2 mainly. Pattern matching and event-oriented analysis.
Got it. Okay, let's talk about speeding up the network. You optimize it using compression.
Right.
So you've got lossy compression, which removes data entirely. That's used for like audio and images.
Yeah, you wouldn't use that for military coordinates.
Right. For tactical data, you need lossless compression because that allows exact reconstruction of the data. And you also use protocol optimization to enhance network speed, right?
Exactly. It strips away the metadata. But we also need to talk about wireless mobility. WLAN uses access points based on the IEEE 802.1 Wi-Fi standard.
But there are challenges with wireless networks in the field, right?
Yeah, 4 exact challenges: noise, false alarms, blindness, and system vulnerabilities.
And you mitigate those how?
With heavy encryption.
Okay, so let's scale this up to the command level for strategic military application and paperless functioning.
Right, we have to look at the specialized systems. First is a Sigma.
That's the secure messaging system, right?
Yeah, secure messaging for paperless functioning. It features multi-level security, a dynamic global address book, and it runs on a fiber optic backbone using VLANs and firewalls.
Oh, okay. And what about the Army Internet?
Well, the Army Internet and HCC security relies on WAN segmentation, bulk encryption units, and coordinated IP addressing.
Got it. But for the actual soldiers on the ground, you have the BMS, the Battlefield Management System.
Yeah, that's crucial.
It acts as the sensor-to-shooter loop right now. It integrates wearable computing, situational awareness, and GIS map overlays.
Exactly. And the strategic C4I2 systems managing all of that from above are asteroids and the MORE, the Modified Operation Room.
What do they actually do?
They emphasize specific features like digital map interfaces, terrain analysis, and satellite imagery integration.
Right.
The reason why we use them is they dramatically accelerate the decision action cycle and act as force multipliers by enabling real-time data transfer.
Okay, that makes sense. But building all this is hard. So the military integrates modern civilian biometric ecosystems too, right? To enhance strategic operations without relying solely on traditional internet networks.
Yeah. Two main civilian systems you need to memorize. First is DigiLocker.
That's the secure personal electronic space, right? With exactly 1 gigabyte of storage linked to Aadhaar.
Right, and its purpose is to minimize physical document use within its participant structure using robust security.
And the second system.
DigiYatra, for contactless travel via biometrics. The vital detail here is that PI, personally identifiable information, is stored locally on the smartphone.
And then it's purged after 24 hours.
Exactly, leaves no trace.
Okay, so let's break down the exact sequence of the airport FRS, the facial recognition system. It detects faces using neural networks, right?
Yeah, that's step one.
Then it extracts 30 nodal points. It represents the face as a faceprint vector. And finally, it matches it against a database.
Spot on. And these exact biometric systems have utility for the armed forces, specifically for garrison security, population monitoring, and non-stop surveillance.
And the best part is they operate even without the internet.
Crucially, yes, even without the internet. And all of this, from IVIS to biometrics, it leads to the ultimate goal, which is completely transforming conventional operations.
Because conventional systems have so many limits, right?
Oh, tons. You have visual and electronic sighting limits, positional accuracy issues, human and logistical constraints, information delays, and hierarchical and technical bottlenecks.
Right. So to synthesize all of this digital transformation overcomes every single one of these barriers by accelerating information flow and enhancing battlefield awareness.
That's exactly it.
Moving to the next chapter. Chapter 5, revision module. Let's start.
Right. If you are prepping for this exam, you need to lock in right now. We are going rapid fire through the exact technical specifications of how humans interface with digitally simulated environments, moving all the way through the AI powering them.
Yeah, so we begin with reality technologies. To establish your baseline, virtual reality, or VR, is an entirely new enclosed world. Augmented reality, AR, is a digital overlay placed onto the real world.
Exactly. And mixed reality, or MR, is the physical hardware integration that blends both together. Let's hit the VR specs first.
Okay, so for your notes, VR is explicitly a computer-simulated environment. But to actually function, it must provide sensory feedback to effectively simulate a physical presence.
Right, and you need to memorize the 4 core pillars that make this work. That's interactivity, immersion, sensory feedback, and telepresence.
And when you successfully integrate those 4 pillars, they synthesize what we define as a sense of presence for the user, right? It basically tricks the brain.
Yeah, exactly. And the hardware systems scale across 3 distinct levels of capability. You have non-immersive, semi-immersive, and fully immersive systems.
Moving on to the military applications for VR, they're highly specific. You need to know we use them for healthcare scenarios, automotive prototyping, spatial architectural feeling, and occupational hazard training.
And the primary advantage you must remember across all those military use cases is high safety. Operators execute highly dangerous protocols like diffusing digital explosives without any physical risk.
Right. So let's move to augmented reality. AR functions by overlaying computer-aided design, or CADE, directly onto the physical real world.
Yeah, and there are 2 types you have to lock down here. Marker-based AR requires actual visual markers, think like a QR code on a table to project 3D objects.
While markerless AR utilizes complex image extraction technologies for general environment recognition, so it just maps the room dynamically.
Right. And applications for AR include industrial assembly view replacement. This is where digital instructions literally replace physical manuals, overlaying directly onto the engine block you are repairing.
And in medicine, AR is used in medical X-ray examples, projecting internal scans seamlessly onto the patient's physical body during surgery.
Exactly. Then we have mixed reality, or MISRCUF. For the module, just define this as the system that physically combines both AR and VR concepts. It does this by utilizing specialized display trackers, sensors, and hardware processors.
Now, you can't run these reality simulations on a basic hard drive. These complex reality simulations require massive, organized infrastructure to host them.
Which brings us to cloud and edge computing. Cloud architecture is defined by internet-based virtual shared servers. Picture divided into 2 distinct segments.
Right. The front end consists of the client devices and user applications, basically the interface you actually touch.
Yeah, and the back end is the engine. It contains the data storage, the middleware communication protocols that translate the data, and the central administration.
There are 2 deployment models you absolutely need to know: the hybrid cloud and the private cloud.
Take note here, the private cloud is the established military standard. You cannot have open source access. It relies on highly stringent access controls.
For sure. The service stack layers then dictate the system's capability. IaaS is infrastructure as a service, which provides the raw virtual hardware.
POHAS is platform as a service, supplying the development platform so engineers can build apps. And SaaS is software as a service, delivering the final, polished end-user software.
But wait, let's unpack the logic here for a second. If this centralized cloud computing architecture is so massive and powerful, why do military systems actively mandate the use of edge computing? Doesn't that defeat the purpose?
It strictly comes down to latency. In a combat scenario, a half-second delay is the difference between an evasive maneuver and losing a drone. Edge computing solves this by bringing the data processing locally to the device itself.
So removing the need to transmit data back and forth to a central cloud server ensures ultra-low latency.
Exactly. That speed is critical for real-time actions and is an absolute requirement for autonomous systems operating in combat environments.
But standard cloud infrastructure, even at the edge, ultimately hits physical limits in the silicon. Moving past those microchip bottlenecks requires entirely new mathematical computing paradigms and unbreakable security structures.
Right, let's compare classical computing to quantum computing. Imagine a classical bit acts like a standard light switch. It is rigidly set to 0 or 1, off or on.
But a qubit, the fundamental unit of quantum computing, is like a spinning coin.
Yeah, that spinning coin state is defined as superposition. It is both heads and tails simultaneously until you measure it. Quantum computing harnesses this quantum mechanics principle to execute complex problem solving.
It achieves incredibly high-level optimization while maintaining very low energy consumption.
Exactly. And crucially, whereas classical computing relies on rigid Boolean algebra, quantum computing operates using linear algebra, allowing for multidimensional calculations.
The ultimate benchmark of this technology is quantum supremacy. You need to cite the Google Sycamore processor for this.
Right. It demonstrated supremacy by solving a problem in 200 seconds that would take a classical computer 10,000 years to process.
And that processing speed allows military applications to focus on massive strategic development. They use it to run vast scientific simulations of complex maze-like logistical paths that classical algorithms simply cannot map in a usable time frame.
But generating that immense data output requires unbreakable security, which introduces blockchain. For revision, define this as a secure hashing structure, entirely based on consensus mechanisms.
So in a blockchain, individual network nodes must validate and then add transaction blocks to the ongoing chain.
Yeah, and this process is executed strictly via network broadcast. No single entity controls it.
The ultimate security mechanism you must memorize within this structure is the keyless signature infrastructure, or KSI.
Right. By utilizing advanced hash functions rather than traditional keys, this mathematically provides unhackable code.
Military applications for blockchain capitalize on this absolute immutability. Once data is logged, it cannot be altered.
Yeah, so it is deployed for logistics tracking, secure finance, system integrity monitoring, and impenetrable secure messaging between command nodes.
Which brings us to the data itself. Massive computing power generates massive data, demanding specialized methods to capture and analyze intelligence. So how do you deal with data volumes that literally break traditional software capabilities?
We define it as big data. These are structured and unstructured data volumes that exist far beyond traditional software capacities.
And managing them relies entirely on parallel processing methods distributed simultaneously across thousands of separate servers.
Exactly. The definition for your exam hinges on the 5 E's of big data. Volume, representing the raw, massive quantity of data. Variety, representing the disparate types video, text, thermal imagery.
Then there's velocity, representing the blinding speed of data generation. Variability, referencing the inconsistency within the data streams when sources drop in and out. And veracity, which measures the fundamental quality and accuracy of the data itself.
Managing those 5 V's presents massive operational challenges for the military. Systems must constantly process the capturing, storage, analysis, search, sharing, transfer, and updating of this data without crashing.
We apply this directly to military intelligence, surveillance, and reconnaissance, or ISR. To parse big data, military ISR utilizes artificial intelligence techniques like Bayes' theorem, pattern recognition, and graph theory.
Yeah, think about Bayes' theorem. It mathematically updates the probability of a threat as new evidence comes in, constantly adjusting the battlefield picture.
Integrating those mathematical models generates distinct operational applications, right? Like providing predictive capability, incident anticipation, historical event comparison, automated threat alerts, and deep social media information mining.
Exactly. And in the cybersecurity domain, this analysis is critical for identifying advanced persistent threats, or APTs. By processing massive data logs, the AI identifies APTs specifically by tracking their modus operandi, their behavioral patterns across the network over time.
Down to the tactical level, these integrations rely on wireless sensor networks fused with radio frequency identification, or RFID systems.
Right, and this network processes big data to predict logistics shortfalls and gathers highly actionable intelligence long before physical supply chains fail.
Now, the primary tool used to make sense of all this big data is artificial intelligence. Let's trace the evolution really quickly. The term AI was officially coined at the 1956 Dartmouth Conference.
Yeah, it's the broad categorization covering machine learning, deep learning, and the hypothetical concept of artificial superintelligence, or ASI.
Machine learning, or ML, functions via self-algorithm discovery, and it operates in 3 specific ways.
First, supervised learning utilizes manually labeled data. You basically tell the system what a tank looks like. Unsupervised learning focuses entirely on unguided pattern discovery within raw data. And reinforcement learning relies on strict trial and error feedback loops, rewarding the system when it succeeds.
Deep learning, or DL, expands on this by utilizing multi-layer neural networks to build hierarchical representations of data.
Right, this mimics the human brain's architecture and is applied to advanced natural language processing, or NLP, and complex computer vision.
The generative AI takes this processing power and actually creates new data. This category includes large language models, LLMs, and generative adversarial networks, or GANs.
And you really need to understand the mechanism of a GAN. Think of it exactly like a high-speed game of cat and mouse between a ruthless art forger and a master detective.
Now, the mechanism relies on a generator that creates synthetic content, the forger painting a fake image. Then, a discriminator rigorously checks it for flaws, the detective hunting for pixel errors.
Exactly. They fight millions of times a second until the fakes are flawless. Military and analytical applications for GANs utilize this mechanism for high-resolution satellite analysis, image restoration of degraded footage, and rapid fraud detection.
However, deploying AI carries extreme operational risks. You must list these system risks for the exam. Models suffer from societal bias derived from historical prejudices embedded in the training data, leading to complex debiasing challenges.
Yeah, and other risks include a lack of system transparency, massive privacy violations, AI hallucinations where the system just fabricates facts, hyper-realistic deepfakes, and massive intellectual property theft issues.
Having defined the algorithms and their risks, we must map the global AI ecosystem. You need to know the players here. The pioneers driving foundational models include OpenAI and Google DeepMind.
The integrators physically deploying these models into tools include Microsoft, Meta, and Anthropic. The safety specialists focusing strictly on guardrails are led by Cohere.
You must also track the Chinese tech giants shaping the geopolitical landscape. Right. So that's Baidu, Alibaba, and Tencent. Finally, the open source community democratizing access is driven by platforms like Hugging Face and Stability.ai.
Which raises a massive security question. With an open source community operating alongside major tech giants, how is the military safely integrating this software into physical platforms?
It's done through strict regulatory and geopolitical frameworks. The baseline regulations you need to cite include the EU AI Act, US initiatives, and China tech integration challenges.
Yeah, and for the military specifically, the absolute regulatory focus is examining and establishing distinct, unbreakable control levels for autonomous weapons.
And direct military applications of these algorithms are widespread. Computer vision is deployed for automated target recognition and satellite imagery trajectory analysis.
While data fusion algorithms are utilized to combine disparate sensor feeds to generate predictive analytics across the battlefield.
And the unmanned physical platforms deploying these algorithms are categorized into 3 areas. You've got AI-guided drones in the air, unmanned ground vehicles, or UGVs, and unmanned underwater vehicles, or UUVs.
In proactive border surveillance, AI systems monitor the line of actual control, or LAC, utilizing autonomous thermal imagers fused with advanced radar data to track incursions instantly.
Examining regional implementations, Indian C4I systems developed by AR and DRDO actively use indigenous technology.
Right, these systems provide advanced command decision dashboards, secure communications, and the control architecture for autonomous swarm technologies.
We also deploy AI into highly specialized reconnaissance robots. Their specific military applications include automated camouflage detection, dynamic battery life optimization in the field, and real-time threat identification in hostile environments.
But you have to understand this. AI is not limited to central servers or standalone robots. It is embedding into every single piece of physical hardware. This is called ubiquitous or pervasive computing.
Right, and ubiquitous computing operates on the strict 4 any rules: any device, any time, any place, and any data format.
It requires minimal human interaction to function. The key hardware technologies enabling this invisible network are RFID tags, digital middleware, and software agents that act on your behalf.
The physical scale of these devices is staggering, too, ranging from millimeter-sized computational dust scattered in an environment up to wearable tabs, handheld pads, and fully interactive boards.
Wait, if we are looking at the exam requirements, ubiquitous computing and the Internet of Things sound identical. Both involve scattered sensors. What is the strict technical difference for revision purposes?
The distinction comes down to configuration and identity. The Internet of Things, or IoT, evolved directly from ubiquitous computing but requires active configuration.
Right, IoT mandates the use of unique identifiers, or UIDs, to transfer data across a network. Ubiquitous computing, by contrast, relies on dispersed, highly invisible processing without needing that same rigid node configuration.
The IoT ecosystem functions in a rigid 4-step cycle. You must memorize these steps. First, sensing the environment through physical devices. Second, communication of that data via network gateways.
Third, processing the data centrally in the cloud. And fourth, action executed through automated hardware responses.
When you apply IoT to defense, it becomes the Internet of Military Things, IOMT, also referred to as the Internet of Battlefield Things, IOBT. This requires 3 distinct architecture layers to function.
Right, so the Info C2 layer processes the command and control information. The effector layer consists of the actual physical assets executing the mission, specifically soldiers and tanks.
And finally, the networking infrastructure, physically and digitally, links the command layer to the effector layer.
Verified IOMT applications include tracking soldier health biometrics in real time, fleet fuel tracking to optimize logistics, automated smart-based screening for security, and acoustic sensor training programs.
Now, the convergence of that IoT hardware and AI software brings us to the final stage of this module, agentic AI and future research frontiers.
Yeah, agentic AI in military applications involves autonomous systems operating entirely independently of manual commands.
These agents are utilized for independent navigation, complex target recognition, dynamic decision support for commanders, and real-time operational planning.
What exactly comprises the action loop that gives an AI system its agency, though? How does it actually operate without us?
Well, the action loop is a 3-stage mechanical process. First, planning, where the AI mathematically identifies the goals and parameters. Second, deciding, where it calculates probabilities to choose the optimal operational path.
And third, acting, where it executes the physical steps required without asking for human permission.
The core functions of this action loop yield massive tactical benefits. It provides autonomous logistics management, autonomous threat response, and real-time network defense.
Yeah, and the strategic benefits include radically enhanced situational awareness, optimized staff time management because the AI handles the data, and unprecedented rapid defense speeds against incoming threats.
Scaling this technology into the future requires navigating the strict 5 pillars of future research. Pillar 1 is establishing user trust and transparency within the algorithms, so commanders actually believe the AI's data.
Pillar 2 is robustness and generalization. The models must have absolute real-world reliability and rigorous mathematical resistance to adversarial attacks trying to poison their data.
Pillar 3 is efficacy and sustainability. The hardware processing this AI must achieve low energy consumption, a reduced carbon footprint, and high computational efficiency to operate in remote theaters.
Pillar 4 is causal and long-term reasoning. This is huge. The AI must be able to analyze complex cause and effect relationships and temporal contexts, definitively moving beyond basic pattern recognition to truly understand why an event is happening.
And Pillar 5 is multimodality and embodied intelligence. This requires the AI to physically interact with the real world, utilizing fused visual and auditory inputs.
Right. It relies on few-shot learning for rapid field adaptability, meaning it learns from just a few examples, and lifelong learning for continuous, uninterrupted adaptation as the battlefield changes.
Powering this future paradigm requires highly specialized hardware architecture. Standard chips just won't work. The industry relies on ASICs, application-specific integrated circuits, and TPUs, tensor processing units.
Yeah, these are entirely custom designed at the silicon level to handle high-speed machine learning workloads and facilitate massive, large-scale training models.
Just think about what happens when those ASICs are eventually replaced by the quantum architectures we discussed earlier. The speed of that action loop will become instantaneous.
Exactly.
Moving to the next chapter.
Chapter 6, Revision Module. Let's begin.
Right, so we are jumping straight into the foundational elements of information warfare today.
Yeah, we have to move fast. No fluff today. You need to know this stuff cold.
Right.
So we are looking at how militaries basically hide the truth and project lies to control perception, right?
Exactly, because in information warfare, perception is reality.
Okay, let's use a rapid analogy to lock this in. Think of Operation Security, or OPSC, as a black box.
Right, a black box.
It hides the truth by absorbing everything and emitting nothing. And then conversely, you have military deception. Think of that as a decoy.
A decoy, right, because its entire function is actively projecting lies.
So let's rattle off the mechanics of both and how they merge into tactical information warfare. First, OPSC.
Okay, so OPSC is a formal process. The goal is to identify critical info, reduce your vulnerabilities, and strictly hide indicators.
Hide indicators, so the enemy cannot derive friendly plans. It's all about hiding the truth. And there's a 4-step process for OPSC. Let's hit them. Step 1.
Step 1 is analysis of threat.
Analysis of threat, so figuring out who is looking.
Right, identifying the adversary and mapping their collection capabilities.
Step 2.
Analysis of vulnerabilities.
Which means asking, where are we leaking information, right?
Exactly. Pinpointing where your own indicators can be observed. Then step 3 is assessment of risk.
Assessment of risk. Calculating the probability of the enemy exploiting those vulnerabilities.
Yep. And if that risk is too high, you go to step 4, which is application of measures.
Application of measures. Executing the actual countermeasures to conceal the truth. Okay, that's the black box. Now the decoy. Military deception.
Military deception is it's a commander planning process, and the operational method is solely projecting lies.
Creating a false narrative. And when you merge OPSC and military deception, you get tactical information warfare.
Right, tactical information warfare. You integrate the black box and the decoy to completely control the adversary's perception.
Which transitions us right into PSYOPs, psychological operations.
Yeah, PSYOPs is using information and propaganda to systematically influence opinions and emotions.
And the purpose here is to shift behavior, right? Shifting the behavior of enemy, neutral, or even friendly groups to support military plans.
Exactly. And you need to know the specific targets for PSYOPs. They target high-value command and control, or C2, structures at the operational and tactical levels.
Targeting C2 structures. Got it. And PSYOPs relies on the principle of psychological impact, right?
Yes, the principle of psychological impact. But it achieves this via truth projection, which is key.
Right. Unlike deception, which is just lies, PSYOPs will use the truth to demoralize you. Okay, next up. Perception management, or PM. There's a 4-step cycle for PM.
Right. Step 1, how you think you are perceived.
Step 2, how you are actually perceived.
Step 3, how you want to be perceived.
And step 4, how you will change that perception. What is the core objective of perception management?
The PM core objective is to influence the reasoning of foreign audiences to get favorable official actions.
Influence reasoning for favorable actions. And the primary components of PM are OPSEC and deception.
Yes, and it heavily utilizes impression management tactics.
Impression management. Okay, but to manage perception, we need to know what influences it. Let's break down the perception influences. There are 3 categories. First is perceiver factors.
Right, how the target's own mind works. There are 3 parts here. First is their schema, or past experience.
Schema and past experience. Second is their motivational state. Right?
Yeah, their motivational state, which is based on their needs and values. And third is their current mood.
Current mood. Okay, the second category of influence is information factors.
Mainly ambiguity. If information is ambiguous, the mind fills in the blanks.
Right, and the third category is target factors.
Which primarily comes down to social status.
Social status, got it. Okay, moving to body section 2, command and control warfare, C2W, and information operations. We are seeing a doctrinal shift from physical armor to speed and cyber.
Huge shift. CDW integrates military capabilities to basically fight the ODA cycle war.
The OD cycle. Observe, orient, decide, act. And the core principle of C2W is what?
The core principle is strictly to protect your own C2 while maintaining continuous ops. Protect your brain while fighting.
Protect own C2. Okay, there are 5 pillars of C2W. Let's rattle them off. 1, OPSEC.
2, military deception.
3, PSYOPs.
4, electronic warfare.
And 5, physical destruction.
Right, and these 5 pillars are grouped into disciplines like C2 protect, which is defensive, and attack principles.
Defensive and attack. And this all falls under the umbrella of information operations, or IO.
Exactly, and IO is conducted in the military information environment, the MIE.
The MIE, which is a key subset of the global information environment, right?
Yes, and the goal of IO is threefold. Enable, enhance, and protect friendly info while exploiting or denying adversary capabilities.
Enable, enhance, protect. Now, the information warfare principles. There are 3 big ones you need to memorize.
Number 1, prioritize cyber over geography.
Cyber over geography. Number 2, prioritize speed over armor.
Speed over armor. And number 3, identify your own targets by gathering intelligence and expertise.
Gather intel. And IW has 2 modes, offensive IW and defensive IW.
Right. And then we have the 7 forms of information warfare.
Let's hit the 7 forms fast. Form 1, command and control warfare.
Form 2, psychological warfare.
Form 3, hacker warfare.
Form 4, information blockades.
Information blockades. Form 5, targeting database trade.
Right, hitting the economy. Form 6 is cyber warfare, which means disrupting the actual info circuits.
Disrupting info circuits. And Form 7, shifting the balance of knowledge.
Right, making sure you know everything and they know nothing.
Okay, body section 3. Cyber threats and organizational infrastructure. Hardware and software weapons. Let's list the 6 software cyber threats. Number 1, computer virus.
A computer virus is strictly a host-dependent code fragment. It needs a host.
Host-dependent, got it. Number 2, a worm.
A worm is self-replicating.
Self-replicating. Number 3, Trojan horse.
Camouflaged malicious code.
Number 4, logic bomb.
Code that triggers only under specific conditions.
Number 5, top or probe virus.
A scout virus used to map vulnerabilities.
And number 6, assassin virus.
Which is for targeted surgical destruction of data.
Assassin virus for targeted destruction. Now, hardware threats. There are 3 primary ones. First, chipping.
Chipping is physically inserting malicious hardware into the supply chain.
Supply chain compromise, got it. Second, nanomachines.
Microscopic mechanisms that alter hardware.
And third, microbes.
Biological microbes literally engineered to consume electronic components.
Eat the circuits, insane. Next, high-power microwave weapons, HPM. They have 3 escalating effects.
Effect 1 is scrambling.
Which causes temporary effect.
Right, temporary. Effect 2 is functional upset.
Functional upset, which means degradation of the system.
Yes, and effect 3 is terminal burnout.
Terminal burnout, permanent destruction of the hardware.
Exactly. Okay, now we have to strictly map the organizational infrastructure, every level.
Yes, you have to know the hierarchy. Starting at the very top, the national level. Who is in charge?
The DGMO and the DDGMO.
Director General of Military Operations. Moving down to the military HQ level.
That is managed by the Management Staff Officer for IW.
Management Staff Officer? Down to the division level.
2 cells here, the PSYOP cell and the EW and Cyber cell.
PSYOPs and EW and Cyber. Go core level.
The core level has the Joint IW Board, the Joint IW Committee, and the Networking and Space Cell.
Board, Committee, and Networking and Space Cell. And finally, the command level, which has 6 specific groups. Let's rattle them.
1, C2W Group. 2, Assurance Agency.
C2W Group, Assurance Agency. 3, Intelligence and PsyOps Group.
4, Hacker and Cyber Warfare Group.
Hacker and Cyber. 5, Information Security Group.
And 6, Infrastructure Development Agency.
Okay, lock those in. Moving to body section 4, Information Systems and Dominant Battlespace Knowledge, or DBK.
Right, let's use the central nervous system analogy for the 4 elements of information systems.
First is the sensor element. These are the eyes.
Right, the sensor element is strictly for data collection.
Data collection. Second is the transmission element, the nerves.
Transmission is for the movement of data.
The movement. Third is the communication element.
Communication is for routing the data.
Routing. And fourth is the command and control element.
That's the brain, where decisions are made.
Okay, and these 4 elements facilitate the info flow process. And this process utilizes long-range civilian data, right?
It does. The purpose is to exploit intel systems and support national objectives.
Support national objectives to generate information power. And it generates that power across 4 areas: space, intel, commercial networks, and electronic systems.
Exactly. And that information power is required to achieve information dominance.
Information dominance, which is defined as gaining and controlling knowledge to dominate air, sea, and space using lethal and non-lethal means.
Lethal and non-lethal means, right? Now, to achieve this, you need defensive and offensive ops.
Let's define defensive ops.
Sure.
3 mechanisms. Mechanism 1, information protection.
Information protection uses active detection and passive defense.
Active detection, passive defense. Mechanism 2, information assurance.
Information assurance protects the ODA loop,
Protects the loop. Mechanism 3, information security.
which prevents exploitation.
Prevents exploitation. Okay, offensive ops. 2 mechanisms here. Mechanism 1, information attack.
Information attack inhibits enemy systems through spoofing and destruction.
Spoofing and destruction. Mechanism 2, information denial.
Denial executes via direct attack or jamming.
Direct attack or jamming. And the specific tools they use are precision attacks, computer viruses, and electronic sabotage.
Right, and the ultimate goal of offensive ops is misinformation, deception, and information superiority.
Information superiority. And when you combine all of this, you get info control and sustainment.
Yes, integrating air, space, sea, and land assets to achieve DBK.
DBK. Dominant battlespace knowledge. Know that term. Okay, final section. Body section 5, network-centric warfare, or NCW, and the strategic information environment.
NCW is crucial. It uses wireless networking protocols, specifically CDMA, GSM, and Tetra.
CDMA, GSM, Tetra. So data-enabled radios, transportable terminals, wideband media.
Exactly. And the most essential feature of NCW is data audits.
Essential feature is data audits. Remember that. Now, NCW has 5 primary objectives. Let's hit them hard. Objective 1, develop information base.
Develop information base means database mapping adversary capabilities and forecasting their actions,
Database and forecast. Objective 2, deny and protect.
which means hiding friendly forces and securing ops.
Hide and secure. Objective 3, influence adversaries.
Shape their perceptions, break their will to oppose, and influence non-combatants for neutral support.
Influence non-combatants, right, to prevent resistance. Objective 4, protect decision-making.
Safeguard internal processes and info structures.
Safeguard internal processes. And objective 5, deceive and degrade.
Executed via deliberate deception and physical or digital decapacitation.
Decapacitation. Okay, targeting and speed principles. There are 7 principles here. Rattle them off.
Sensor primacy. Alacrity.
Alacrity means speed.
Right. Knowledge survivability. Structure and power. Interoperability.
Interoperability,
Hierarchy. And intensity.
hierarchy, and intensity. And all of this is driven by dynamic networking.
Yes, dynamic networking is built on the purpose of info sharing and the 4 tenets of self-synchronization.
Self-synchronization. It generates combat power via superior knowledge, command and control, and C4ISR systems.
C4ISR. Let's spell that acronym out. Communications,
Computers,
intelligence,
surveillance,
and reconnaissance.
reconnaissance. Got it. And that elevates tactical networking into strategic information warfare, which involves global data collection and
It's
process.
global data collection.
Yeah.
And this happens in the global information environment, the GIE.
With GIE, let's list the actors in the GIE.
Media and journalists, NGOs,
Think tanks, academic institutions.
and public individuals. And remember, the military information environment, the MIE, interfaces directly with the GIE for command objectives.
MIE interfaces with GIE. Finally, let's list the strategic impacts of all this.
The impacts are electronic sabotage, national security vulnerabilities, espionage,
Espionage, terrorism,
and economic competition.
economic competition, which is driven largely by post-Cold War politics. Review this list immediately. Moving to next chapter.
Chapter 7, electronic warfare. Let's get right into it.
Absolutely.
Because if you're cramming for this exam right now, you probably know that the most intense battles today aren't actually fought with bullets.
No, they're not. They are, completely silent, invisible.
Right, just electromagnetic waves crashing through the air. And our mission for this deep dive is to decode all of that. We're going to break down the jamming, the radar deception, all the invisible chess moves.
Because if you lose control of the spectrum, your multi-million-dollar fighter jets are blind.
Yeah.
Precision missiles just fly straight into the dirt. It is catastrophic.
Totally. So let's start with the playing field. The core strategic aim here is dual purpose.
Right, exactly. You want to deny the enemy's ability to use the electromagnetic environment and ensure that your own forces can still use it.
And this spans every domain: air, sea, land, space, and the information domain.
Right. And to manage that, militaries use what they call the EW tree.
Okay, the EW tree. Break that down for us.
So it has 3 main branches. First, you've got electronic support, or ES. That's detecting and identifying threats.
Just listening, basically.
Yeah, exactly. Then there's electronic attack, EA. That's the offensive side to degrade the enemy. And finally, electronic protection, EP. Defending your own systems.
I always picture this like there's a high-stakes game of hide and seek, but it's in a pitch-black forest, and everyone has flashlights.
I love that analogy.
Right. So electronic support is you just standing perfectly still in the dark.
Just looking for the faintest beam of their flashlight.
Exactly, without turning yours on. And then electronic attack is when I finally see them, I pull out this like blinding million candle power spotlight and just shine it in their eyes.
Yep. And electronic protection is you putting on polarized sunglasses beforehand, so their spotlight doesn't blind you.
Makes sense. Now for electronic attack, there are 2 options, right? Soft kill and hard kill.
Right. So soft kill is the jamming the blinding spotlight. It's temporary. Hard kill is physical destruction. permanent.
Like an anti-radiation missile, an ARM.
Oh, RMs are terrifying. They home in directly on the enemy's radar transmission.
So if an anti-aircraft battery turns its radar on to find you,
the missile just rides that invisible radar beam all the way to the ground and blows up the dish.
wow. But you can't fire that ROM without the first branch, right? Electronic support.
Precisely. You need signals intelligence, or SIGINT. It's the absolute bedrock of command and control warfare targeting.
Because you have to know what you're shooting at.
Right, and SIGINT comes in two flavors. COMINT, which is communications intelligence intercepting spoken words or data.
And the other is ELINT.
ELINT, electronic intelligence. That handles non-communication signals, like the raw pulses of a radar.
So you have to intercept that ELINT transmission to give the missile something to lock onto.
You do. The ultimate strategic aim here is directed energy control, unbalancing the enemy through critical timing, leading to, permanent neutralization.
Okay, so let's get into the math and muscle of jamming. How do we actually overpower their signals?
Well, the core metric is the JS ratio, the jamming to signal ratio.
The golden rule being that the jamming factor must be greater than 1.
Right. It's basic physics. If your jamming noise isn't stronger than the intended signal when it hits the receiver, it just gets filtered out.
Like trying to stop two people from talking at a loud concert.
Exactly. You have to shout louder than the person they want to hear.
Yeah.
But it's not just about cranking the volume.
Right. It depends on location, distance modulation, and ERP, right? Effective radiated power.
Yeah. ERP is huge, along with hardware factors like antenna gain and polarization.
Okay, let's talk about polarization because that's crucial.
It is. Think of a radio wave like someone throwing a frisbee.
Okay.
If the transmitter throws it perfectly flat horizontally, the receiver is basically a horizontal slot designed to catch it.
So if I want to jam it, I need to throw my noise horizontally too.
Exactly. If you broadcast vertically, like throwing the frisbee sideways, it just bounces off the slot.
Oh, wow. So you lose all that power just from the wrong angle?
You do. And beyond power, a good jammer needs a search and surveillance receiver, high frequency stability, and spectral purity.
Spectral purity meaning you don't bleed into friendly frequencies.
Right. You need a surgical blast. Plus, an auto-follow capability to track them if they change frequencies.
Now, for the actual hardware, militaries use VHF systems for wideband coverage, right? Between 20 to 80 megahertz.
Yep, with a minimum of 15 watts of power. They use these 8 to 10 foot whip antennas, or ground plane antennas.
And you can boost that power using directional antennas or just making them higher for better line of sight.
Exactly. These are rugged systems. Manual scanning, oral monitoring, receiver muting. They run on 12-volt NiCad batteries or hand generators.
And there are specific systems for this. The Cobra system, which changes frequencies rapidly. The Panther system for managing 2 simultaneous nets. And the Zebra system, which manages 2 nets right from the control station.
But how you deploy them is what really matters. You have spot jamming, which is a concentrated narrow band attack. All your power on one frequency.
Okay. And then barrage jamming is the opposite.
Right. Wideband distributed attack, blasting white noise across a huge swath of the spectrum. But obviously your power is spread thin.
And the third is sweep jamming. Sequential attack, like sweeping a searchlight back and forth.
Exactly.
But wait, if I set up a huge antenna and just blast barrage jamming everywhere, aren't I just a giant glowing target?
Oh, absolutely. Any basic receiver will see you and you'll eat an anti-radiation missile.
So how do you avoid that?
Environmental factors, terrain mostly. You hide behind a mountain so your line of sight to the missile sensor is blocked, but you can still hit the target receiver.
Or you use smart and expendable jammers, right?
Yes, those are amazing. You fire them in an artillery shell right next to enemy communication hubs.
So they don't need big generators because they're so close.
Exactly. They rely on signal collision just yards away. Short battery life, but they cause total chaos. You can also mount jammers on vehicles, elevated mass, or tethered platforms to keep human operators safe.
Still, screaming over the enemy is dangerous. Deception seems smarter, like throwing your voice instead of shouting.
Deception ECM is an art form. Simulation, imitation, confusion.
And non-communication deception, like seduction and distraction.
Right. The backbone is repeater jamming. You intercept their radar, store a replica, delay it a fraction of a second, and send it back.
Creating huge range and direction errors.
Yeah. And they exploit side lobes to do it. Every radar has a main beam, but it leaks weak beams out the sides, the side lobes.
So you blast a fake signal into the side lobe, and the radar thinks it came from the front.
Exactly. It completely miscalculates the target's location.
That's brilliant.
Yeah.
The gate stealers are my favorite, like the range gate stealer for continuous wave or CW radars.
It's basically a heist.
Right, so a radar expects an echo in a narrow time window, called a tracking gate.
And the range gate stealer intercepts the pulse, syncs up, and sends back a fake artificially strengthened echo.
The radar likes the stronger signal, locks onto it, and then the jammer just slowly drags that tracking gate out into empty space.
It's so elegant. But the velocity gate stealer is even crazier. It targets the physics of motion using false Doppler frequency shifts.
Like the ambulance siren effect. Pitch goes up when it approaches, down when it leaves.
Exactly, which is how radar measures speed. The velocity gate stealer broadcasts a fake return echo and slowly alters the pitch.
So the enemy missile's computer thinks your jet is going hundreds of miles an hour faster than it is.
And it recalculates its intercept course and just flies right past you.
Wow. Now, shifting to ground ops, cell phone jamming is a totally different beast, right?
It's really tricky. When a cell phone gets blocked, it automatically cranks up its transmission power to punch through.
So a static jammer doesn't work.
No, you need dynamic power matching. The jammer constantly monitors the phone and dynamically escalates its own power to match it.
Crazy. And we also have to mention passive ECM, stuff that reflects energy instead of radiating it.
Right, like chaff dropping clouds of tiny aluminum strips from a plane to create a blinding white wall on radar.
And rope for lower frequency radars.
Yep. And the ultimate passive ECM is radar cross-section, or RCS, reduction shaping.
Stealth aircraft geometry, scattering the energy so it never bounces back.
Exactly.
Okay, so with all these offensive tools, how do you defend against this?
That's ECCM, electronic countermeasures, anti-jamming, and anti-deception.
The defensive shield. And tactically, that starts with electronic emission policy, EEP.
Radio silence. You only transmit if you have to. You verify identities to stop spoofing.
You also deploy small, mobile units and distribute the front line to create a resilient jamming curtain.
Because if they pinpoint you, the threat is massive. Look at GPS scrambling.
Right, like the Russian Zatel jamming station.
Yeah, it blocks GSM networks and Navistar GPS frequencies.
Which means your JDAM bombs, your long-range HIMARS, your advanced drones, all multi-million-dollar assets, just lose their navigation and hit empty fields.
Total off-target failure.
So how do we stop the Zatel from scrambling the brain of a HIMARS?
Frequency hopping spread spectrum, FHSS.
Okay, let's unpack FHSS. You basically convert a narrow band signal into a wide band signal, right?
Yes, and it spreads the energy below the noise floor.
Like whistling a specific tune in a really loud restaurant.
Exactly. The noise is too loud to just yell, but a complex pattern can be recognized by the receiver even if it's quiet.
And that pattern is controlled by Trandesi pseudorandom keys.
Right. It jumps hundreds or thousands of times a second. You have slow hopping, where it sends a few packets before jumping, and fast hopping, where it jumps mid-packet.
So the jammer can't predict it.
It provides massive resistance to narrowband and pulse jamming, prevents eavesdropping, stops multipath fading where signals bounce off buildings and cancel out.
And it supports CDMA, letting multiple friendly radios share the same airspace.
Yep. The hardware relies on high signal-to-noise ratios, or SNR, low side-lobe antennas, and rapid polarization changes.
Also pulse compression with matched filters, right?
Crucial. The matched filter is the digital brain tuned to the exact mathematical shape of the friendly signal, pulling it out of the noise.
And to stop enemy jammers from predicting radar pulses, they use PRF jitter, pulse repetition frequency jitter.
Right, like a drummer adding random microscopic variations to a beat. The jammer can't sync up to steal the gate.
Plus saturation prevention with large dynamic ranges and automatic gain reduction to dampen incoming noise spikes.
Absolutely.
So FHSS protects us. But how do we find the enemy if they're using this stuff?
Direction finding.
DF, finding the source of radiation. You have resection, which is using known enemy emitters to find your own location.
And intersection, which is using known friendly stations to find an unknown enemy.
So for intersection, you put 3 to 4 receivers along a baseline. They all take a bearing on the signal, and where the lines cross on a map, that triangle point is a target.
In theory, yes, but they use bidirectional azimuthal patterns to get those angles, specifically loop aerials.
This part is so cool, you think you point the broadside of the loop at the signal.
But actually, the signal is weakest at a null when the broadside faces the transmitter.
So you use the silence to find them.
Because a peak is fuzzy, but a null is incredibly sharp. They also use adcock element pairs for more precision.
Now, a classic DF system is the Watson-Watt system, but it's prone to errors.
Lots of them. Instrument flaws, physical site issues like metal re-radiation where a nearby fence bounces the signal.
And propagation errors from the atmosphere, so you constantly have to recalibrate it.
Exactly. And DF is just one part of ESM, electronic support measures. ESM evaluates 4 pillars.
Frequency and modulation, enemy order of battle, intentions and locations, and codes and ciphers.
A great example of ESM is a radar warning receiver, or RWR, in a jet.
Right. It intercepts a pulse, matches it to the enemy order of battle library in a millisecond, and tells the pilot they're being painted by like an SA-6.
And it automatically triggers evasive maneuvers, chaff, and flares.
But on a macro scale, dealing with thousands of signals on the ground, you need systems like the Simuke to EW suite.
Right, it filters the chaos using a 3-level hierarchy.
Level 3 at the bottom. Control center blocks overseeing 2 non-com blocks gathering raw data.
They pass that up to level 2. The EW control post at the HQ EW battalion overseeing 3 comm blocks.
And finally, level 1, the higher level control center at the HQ EW brigade.
Keeps commanders from getting paralyzed by data overload.
But ground sensors still hit the Earth's curvature, line of sight limits. So you need AWACS, airborne warning and control system.
A massive radar dome on a jet, overcomes terrestrial limits, highly survivable.
Uses pulse Doppler radar, but to filter out ground clutter from 30,000 feet, it needs high PRF, right?
High pulse repetition frequency. It lets the Doppler processor separate slow ground clutter from fast jets, giving it over a 250-mile range.
With major subsystems like advanced ESM, GTIs for secure data, and fusion software.
And India's Project Nutra takes it further with an indigenous ASA platform with a 400-kilometer range.
These are ultimate force multipliers for network-centric warfare. Combining Samyukta on the ground with AYACS in the sky gives commanders a full 3D picture.
It's all deeply interconnected.
It is. From the physics of the JS ratio and CTEL jammers, to gate stealers, frequency hopping, and AYECS.
You really have to understand the how and why behind all of it.
But here's a thought before we go. We talked about how fast all these calculations have to be. Doppler shifts, hopping channels thousands of times a second. With AI integrating into EW systems, it's very likely these JS ratios and frequency jumps will become automated at speeds humans can't even comprehend.
Right.
Meaning future wars could be won or lost entirely in the electromagnetic spectrum before a single physical shot is fired.
It is a sobering reality.
Moving to the next chapter.
When we imagine building a fortress, our minds usually go straight to physical architecture, right? Like thick stone walls, a deep moat, maybe a heavy iron gate.
Yeah, it's tangible. You can walk right up to it.
Exactly. You can touch the perimeter and know with absolute certainty that this line is where your defense begins.
And it is incredibly comforting to our human brains to see clear boundaries. Knowing exactly where the inside ends and the outside begins gives us this sense of control.
But the moment we step into the digital realm, that comforting perimeter completely vanishes. We find ourselves looking at a defensive landscape that is invisible, constantly shifting, and honestly terrifyingly porous. Welcome to the deep dive. Today, we're tearing apart a manual that reads like a survival guide for the digital age. Well, specifically the Chapter 8 revision module.
Which is just a fascinating document.
It really is. It outlines the modern anatomy of cyber threats, information assurance, and exactly how digital fortresses are built. And more importantly, it shows us how they are attacked and what it takes for them to survive.
Right. We're going to unpack the mechanics of this invisible battlefield. Because defending against a threat always starts with understanding its most basic anatomy.
So how does this framework break it down?
Well, cyber threats are broken down into 4 distinct forms. The most obvious is destruction, which is simply wiping out data. Then you have disclosure, which is, the unauthorized leaking of sensitive information.
I always think of modification as the most sinister of the four, though.
Oh, absolutely.
Because that's secretly altering data so it can no longer be trusted. Imagine someone doesn't delete a hospital's database, but instead changes the blood types of the patients. The chaos that causes is far worse than a simple deletion.
It really is. And the fourth form is denial of service, or DOS, where an attacker just overwhelms the system with traffic until it completely crashes.
And what makes those four threat forms so difficult to defend against is the sheer variety of actors launching them. I mean, the manual identifies everyone from foreign nation states and organized crime cartels to independent hackers, terrorist groups, and even malicious insiders.
Yeah, you have to build a system that can withstand an adversary with the unlimited budget and time of a foreign military, while also protecting against a disgruntled employee who, already has a key card to the server room.
Which brings up a fascinating concept from the material. Like, how do you actually calculate how dangerous an adversary is? It's not just a gut feeling, right? It's treated as a mathematical equation.
Right. The threat level of any adversary equals their capabilities plus their motivation plus their willingness to strike.
You cannot just measure how sophisticated a piece of malware is.
No, you have to measure the human behind the keyboard.
Let's think about this like guarding a physical bank vault for a second.
Okay, sure.
A petty thief might have the motivation. They obviously want the millions of dollars locked inside.
Right.
And they might have the willingness, meaning they are daring or desperate enough to try.
Right.
But if their capability is just a crowbar and a ski mask, the actual threat level to a foot-thick steel vault remains entirely manageable.
Exactly. It is only when all three factors align, when that highly motivated thief also possesses advanced safe-cracking tools and architectural blueprints, that you have a critical situation.
And that equation is the foundation for an organization's information assurance strategy.
Because threat levels constantly fluctuate, defense requires two parallel tracks. First are the proactive measures.
So this is your prevention.
Yeah, building the digital walls, patching vulnerabilities, and locking the doors. But no wall is impenetrable. Given enough time and capability, an attacker will get through.
Right.
So you must have reactive measures functioning at the same time. This is your system's ability to detect a breach the second it happens, survive the ongoing attack without total collapse, and respond effectively to neutralize the intruder.
To make both those proactive and reactive tracks function, a modern cybersecurity framework relies on three core pillars: people, process, and technology. And the most interesting detail here is that technology is explicitly categorized merely as the support tool.
Which surprises a lot of people. People tend to throw expensive software at a problem and assume they are secure.
Just buy a bigger firewall.
Right. But if you haven't trained your people to recognize a phishing email, or if your organizational processes allow someone to bypass security protocols because they are in a hurry, the most advanced firewall on the planet is completely useless.
Technology only supports the rules and behaviors you have already established.
Exactly. That philosophy extends into what the manual outlines as the 7 pillars of security. We are talking about personnel security, physical security, hardware, software, database, communication, and network security.
It is a massive web of interconnected defenses. But if a single weak link, like a physical door left propped open by an employee taking a smoke break, can compromise an entire system, it makes you wonder why adversaries even bother with small-scale hacking when they could target the broader infrastructure.
And that's exactly what happens when you zoom out. Zooming out from individual servers to the nation-state level completely changes the calculus of warfare.
Yeah.
When we scale this up, we are no longer talking about a lone wolf stealing credit card numbers in a basement. We enter the realm of state-sponsored conflict, which is categorized into two massively different strategic approaches: cyber war and net war.
We hear the term cyber war thrown around a lot in the news, but the definition here is very specific, right?
It is. Cyber war has a tactical military focus. The objective is to achieve information dominance by disrupting or destroying systems.
So we are talking about targeting communication networks, taking down regional power grids, jamming early warning radar, or blinding an enemy's military infrastructure.
Yeah, it is the modern digital equivalent of bombing a bridge or severing a supply line.
Yeah.
You are physically or functionally destroying the enemy's ability to operate their machinery and communicate with their troops.
But net war operates on a totally different plane. Net war focuses purely on societal impact.
Right.
It is a grand-level conflict fought across economic, political, and cultural lines, and its primary target is the public mindset and elite leadership.
The methods used in net war are fascinating because they often don't look like traditional hacking.
I mean, instead of writing a virus to crash a military server, an adversary wages net war through propaganda, diplomatic manipulation, psychological campaigns, and cultural subversion.
Exactly. They infiltrate social networks and media ecosystems to quietly alter how a population perceives events.
So for you listening, the core distinction to keep in mind is that cyber war targets systems, whereas net war targets the mindset.
That is the key takeaway.
If cyber war blinds a nation's radar so they can't see the incoming bombers, net war is a decade-long campaign to convince that same nation that they don't even need radar, or that the country sending the bombers is actually their greatest ally.
It is psychological infiltration, and it is treated as a highly structured, recognized form of warfare.
Understanding that grand strategy naturally forces us to look at the tactical execution. Whether you are blinding radar or stealing state secrets, how are these attackers actually breaching the systems?
Right, we are stepping into the spycraft of breaches, and the methods detailed in this manual are genuinely mind-blowing. We have to look far beyond the Hollywood trope of someone frantically typing code into a terminal.
Let's unpack the communication breaches first. They fall into two categories, active and passive. Active breaches are what we normally imagine.
An attacker transmitting data on a terminal, actively inserting themselves into your network, or sending malicious commands.
But passive breaches are entirely invisible. The attacker is just sitting back, monitoring and absorbing your data as it flows.
We all know about wiretapping or piggybacking on an existing transmission, but the manual dives deep into phenomena like crosstalk.
This part is wild.
Right. Data cables are just copper wires carrying electrical pulses, and those pulses generate tiny electromagnetic fields.
If cables are bundled together without proper shielding, the magnetic field from one wire can induce a faint, identical signal in the adjacent wire.
Meaning an attacker with a sensitive enough antenna can read your data stream just by being near the cable, without ever physically tapping into it.
That is wild. And it gets even more surreal when we look at system eavesdropping. The manual highlights VDU, or video display unit interception.
Every computer monitor emits varying levels of radiation and radio frequencies as it draws the image on the screen.
So attackers can set up equipment outside your building, capture that radiation leaking through the walls, and use signal reconstruction to recreate exactly what is on your monitor in real time.
They can literally watch you type a classified document without ever touching your network. Along with visual eavesdropping, using advanced photography or high-powered optics through a window, it highlights just how vulnerable the physical environment is.
The part that genuinely stopped me in my tracks was a category called analysis threats.
Oh, the acoustic analysis.
Yeah, it mentions specifications leaks, which is standard corporate espionage, but then it outlines sound pattern analysis. We were talking about acoustic analysis, acoustic coupling, and machine sound deciphering.
Because every single physical machine makes noise. A hard drive spins, a cooling fan changes its speed depending on how hard the processor is working.
But more specifically, think about a physical keyboard. Each key is located at a slightly different distance from the microphone on a laptop, and the plastic strikes the membrane with a microscopically different acoustic signature.
Meaning a compromised microphone in the room, maybe a smartwatch or smart speaker, could just be listening to the clicking of your keyboard. By running those clicks through machine sound deciphering, an attacker can reconstruct your password based purely on the subtle acoustic differences of your keystrokes.
It feels like science fiction, but it is a documented tactical threat.
It forces security architects to treat the physical environment with the exact same paranoia as the digital network, which ties into the program's security risks.
Adversaries will recover waste paper, gather technical intelligence on the building layout, or steal program listings and system blueprints just to plan their assault strategy.
Interestingly, the core defense against losing those critical programs is simply maintaining rigorous, isolated backups.
But let's push back on the super spy narrative for a second. We picture this acoustic, radiation-capturing intelligence operative. Yet, when we look at the hardware breaches section, the biggest threat to an organization might just be the person arriving to fix the air conditioning.
Oh, environmental controls are a massive vulnerability. Hardware breaches include environmental errors like AC and humidity failures.
If an attacker can manipulate the climate control in a server room, they can overheat the hardware and cause a catastrophic system failure without writing a single line of malicious code.
The manual also flags physical access tampering by maintenance engineers. Someone comes in for a routine check and swaps out an internal card or replaces a hard disk with a compromised one.
They also exploit logic errors, manipulating power and voltage changes to force a system to reboot into a vulnerable state.
And you combine that physical risk with remote terminal risks. If an organization has remote operations that lack proper audit trails, they have absolutely no idea who is sitting at that terminal or what they're doing.
Which bleeds heavily into software security breaches, unauthorized access to source code, someone internally introducing a virus or database intrusion.
Time and time again, the recurring theme is that the insider, the user, who already has access, poses the most critical threat.
So with attack methods ranging from acoustic deciphering to a rogue AC repairman, how does a military or a government actually govern this space and fight back?
They have to establish a rigid, legal, and architectural playbook. You cannot fight an asymmetric digital war without a foundation of authority. The manual points to legal frameworks like the IT Act of 2000 as that baseline.
The IT Act was initially established to promote e-commerce, support e-governance, legalize digital signatures, and give electronic records legal status.
But crucially, it features certifying authorities and clearly defines the penalties for unauthorized access. It sets the rules of the road.
From that legal baseline, defense planners use what is called the cybercrime taxonomy. This is a three-way classification system that defines exactly how a computer fits into a criminal act.
Because understanding this taxonomy dictates the entire incident response. A computer can be the target, the subject, or the instrument of a crime.
Let me help conceptualize this taxonomy with a relatable example.
Yeah, that would be helpful.
So the computer as the target is someone actively hacking your personal laptop to steal your identity, infect it with ransomware, or disrupt your work. The computer is the victim.
Right.
The computer as the subject is your laptop being secretly used as an incubator. Maybe a hacker hides a self-replicating worm on your hard drive, or uses your storage for illegal data waiting to deploy it later.
Exactly. And the computer as an instrument is when your laptop is actively used as a tool, like a digital getaway car, to commit a traditional offense, like financial fraud or distributing illicit materials.
Categorizing the threat legally allows for structured operational action plans. For large-scale defense, like the armed forces, these plans require unified command, strict standard operating procedures, and heavily rely on a centralized cybersecurity agency.
That centralized agency acts as the master architect of the defense. They hold capability acquisition authority, meaning they decide what tech gets bought.
They enforce security instructions, guide policy evolution, define current threat conditions, and manage the overarching network architecture.
And they govern that architecture using 11 specific measures for information system defense. We don't need to read the whole list, but the philosophy boils down to creating an environment where no single failure sinks the ship.
Right. You are layering data and access controls, physical and technical hardening, continuous anomaly detection, personnel security vetting, and malicious traffic blocking.
All of those measures work together to ensure mission continuity, which is that reactive ability to survive an attack we discussed earlier.
This concept is visualized in the strategic framework and architecture through layered security. By using structural layering, you ensure there is no single point of failure.
If an attacker breaches the outer firewall, they immediately hit an internal access control and then a physical security barrier.
The architecture also demands rigorous data classification. By categorizing information based purely on its value and sensitivity, you prevent broad system misuse.
Not every employee needs access to the nuclear codes, so you don't store them on the same server as the cafeteria menu.
Exactly. To protect that classified information environment, the framework uses logical isolation, physical isolation, and network isolation. Think of it like the watertight compartments on a submarine.
If one section gets breached and starts flooding with water, you can seal the bulkheads. That compartment is lost, but the isolation prevents the entire submarine from sinking.
And to make sure those bulkheads actually work, the agency runs continuous periodic security checks and audit mechanisms.
At a national level, this philosophy scales up into massive infrastructure projects like the DCN or Defense Communication Network.
The DCN is engineered with coordinated design goals that prioritize robustness, survivability under fire, and interoperability between different branches.
Furthermore, the Joint Services Action Plan is implemented to ensure harmonization and economy of effort.
Let's demystify a term the manual uses there, C4I2 systems. It stands for Command, Control, Communications, Computers, Intelligence, and Interoperability.
Basically, It's the nervous system of a military.
The Joint Services Action Plan prevents different branches of the military from building duplicate, isolated nervous systems that can't talk to each other during a crisis.
But building the architecture isn't enough. You have to constantly check your homework. The cybersecurity organization acts as an IT network policing knowledge center.
Their day-to-day role involves proactive threat prevention, classifying new hardware, formulating policy, managing encryption keys, and providing the architecture for intrusion detection systems.
They are running routine, scheduled checks constantly. Disaster avoidance drills, internal security reviews, verifying system integrity, and making sure everyone understands their organizational responsibility.
Inevitably, though, a breach will happen.
Right, it's just a matter of when.
When it does, the post-occurrence investigation kicks in. This involves forensic audits, deep dive database breach analysis, and meticulous evidence collection from system admin logs so that legal action can be taken based on that IT Act of 2000 we mentioned.
If a system is brought down entirely, disaster recovery is handed over to CERT's computer emergency response teams. Their sole focus is restoration services, getting the network back online.
Meanwhile, vulnerability assessments are constantly being run to identify weaknesses before they can be exploited. They probe current networks and evaluate proposed systems to see if they're actually safe to deploy.
All of this, the legal frameworks, the watertight architectural layers, the forensic audits, leads us to the final stage of the manual.
This is where we look at the everyday, practical methods for achieving security and the ultimate geopolitical strategy for data defense.
The everyday proactive methods are really interesting because they require thinking like the enemy. The manual advocates for proactive expertise, which literally means hiring ethical hackers as security advisors.
You need people whose brains are wired to break things in order to catch the thieves.
Next is software hygiene. It sounds basic, but it requires constant vigilance. Monitoring bug bounty sites, applying regular patch updates immediately, and constantly filling known security holes before they're exploited.
Then you have attack surface reduction. This is the practice of minimizing access points and disabling any unnecessary protocols.
Right, if a digital door doesn't strictly need to exist for business operations, you don't just lock it, you brick it over entirely.
Finally, there are the technical measures we all interact with. Complex authentication, enforcing strong password policies that require alphanumeric characters and regular changes, and relying on heavy encryption to ensure secure data exchange.
But the manual introduces a fascinating dilemma when it talks about product selection. It advises organizations to use off-the-shelf, commercially available software for amateur threats, but to rely entirely on indigenous systems for high-value operations.
I found that surprising. Why would an organization use off-the-shelf software at all if they know it is inherently less secure and potentially compromised?
It comes down to economy of effort and resource management. Building custom, hyper-secure technology is incredibly expensive and time-consuming.
Oh, that makes sense.
You do not need to deploy a custom-built billion-dollar sovereign operating system just to protect low-value, unclassified data from amateur script kiddies. You reserve your truly indigenous, highly secure tech for the crown jewels, your power grids, your military communications, your financial sector.
Save the heavy artillery for the real war. And that concept leads to the ultimate conclusion of this entire source document, strategic sovereignty.
According to this manual, strategic sovereignty is the absolute pinnacle of defense.
Strategic sovereignty means relying entirely on indigenous systems, hardware manufactured within your own borders, and software coded by your own citizens.
The goal is to avoid foreign supply chain snags and, more importantly, to prevent hidden trapdoors.
The core pillars of this trust architecture are people, process, and technology, all operating strictly under sovereign control.
Because if you buy a router or a microchip from an overseas manufacturer, how do you know the firmware doesn't have a dormant piece of code waiting for a signal to shut down your power grid?
You cannot truly trust a system if you did not build every single component and write every line of code yourself.
That is the only way to be certain an adversary hasn't left the back door wide open before the equipment even arrived at your facility.
It is a radical stance, but in the context of net war and nation-state level threats, sovereign control is presented as the only way to guarantee the integrity of your information environment.
It really is the ultimate defense.
We have covered a massive amount of ground today. We took this dense survival guide and mapped out the digital battlefield for you.
We started by understanding the math behind threat levels, capability, motivation, and willingness.
We explored the terrifying reality of invisible espionage, from electromagnetic crosstalk to acoustic keystroke deciphering.
We zoomed out to understand how net war targets the psychology of a society rather than just its servers.
And finally, we walked through the layered architecture, the legal framework, and the aggressive pursuit of strategic sovereignty required to keep a nation's data safe. But as we wrap up, I want to leave you with a final thought to mull over based on that ultimate conclusion.
Okay.
If the absolute pinnacle of defense against cyber threats requires a nation to build entirely indigenous hardware and software from scratch just to avoid foreign trapdoors, well, how secure can any interconnected, globalized internet ever truly be?
Right, that is the big question.
Are we inevitably heading toward a future of completely walled-off sovereign national internets where digital borders match physical ones? It is something to think about the next time you connect to a global server. Until next time. Chapter 9, Revision Module. So we are diving straight into the foundation today, which is infrared technology and radiation.
Right. And the absolute core fact you have to memorize here is the molecular activity principle.
Okay.
Basically, everything emits infrared or IR radiation. And that is purely because molecules are just constantly vibrating.
Yeah, and that IR radiation travels in perfect straight lines, right? Through both vacuums and solid matter.
Exactly. And if you look at the electromagnetic spectrum, it sits right there in the middle between visible light and microwaves.
Right. Now, we need to rattle off the 3 specific IR bands.
Okay, let's hit them. First, near IR. That covers 4.7 to 1.5 microns.
Got it. And then intermediate IR is 1.5 to 5.6 microns.
Yes. And finally, far IR, which stretches from 5.6 all the way to 1,000 microns.
Okay, so theoretically, to mirror this heat emission, physics uses a reference point called a black body, right?
Exactly. A black body is this theoretical object that absorbs and radiates maximum energy.
But the absolute physical limit, like the real floor, is absolute zero.
Right. Minus 273 degrees Kelvin. That is the point where molecular vibration just completely stops, meaning no heat is radiated at all.
So I always think of military heat signatures like leaving wet footprints on a completely dry floor.
Well, that's a good way to picture it.
I mean, unless you are literally perfectly matched to absolute zero, you cannot hide your trace. It's totally different from radio waves or microwaves. It's an unavoidable signature.
And that unavoidable signature dictates how detection works. So you have active IR detection, which requires an IR transmitter or an illuminator and a receiver.
Right.
And then you have passive IR detection. This uses an IR scanner just for stealth, relying purely on natural heat radiation.
Wait, I have to push back here. Isn't passive detection strictly superior just because using an active illuminator instantly gives away your position?
Well, yes, passive is much safer for stealth, absolutely. But it's not strictly superior in every case. Like if a target has the exact same temperature as the background, a passive scanner won't see it. You need the active illuminator to bounce energy off the target and force a contrast.
That makes sense. Okay, moving on to seeing the dark. Night vision devices, or NVDs.
Right, and NVDs are entirely passive systems. They project absolutely no energy.
They strictly rely on light intensification, right? Pulling ambient light from the moon, stars, or sky glow.
Exactly. But they have some really severe limitations. They are totally useless in heavy rain, snow, fog, and absolute darkness.
Because if it's pitch black, there are 0 photons to multiply. You have to use flares or lasers to give the system something to work with.
Right, and that thick fog also severely limits aerial and TV systems.
But tactically, things like starlight scopes are incredible for stealthy surveillance. I mean, they completely overcome human sight limitations in poor weather or at really long ranges.
Yeah, and for the exam, you need to know the 5 precise steps of the image intensifier tube.
The pips tube? Let's rattle these off. I always use a rapid financial analogy for this.
Go for it.
Okay, step 1. Capture by the objective lens onto a photocathode. This is like your small initial cash deposit.
Right, and step 2 is the conversion of photons to electrons via the photoelectric effect.
Basically converting that cash into digital currency so the system can process it.
Exactly. Step 3 is amplification through a microchannel plate, or MCP.
And that uses secondary cascaded emission, right?
Yes, which results in a massive 40,000 times intensity increase.
So that's applying massive compound interest, the 40,000x multiplier.
Right, then step 4 is the reconversion on a phosphor screen, changing those electrons back to photons.
Cashing out the investment.
And finally, step 5, viewing through an eyepiece lens, which gives you that classic green-tinted image.
Perfect. But if NVDs completely fail in thick fog, operations have to pivot back to surveillance sensors and thermal imaging, right? TI.
Yeah, you have to capture actual heat. But remember, there are alternative detection sources before you even boot up TI.
Right, let's list those out. You have ground vibrations, seismic waves, and mechanical waves.
You also have acoustic waves, which are crucial for picking up helicopter rotors and gunfire.
And chemical sensors, sniffer dogs, and personnel detection for sniffing out explosives and agents.
Exactly. But for thermal imaging, it relies on IR radiation, specifically in the 3 to 14 micron range.
And it utilizes IRLS, right? Infrared line search.
Yes, which translates that heat into visual grayscale or color maps, and it works for any target warmer than absolute zero.
Now, detectors split into 2 main categories, cooled and uncooled detectors.
Right. Cold detectors use MCT or NSB sensors with cryogenic cooling.
And that cooling reduces the internal heat noise, right? So they can detect differences as small as 0.025 degrees Celsius.
Exactly. Then you have uncooled detectors, which use vanadium oxide or VOX. That makes them super compact and portable.
Wait, if VOX tech makes uncooled detectors so portable, why would you burden troops with bulky cryogenic cooling systems?
It comes down to a tactical trade-off. Uncooled is great for portability, sure. But if you need to spot a camouflage soldier whose body heat matches the wet jungle foliage around them, an uncooled sensor won't see them.
So you desperately need that 0.025 degree precision.
Exactly. So for infantry applications, they use thermal binoculars with a 6-kilometer range.
And man-portable systems for coordinate recording, plus indirect vision to protect the operator's eyes from lasers.
Right. And the ultimate integration of this is the SHOSHUS-TI MFH-HTI, the multifunction handheld thermal imager.
That thing is a powerhouse. It integrates thermal sights, an eye-safe laser rangefinder, a digital compass, GPS, and a color CCD camera.
Yeah, perfect for foliage searches or pitch-dark ambushes.
Okay, since it has a laser rangefinder, let's immediately jump into precision light and laser physics.
First fact to round it off, LASER is an acronym. It stands for light amplification by stimulated emission of radiation.
And its characteristics are highly concentrated, coherent light, monochromaticity, and coherence in the same phase.
Right, and the core properties are based on stimulated emission and photon cloning.
I always explain this with a quick analogy. A regular light bulb is like a totally disorganized crowd wandering in different directions.
Okay.
But a laser is a highly disciplined marching band, moving in perfect lockstep, coherent, monochromatic, and in the exact same phase.
That's a great way to remember it. And to build one, you need 3 core components: a gain medium, a pump source for energy, and an optical cavity.
And we classify them by that medium, right?
Yeah.
So gas lasers are for alignment tasks.
Semiconductor lasers are compact and affordable.
Solid-state lasers like the N.YAG are heavy hitters.
Dye lasers are primarily for military applications.
And fiber lasers produce highly focused beams, mostly used in surgery.
Exactly. So let's talk about weaponizing that light, looking at laser applications.
First, general applications. Surgery, environmental monitoring for pollution or particle size, security intrusion alarms, invisible tripwires, 3D holograms, and color TV systems.
Right. Now, for military targeting and rangefinding, they use the time-of-flight principle for artillery and missile guidance.
Wait, can you rapidly break down how time of flight actually calculates distance? Because I know listeners might confuse it with traditional radar.
Sure. Radar sends out a broad cone of radio waves and measures the reflection. Time of flight is surgically precise. It fires a single microscopic laser pulse, times the exact microsecond it takes to bounce back, and calculates the precise millimeter range instantly.
Wow, okay. Lasers are also huge in electronic warfare, jamming sensors and completely disrupting IR tracking.
And for military support, they're used for blinding satellites and establishing highly secure data links with anti-intercept capability.
Because the beam is too physically narrow to tap into, we also have laser designators.
Right, providing illumination for precision-guided munitions, acting as night strike markers, and handling ranging via reflection time and energy absorption sensing.
Then you escalate to directed energy weapons, or DDoWs. These rely on optical scattering, penetration, and see-through instruments.
And their main function is to cause immediate structural damage and disable internal electronics.
Specific systems here include the laser weapon system, LAWD-US, and the iron beam, right?
Exactly. And for non-lethal options, you have dazzlers.
But there's a strict rule on vision. The protocol on blinding laser weapons strictly and permanently enforces a ban on weapons designed to cause permanent blindness.
Yes, that is a critical point. So finally, let's tie it all together with the ultimate integration. The SATA process and systems.
SATA surveillance and target acquisition. Let's rattle off the definitions.
Okay, surveillance is systematic watch and continuous observation, evaluating all weather capability and timely information.
Then detection is discovering interest based on contrast, movement, shape, and behavior.
Recognition is identifying the general object type and establishing whether it's friend or foe.
And target acquisition is identifying the exact model, determining location and position, evaluating weapon range requirements, and achieving precision accuracy for engagement and guidance. But wait, why separate detection, recognition, and target acquisition like that? Can you rattle off a lightning-fast scenario, mapping those three?
Definitely. You are scanning a forest, you detect a moving thermal blob. That's detection.
Okay.
The blob turns, and you realize it has the profile of a tank. That's recognition.
Right.
Then you hit it with a laser, establish it's a T90 exactly 3.2 kilometers away, and lock that in. That's target acquisition.
That makes total sense. And the equipment technology incorporates literally everything we just talked about. Optical, IR, laser, radar, and acoustic sensors.
Right. And because it's so much data, user interfaces have to focus on reducing operator strain.
With ergonomic bodies, adjustable eyepieces, data output overlays, and intuitive menus, like in the Shrusty MFH HTI.
Exactly. And another massive integration is the Tata Rajak ULRS.
Right, featuring multi-sensor housing, dual video display, and defogging technology.
And it utilizes IP network control via pan-tilt units, wireless radios, and optical fiber cables. It is heavily used by artillery, infantry, and mechanized infantry.
Moving to next chapter.
Chapter 10, Revision Module. Let's start at the deep dive.
Okay, let's jump straight into the basics. Radar. It stands for radio detection and ranging.
Right. And it's basically an electromagnetic system for when you're dealing with, darkness, fog, rain.
Exactly. And the fundamental principle you have to know is the echo. It's just reflected electromagnetic radiation bouncing off electrically leading surfaces.
And to calculate distance, the system uses the running time of those pulses, right? Measured against the constant speed of light.
Yeah, that's it. And for direction, it's strictly calculating azimuth and elevation.
Okay, let's unpack this for you because you need to know the core hardware that makes this happen. First up, you've got a high-power oscillator for transmission.
Right, and a transmitting antenna to send it out, plus a receiving antenna to catch the echo.
And then, signal processing takes over to extract the velocity and location.
Now, for waveforms, you're looking at two main types. Pulse, or continuous wave, which is usually just called CW.
Got it. And the core hardware driving this, you've got the magnetron, the klystron, and the traveling wave tube, or TWT.
Yeah, plus the antenna system, a local oscillator, and the intermediate frequency or IF conversion modules.
And then there's the duplexer. Think of it like a highly efficient traffic cop. It protects the sensitive receiver and directs traffic between the antenna, transmitter, and receiver, basically ensuring a really loud shout from the transmitter doesn't deafen the system's own ears.
That's a great way to look at it. So moving on to classifications. Primary radar uses reflected echoes for range, height, angle, and speed. It's standard for military air defense.
Because it doesn't need cooperation from the target, right?
Okay.
But secondary radar requires active target ID.
Exactly, like military IFF identify friend or foe and civil ATC RBS.
Now, hardware configurations. Monostatic is a single antenna setup, so it completely requires that duplexer.
Right, whereas bistatic uses separate transmitting and receiving antennas located at, totally different locations.
What about waveforms? Continuous wave, if it's unmodulated, measures speed via the Doppler effect.
Yeah, but if you modulate that CW, then it can measure range.
Okay, and pulse radar. That uses high-power pulses classified by PRF pulse repetition frequency.
Right, so low PRF is for MTI, which is moving target indication, and high PRF is used for pulse Doppler.
And for outputs, we have imaging, like SAR, for pictures, mapping, and ID.
And non-imaging, that's just raw data from altimeters or scatter meters.
Then for displays, you've got the standard A-scope and the PPI, the planned position indicator. That one scans a specific sky slice for azimuth, elevation, and target detail.
Right, now let's rattle off the frequencies. The spectrum spans from 220 megahertz up to 35 gigahertz.
Low bands are HF3 to 30 megahertz, and VHF-UHF covering 30 to 1000 megahertz.
The conventional bands are L, S, C, and X. Those sit between 1,000 and 12,000 megahertz.
And the high precision bands, that's Q, K, and Ka, ranging from 12 to 40 gigahertz.
Plus the millimeter bands, which are 30 to 300 gigahertz. If we connect this to the bigger picture, the reason we separate lower frequencies from high precision millimeter bands all comes down to the physical limits of the waveforms.
Right, because lower frequencies punch through weather, but millimeter bands give you the high resolution details.
Exactly. So let's look at operational roles. For civil utility, you have air traffic control doing en-route and ground approach.
Also terrain following, weather avoidance, and ship collision prevention.
Plus satellite tracking, remote sensing like they use for the moon landings, and meteorology for precipitation, cloud physics, and storm tracking.
Okay, military utility, early warning for detection and search.
Target acquisition for range and velocity.
Targeting and fire control,
Yeah.
for lock-on and clutter differentiation.
Right. And proximity fuses for non-direct hit artillery detonation.
Plus imaging, like SAR-2D and 3D all-weather, and radar warning receivers, RWR, for finding enemy emission, direction, and distance.
Now looking at mission profiles, strategic search and early warning handle broad surveillance and track.
While tactical tracking and fire control rely on high PRF for beam rider guidance and homing, and aviation support uses its own specialized networks.
Down on the battlefield, the ground systems include Flycatcher for fire control and missile guidance.
There's the Reporter, which is S-band with a 40-kilometer range.
The Barani with a 90-kilometer range.
And the BFSR 2140NG, which is a terrain-specific man-portable system.
Yeah.
Okay, wait, rapid pushback question here. With so many overlapping signals from proximity fuses, RWRs, and fire control all operating at once on a battlefield, how does a system avoid blinding itself with clutter?
Well, that's purely handled by signal processing and PRF. The system's algorithms only accept return signals that perfectly match the timing of its specific pulse repetition frequency. Everything else is just rejected.
Right, okay, breaking the limits.
Yeah.
Conventional ground radar hits the line of sight limitation, which is the radar horizon caused by Earth's curvature.
Yeah, so to fix that, we use OTH, over-the-horizon radar. It overcomes the curvature using high-frequency skywave refraction or ground wave diffraction.
Skywave uses ionospheric refraction and multi-hop extension.
Right, exactly. And ground wave relies on diffraction, which is great because it's completely immune to auroras and ionospheric radiation.
But the specs for OT are massive. You need separate transmit and receive systems, huge phased arrays, and resonance region apertures up to 1,200 meters.
What's fascinating here is the sheer physical scale. You literally need a 1,200-meter aperture just to effectively bounce those low-frequency signals.
Yeah, but the performance is wild. Range is 1,000 to 4,000 kilometers with a 60 to 120 degree angle.
Range resolution is broad, 20 to 40 kilometers, but relative range accuracy is 0.2 to 0.4 kilometers.
And applications include remote APC, sea condition monitoring measuring wind and waves via Doppler shift, and strategic surveillance of aircraft, missiles, and ships.
Moving on to advanced imaging. Synthetic aperture radar, or the SAR, synthesizes a massive antenna aperture mathematically via vehicle movement.
Right, it produces high-res, photographic quality images and penetrates clouds and darkness. Heavily used for combat surveillance and precision nav.
Then you have LiDAR, which is laser radar. It's used a lot in urban combat, but it suffers from signal fading in bad weather.
Okay, final section. Stealth versus weapon locating radars, or WLR. Stealth technology exploits radar limitations to reduce the radar cross-section.
Right. Method 1 is shaping. It reflects energy away using a cone of silence, faceted surfaces, contoured surfaces, and controls edge diffraction.
Method 2 is loading, which absorbs electromagnetic energy using radar-absorbent material RAM.
On the flip side, you have WLR. Its mission is trajectory tracking for mortar shells, unguided rockets, and missiles.
It basically extrapolates the point of origin and provides fire correction for friendly artillery.
Yeah. The ANTPQ-37 Firefinder was the first long-range WLR with rapid location capability.
And a major modern example is the Swathi system, an indigenous Indian system derived from the Rajendra radar.
Swathi's specs are impressive. It's a passive electronically scanned array, or PISA, with a coherent TWT transmitter pushing 40 kilowatts.
It has electronic steering of plus or minus 45 degrees and physical slewing of plus or minus 135 degrees, which gives it a full 360-degree scan.
Its advanced features include monopulse tracking for low probability of intercept LPI.
Plus real-time 3D digital mapping, and it handles up to 7 targets at once.
Right.
Here's where it gets really interesting. It's the ultimate cat-and-a-mouse game between shaping and loading and stealth, and the relentless 5-step operational sequence of a system like Swathi. Step 1 is threat detection and classification.
Step 2 is the tracking sequence.
Step 3 is trajectory extrapolation.
Step 4 is friendly fall of shot correction out to a 30-kilometer range.
And Step 5 is target storage, holding up to 99 locations.
This raises an important question, though. How will future systems balance LPI, that low probability of intercept, against increasingly capable RAM technologies?
Moving to next chapter, Chapter 11 Revision Module. We begin at the highest altitude to establish the scientific foundation of overhead sensing before moving to ground-level applications.
Right, so the absolute baseline for all of this, the foundation you need for the exam, is remote sensing, which, I mean, in the simplest terms, is acquiring data about an object or area without any physical contact, strictly using electromagnetic radiation, or EMR.
Okay, let's rattle off how we actually gather that EMR. It splits into 2 methods, passive sensing and active sensing. So passive is basically just gathering existing radiation, right? Like reflected sunlight, film photography, or even infrared sensors picking up heat.
Exactly, it's just listening.
Yeah.
Active sensing, on the other hand, emits its own energy and measures the backscatter. So that's your radar and LiDAR. They actively bounce signals off targets.
Got it. And the goal of both methods is capturing spectral signatures.
Yeah, because every material reflects EMR differently. These spectral signatures are unique radiation patterns. They allow us to not just identify an object, but actually determine its chemical and physical properties based on the transmitted wavelengths.
Right, but capturing that from orbit means dealing with the atmosphere. So we have to talk about atmospheric windows. To make this stick for you, think about tuning a radio dial. You have to tune your sensor specifically to a frequency between 0.1 to 14 micrometers. That exact window bypasses the static of atmospheric scattering and absorption across the UV, visible, and infrared spectrums.
That's a perfect analogy. But even perfectly tuned, you still hit sensor band limitations. The data you get is strictly governed by pixel size, bandwidth, repetitivity, and bit depth.
Let's run through those fast. Pixel size, the spatial resolution.
Bandwidth is how wide a slice of the spectrum you capture.
Yep.
Repetitivity is how often the satellite revisits that same spot. And bit depth is the amount of data recorded per pixel.
Like dynamic range.
Exactly. And you have to use these bands properly. A prime example of limitation is single-band panchromatic images.
Right, the high-res black and white photos.
Yeah, they suffer from optical scattering and are entirely ineffective for camouflage detection. Because it's just black and white, commanders are forced to require active and passive thermal imaging just to compensate.
Okay, so atmospheric scattering limits overhead sensors. We need to drop directly to the ground level to discuss unattended ground sensors, or UGS. These are the physical tripwires filling the coverage gap.
Right. A UGS network has a few core components, the sensor types, a power pack, and the communication media.
And the comms are critical here.
Yeah.
They operate in the VHF band, 138 to 174 megahertz, with a 2 megahertz bandwidth. They use digital coded messages and, crucially, omnidirectional antennas.
Which gives them immunity from monitoring.
Exactly. You don't want the enemy tracing a directional beam back to the sensor.
Yeah. So looking at the detectors themselves, you have the geophone detector. It's a seismic detector using a moving coil and a magnet to detect ground vibrations from human or vehicle intrusion.
And then the magnetic detector, which senses changes in the Earth's magnetic field from ferrous metals. And these two are often paired together, right?
Yes, specifically for directionality. You also have infrared or IR detectors, but these actually see underground deployment, detecting radiation changes from the friction of vehicle movement above them.
Okay, my favorite one is the Secatech piezo cable. It's a 2-core copper wire using the mechanical stress principle. I liken it to a synthetic nervous system for the dirt. Physical pressure instantly translates into an electrical pain signal, basically a voltage shift, to alert you.
It's incredibly effective. And to avoid false alarms, these UGS systems have special features. You need to remember the animal filter, versatile placement options, the tamper alarm, and a status alarm that does daily check-ins.
And you can run them in continuous mode or hourly mode to save battery.
Right. So ground sensors tell us what is moving at a choke point. But to plan routes to get there, we synthesize massive amounts of spectral terrain data using multispectral and hyperspectral imaging, MSI, and high.
This is broad area coverage, like a 180 by 180 kilometer scale overview.
Yeah, it's macro level. We use it for mission planning. This involves 3D image synthesis, perspective scene generation, helicopter landing zone analysis, and integrating DTED, which is digital terrain elevation data.
And trafficability assessment, right? Looking at soil moisture to determine potential vehicle speeds.
Exactly. We do advanced spectral analysis for this. Near infrared, or NIR, and shortwave infrared, SWIR, are used for camouflage detection.
And long-wave infrared, LWIR, is for thermal detection, but also bathymetry, meaning determining water depth based on thermal mass.
Right. And platforms like the HISIS satellite use push broom imagers, capturing over 55 spectral bands, utilizing VNIR and SWIR sensors.
Okay, wait, I need to push back on one of the limitations here. The data says these systems have a low spatial resolution of 3 to 4 meters. Tactically, how is 3 to 4 meters even useful?
Well, it isn't for targeting individuals or single vehicles. It's strictly for broad trafficability and route planning for large vehicle convoys. At that massive scale, you just need to know if a whole armored division is going to get stuck in mud.
Oh, okay, that makes sense. Other limitations are non-real-time processing, atmospheric obstruction, and long revisit times.
Right. So if optical route planning is totally obstructed by atmosphere or camouflage, we switch sensory domains to passive acoustics, sound ranging systems, or SRS.
Which goes back to World War I. Passive target acquisition and source identification from air, ground, or water. Let's rattle off the core components. You have a microphone array at surveyed locations, meteorological data weather sensors, radio or line communication links.
And a command post computing system, adjusting posts and listening posts.
The listening posts are cool. They're part of the queuing process. Think of them like motion sensor driveway lights. Positioned ahead of the main array, they activate the system only when they hear something to save energy.
Yeah, it's highly efficient. The calculation principle is that the difference in receipt times across the microphones allows for a bearing calculation. The intersection of those cross bearings provides the exact location for counter bombardment.
But the limitations are brutal. It's manpower and time intensive, highly sensitive to vehicle noise, requires precise coordinate requirements for every mic, and physical cables are super vulnerable.
Which is why we integrate passive and active locating systems. Because passive acoustics have limits, we combine SRS with active electromagnetic detection, specifically weapon locating radars, or WLR.
This gives massive tactical advantages. SRS provides stealth to avoid enemy direction finding and offers continuous surveillance. It cues the WLR, which hugely reduces radar logistical constraint.
Yeah, it plugs radar gaps, provides 360-degree coverage, and is a very cost-effective deployment. Modern improvements even include self-locating GPS arrays and wireless communication to reduce setup time.
But you still have acoustic limits. The rumble effect, wind interference, temperature sensitivity, battlefield confusion, and my favorite phrase from the data, the invisibility of a silent enemy. If they just don't fire or make noise, this massive integrated system is totally blind.
Exactly. Which is why orbital observation is the ultimate safety net. To overcome the silent enemy and weather limits, we return to space with the NISAR satellite mission, a modern, dual-band, active radar satellite penetrating weather and camouflage.
NISAR is a joint satellite mission launched via the GSLV Mark II Flight F-16 vehicle. Uses a 12-meter deployable antenna, providing HISIS complementary imaging.
Right, and it uses two bands. L-band SAR from NASA, built for deep penetration of forest canopy and ice, and tracking ground deformation.
And the S-band SAR from ISAR, built for surface-level monitoring like crops and wetlands. So for your revision, L-band is the duct tissue X-ray, S-band is the surface magnifying glass.
Spot on. The objectives and applications are vast. Ground deformation tracking, disaster mitigation, infrastructure stability monitoring, sustainable forest management, oil spill detection, and economic planning. It's comprehensive. And, it leaves you with a thought for this deep dive. If a satellite can see millimeter changes under a dense forest canopy from space, and a buried copper cable can feel the pressure of a single footstep, are we rapidly entering an era where the very concept of stealth is mathematically impossible?
Moving to the next chapter. Chapter 12, revision module. Let's begin.
Right. We're starting immediately with the absolute foundation. We need to cover the physics of the shot, what defines a hit, and the specific classifications of the small arms used to fire it.
Yeah, and to really understand a hit, you have to separate two highly distinct concepts that people constantly confuse: accuracy and consistency.
Exactly.
If you think of a standard dartboard, accuracy is hitting your exact point of aim. It's putting the dart right in the bullseye. But consistency is entirely different.
Right. Consistency is getting all of your darts to land in a tight overlapping group, regardless of where they actually land on the board.
So you could have a tight group of darts just hanging out in the top left corner. That is incredibly consistent, but wildly inaccurate.
Precisely. And in ballistic science, that tight group is mathematically defined as the mean point of impact, or MPI.
God.
Achieving both accuracy and a tight MPI relies entirely on four specific pillars. First, the firer. Second, the weapon itself. Third, the ammunition. And fourth, external factors like wind and temperature.
So if any one of those four pillars introduces variance, say the ammunition has a slightly different powder charge or the shooter flinches, your MPI just spreads out, you lose consistency.
Exactly. But the weapon itself is essentially fighting the shooter every single time they pull the trigger. You're dealing with violent physical phenomena, specifically recoil and muzzle jump.
Which is just pure Newtonian physics, right?
Yeah.
Every action has an equal and opposite reaction.
Yes, exactly. Muzzle jump specifically occurs due to a combination of three factors. You have the backward recoil force, the violent explosive force of the gases exiting the muzzle, and crucially, an offset center of gravity.
Let's visualize that offset center of gravity for a second. The physical line of the barrel, the line of bore where the bullet travels, is actually located a few inches above the point where the stock meets your shoulder.
Right. The recoil force pushes straight backward along that high bore line, while the weapon's mass is centered lower, and your shoulder is providing resistance lower down.
Oh, so it creates a fulcrum.
Yes. It acts as a literal lever that physically pivots the muzzle upward.
And if you're firing a weapon on automatic, that upward pivot just compounds rapidly, doesn't it? The weapon simply doesn't have the time to settle back down into your shoulder between shots.
Exactly. This causes what we call pattern climbing. The bullets will literally draw a vertical line straight up the target.
Wow. Okay, so tracking the bullet's journey, the ballistics, we divide this into two distinct phases.
Right. Internal ballistics covers everything happening while the bullet is still inside the barrel. And the barrel isn't just a smooth pipe. It has spiral grooves called rifling, which physically grip the bullet and induce a high-speed spin.
Which provides gyroscopic stability.
Yes. But because this is an environment of extreme contained pressure, there is a major catastrophic risk if you fire a weapon with an oily barrel.
Because oil is a fluid, and physics dictates that fluids are incompressible. If you have a layer of oil trapped inside the barrel ahead of the bullet, it basically creates a hydraulic bottleneck.
You nailed it. The bullet is moving at supersonic speeds, pushing a shockwave of air and encountering that incompressible fluid. The immense pressure of the expanding gunpowder gases suddenly has nowhere to go.
That sounds dangerous.
Extremely. It causes a massive pressure spike, which can easily bulge the steel or completely rupture the barrel.
Right. Then the bullet leaves the muzzle, and we enter the second phase. External ballistics.
Where air resistance and gravity instantly take control, the drag of the air slows the bullet down and gravity pulls it relentlessly toward the earth.
So a bullet never travels in a perfectly straight line. It flies in a curved parabolic trajectory.
Always.
Okay, so knowing how precise that parabolic trajectory has to be, how do external mechanical supports alter the final impact point? Like if a shooter rests the barrel on a hard surface to steady their shot, you're saying that physically alters the ballistics.
It alters the barrel harmonics. When a round fires, the intense pressure and the bullet scraping down the rifling cause the steel barrel to violently vibrate and whip, much like a tuning fork. If you fix a bayonet to the muzzle, you are adding dense physical weight to the very end of that vibrating pendulum. That extra mass dampens the upward whip, which generally makes your hits land low compared to your ZO.
Interesting. And what if they rest the weapon on a wall or like a sandbag?
If you rest the front of the weapon directly on a hard support, the violent vibration of firing causes the barrel to actively bounce away from that upward pressure. It kicks off the hard surface, making hits land high.
Oh, wow.
Yeah. Conversely, if you rest the rear of the weapon on a support, it pushes the stock up, which angles the muzzle down, making hits land low.
That makes perfect sense. So that brings us to the tools themselves. Small arms.
Mhm.
The strict military definition here is any weapon with a caliber of less than 25 millimeters, designed to be operated by one or two people.
Yes, and we can't ignore the psychological factor either. From a tactical perspective, successfully deploying these weapons provides a major morale boost to troops in combat.
Right. And we categorize these systems strictly by their tactical function, correct?
Yes. Pistols are designed for close-range, one-handed operation. Mechanically, they can be self-loading, meaning the weapon cycles itself, but only fires one shot per trigger pull, or they can be fully automatic for a continuous stream of fire.
Then you step up to rifles, like the traditional SLR or self-loading rifle. These are optimized for aimed single shots over longer distances.
Right, they prioritize high precision and strict ammunition economy over just, a sheer volume of fire.
And sitting right between those two extremes are submachine guns, or SMGs.
Yeah.
They fire smaller pistol caliber ammunition, but they bridge the gap to automatic fire.
Offering a massive volume of fire in a highly compact, maneuverable frame, yeah. Finally, you have machine guns, designed to provide heavy, sustained covering fire. These are classified by weight and tactical role into light, medium, general purpose, and heavy machine guns.
And regardless of the classification, the main weapon parts you always need to know are the barrel, the trigger mechanism, and the magazine feeding the ammunition.
Correct. And to align all of this with the target, sighting systems break down into two broad categories.
Traditional iron sights, which require the shooter's eye to physically align a front post with a rear notch.
Right, versus modern advanced sights, which use magnifying optics, lasers, and electronics, which is actually the perfect foundation to explore the complex principles of automatic operation.
This is where the engineering numbers get truly staggering. When a cartridge detonates, an immense amount of kinetic energy is generated. But up to 40% of that total energy is not used to push the bullet out of the barrel.
No, it's intentionally redirected back into the weapon itself.
Break down exactly what that energy is doing inside the receiver.
It is powering a highly precise, sequential 10-step mechanical cycle. It's a violent process of storing and releasing energy. Step 1 is unlocking. The breech is tightly sealed to handle the explosion, so the mechanical lug securing it must physically rotate or drop out of the way.
Which frees up the mechanism for step 2, retracting. The massive bolt assembly is forced violently backward.
Correct. And as it moves back, we hit step 3, extracting. A small metal claw grabs the rim of the spent, extremely hot cartridge and rips it backward out of the firing chamber.
Leaving the chamber empty.
Exactly. Step 4 is compressing. That rearward movement crushes a heavy return spring located behind the bolt, converting the kinetic energy of the shot into potential energy stored in the spring.
We're halfway there. Step 5 is ejecting, so getting rid of the brass.
Yeah.
An internal pin kicks that empty casing right out of the ejection port.
Step 6 is cocking. The rearward motion of the bolt pushes the hammer or striker down, catching it on the sear, fully resetting the firing mechanism. Now the weapon is ready to load again.
So step 7 is feeding. The spring inside the magazine pushes a fresh, unfired round up into the open path of the bolt.
Yes. Now that return spring you mentioned earlier gets to work. Step 8 is chambering. The spring violently decompresses, driving the bolt forward to strip the new round from the magazine and push it directly into the barrel.
Step 9 is locking. The bolt reaches the front, and those mechanical lugs rotate back into place, firmly sealing the high-pressure chamber.
And finally, step 10 is releasing. The trigger is pulled, releasing the firing pin to strike the primer of the new round, and the entire cycle starts all over again.
10 completely distinct mechanical steps, happening continuously in fractions of a second. But how exactly does the weapon physically tap into that 40% of wasted energy to drive those steps?
Engineers generally rely on one of two distinct operating systems. The first is recoil operation. This harnesses the physical rearward kinetic kick of the firing event itself.
The physical pushback for the explosion just shoves the bolt backward. The classic 7.62 millimeter rifle operates on this principle, right?
It does. But the other system is gas operation. And this literally bleeds high pressure, expanding gas out of a tiny hole in the barrel before the bullet has even exited the muzzle.
Wow. And gas operation is divided into different engineering methods, isn't it?
Precisely. The first method uses a gas port to drive a physical piston. The expanding gas pushes a solid metal piston, which violently strikes an operating rod, sending the action backward. The crucial thing here is that the duty gas stays at the front of the weapon, away from the moving parts.
But there's a second method.
The second method uses a gas tube to channel the hot expanding gas directly back into the receiver, blowing it straight into the bolt carrier itself. There is no separate solid piston.
Because it removes those extra physical metal parts, it's the lightest operating system available, right?
Yes, and it maintains a very steady weapon balance. You see this method commonly used in modern light machine guns.
But blowing hot, dirty gas directly into the complex internal moving parts of a gun sounds like an engineering nightmare.
It definitely can be. The major mechanical drawback to this second method is that it is highly prone to severe carbon fouling. The microscopic soot and residue from the burned gunpowder instantly bakes onto the metal. Over time, that causes lethal friction and jams in combat.
So moving from internal mechanisms to external architecture, we see how these principles dictate modern trends and highly specialized weapon layouts. Let's unpack the bullpup layout, because this completely changes the geometry of a rifle.
It really does.
The best way to visualize a bullpup is using a car analogy. It is exactly like taking the engine from the front hood of a car and moving it entirely into the trunk. In a bullpup rifle, engineers move the magazine and the complex firing mechanism completely behind the trigger group so it rests inside the shoulder stock.
And the primary tactical advantage is overall size reduction. In close quarters combat, a long barrel gets caught on doorways and tight corners. By moving the action backward, the entire weapon becomes about 30% shorter.
But crucially, it does this without sacrificing a single inch of barrel length or muzzle velocity.
Exactly. It also shifts the center of gravity much closer to the shooter's shoulder, drastically improving balance and reducing arm fatigue during long patrols.
But sticking with that car analogy, if the engine is in the back, the mechanical explosion is happening right next to the driver's head. The major disadvantage of the bullpup layout is that the firing mechanism, and specifically the ejection port throwing out burning hot brass, are positioned mere inches from the shooter's face.
Which is why modular and ambidextrous systems have become an absolute necessity in modern weapon architecture, because, a left-handed shooter would get hit in the face with brass firing a right-handed bullpup.
Oh, right.
So modern platforms use shared common components and ambidextrous architecture. This allows operators to instantly switch the safety selector, the charging handle, and even the ejection direction from the right side to left side in the field.
And they also universally integrate the Picatinny rail, right?
Yeah.
Which is a standardized slotted mounting bracket for instantly attaching optics, lasers, and grips without needing gunsmith tools.
Exactly.
Let's look at another unique mechanical layout that solves a completely different problem: the Gatling gun.
The Gatling gun abandons the concept of a single barrel entirely in favor of multiple rotating barrels. The fundamental physics benefit here is thermal management.
Because rapid automatic fire generates immense metal warping heat.
Right. If one single barrel fires thousands of rounds a minute, it will physically melt and fail. But with multiple barrels rotating, each individual barrel only fires a fraction of the total rounds. As it spins through the cycle, it rapidly cools in the ambient air, preventing catastrophic thermal failure while maintaining an unbelievable rate of fire.
Now let's analyze specific modern weapon families in use, starting with the INSAS family, which operates in the 5.56mm caliber.
The INSAS family is a comprehensive tactical system that includes an assault rifle, a light machine gun, and a carbine. The engineering features are highly specific and designed for mass deployment.
It uses a pressed sheet metal housing, right? Stamping sheet metal is vastly faster and cheaper to manufacture than milling receivers out of solid steel blocks.
Yes, it utilizes a rotating block breech to ensure perfectly secure locking under the high pressure of the 5.56 round.
And the accessories are heavily customized for combat realities. Like, it incorporates beta light sights, which use glowing tritium gas to provide low light illumination without ever needing batteries.
Plus, it features translucent plastic magazines. This is critical because, in the extreme stress of a firefight, a soldier loses count of their rounds. Translucent plastic allows them to visually check their exact ammunition count instantly.
It also uses plastic furniture for the stock and grips to shed overall weight.
Absolutely. A vital mechanical feature of the INSAS is the 3-round burst, or TRB mechanism. An internal sear mechanically limits the automatic cycle to exactly 3 shots per trigger pull,
Giving you 70% less recoil compared to sustained, fully automatic fire.
Exactly. It keeps the weapon lightweight and compact while allowing the operator to maintain tight target control. And maintaining the integrity of all these systems requires rigorous procedural standards.
Right, like tracer-proof testing to ensure the barrel metallurgy can handle the intense burning heat of pyrotechnic tracer ammunition.
And comprehensive ballistic drills for operators, plus thorough standardized weapon inspections across the armory.
Then you have systems focused heavily on operator ergonomics, like the Tavor assault rifle.
The Tarai is a modern bullpup that heavily emphasizes human-machine integration. It's uniquely balanced and designed for single-hand operation, allowing a soldier to return fire even if one arm is incapacitated.
It features integral sights specifically calibrated for both eyes open firing, right?
Yes, this prevents tunnel vision, preserving the operator's peripheral vision and vital situational awareness. The tactical variants include the standard TAR-21, a highly shortened paratrooper version optimized for extreme confined spaces, and the TAR S-21 sharpshooter model,
Which comes equipped from the factory with a 4x optical sight for extended range engagements.
spot on.
But what about highly specialized asymmetrical tactical environments? That's where the mechanics of the corner shot weapon system come into play.
The corner shot is an articulated tactical platform. It physically bends. It consists of a front handgun section that can pivot up to 60 degrees left or right.
And the rear shoulder section holds the actual trigger, a video monitor, and the stock.
Right. The trigger in the back is mechanically linked to the gun in the front, and a high-resolution camera feeds the sights directly to the monitor. This geometry provides accurate, aimed fire up to 200 meters without ever exposing the operator's head or torso to incoming enemy fire.
And to round out the new introductions to modern armories that you need to have logged, there's the AK-203 assault rifle, the NEDGV light machine gun, and the ASMI submachine gun.
But for every advancement in kinetic weapons, we must understand the engineering countermeasures. This brings us to advances in armor and the emerging frontiers of armament technology.
Let's dissect the physics of bulletproof glass, specifically for anti-terrorist and VIP protection applications. The popular concept of one-way fire glass seems to defy physics. How can a specialized response team sitting inside a vehicle shoot their weapons out through the glass while incoming enemy fire is completely stopped from getting in?
It doesn't defy physics at all. It relies entirely on asymmetrical layering. Modern bulletproof glass features advanced variants like low spall and no spall.
Spall being the lethal, razor-sharp fragments of glass that explosively shear off the inside surface when a bullet strikes the outside.
Right, and you want to prevent that spall from hitting the passengers. The one-way fire property works because the glass is built with a hard, brittle, energy-absorbing layer mounted on the outside and a soft, flexible polycarbonate catching layer mounted on the inside.
So if you fire a weapon from the inside of the vehicle looking out,
The bullet easily punches through that soft, flexible interior layer first. The outward pressure from the bullet then violently shatters the hard outer layer, letting the bullet exit the vehicle with lethal force.
but if an enemy fires from the outside, the physics reverse.
Exactly. The incoming bullet strikes the hard, brittle outer layer first. This flattens the bullet, stripping its aerodynamics and dispersing its massive kinetic energy across a wide surface area of shattered glass.
And whatever kinetic energy remains is caught by the flexible interior polycarbonate layer, which stretches and deforms, acting exactly like a baseball catcher's mitt.
You've got it. However, there's a hard physical limit to this one-way effectiveness. It is generally effective only up to a 7.62 millimeter caliber limit. Anything heavier, like a 50 caliber round, contains too much kinetic energy and overcomes the structural design entirely.
Let's move from vehicles to individual personnel protection, body armor.
Traditional advances in body armor rely on weaving sturdy aramid fibers like Kevlar, layering rigid plastic laminates, and even deploying modern lightweight variations of historical chainmail.
Because the protection profile of a modern vest must be multi-spectrum. It cannot just stop bullets. It has to cover high-velocity ballistic threats, slicing-edged blades, and penetrating spikes used in close-quarters ambushes.
Yes, but material science is currently pushing past woven fabrics entirely into liquid body armor.
Specifically utilizing STF, or shear thickening fluid. This relies on non-Newtonian physics, right?
It does. Under normal ambient conditions, the STF remains a flexible, viscous fluid. This allows the soldier full mobility to bend and run, but the instant it is subjected to the high-velocity, high-shear impact of a bullet, the molecules instantly lock together.
So the fluid rapidly transitions into a rigid solid, spreading the kinetic energy across a wide surface area to prevent blunt force trauma.
Exactly.
But adding layers of liquid and hard plates creates an incredible weight burden.
Which is why we are seeing the simultaneous development of powered exoskeleton armor. These are robotic, motorized frames worn over the uniform, designed to physically bear the heavy weight of these advanced protection systems. They transfer the load directly to the ground and save the soldier from combat exhaustion.
Which brings us to the absolute frontier. Offensive weapons that don't rely on traditional kinetic mass and gunpowder at all. Directed energy weapons, or DEW.
DWs operate by projecting photons or particles at the literal speed of light rather than firing a physical heavy bullet. A major category of this is high-power microwaves, or HPM.
HPM technology doesn't destroy physical structures, though. Instead, it uses intense, invisible bursts of radio frequency power to induce massive voltage spikes.
Right, this causes instant, catastrophic electronic overload, completely frying the circuitry in enemy computers, drones, and communication systems.
Another major category within directed energy is charged particle beams, or CPB. Instead of microwaves, CPBs project accelerated streams of atomic or subatomic particles to heat and destroy physical targets at a molecular level.
Correct. And alongside these offensive frontiers, there are specific defensive and non-lethal technologies that dictate modern engagements. Active denial technology acts as a non-lethal weapon for riot control and perimeter defense.
That's the one that projects millimeter waves, right? That harmlessly but painfully heat the water molecules in the very top layer of human skin, forcing targets to instinctively retreat.
Yes, exactly. Defensively, against kinetic weapons, you have highly automated intercept systems like the phalanx on naval ships and the Iron Dome. These systems instantly calculate incoming trajectories and shoot down airborne threats like rockets and mortars faster than human reflexes allow.
And the increasing automation of those very defensive tracking systems leads directly into the development of laws wars, lethal autonomous weapons. These systems raise profound offensive concerns regarding autonomous decision-making in combat.
It's a huge debate. The core issue military ethicists and engineers are looking at is whether a machine algorithm should be permitted to independently decide to identify, target, and use lethal force without direct human intervention or oversight.
Finally, even traditional kinetic ammunition is fundamentally evolving to keep pace with these high-tech platforms. The current frontier for infantry rifles is case telescopic, or CT, munitions.
Yes.
Telescopic meaning the actual bullet is physically seated entirely inside the cartridge case, totally surrounded by the propellant powder, rather than protruding out the front like a traditional brass round.
Precisely. By redesigning the geometry to a perfect cylinder and utilizing advanced heat-resistant polymer cartridge cases instead of traditional heavy brass, CT munitions offer a massive 33% weight reduction per round.
Which drastically alters battlefield logistics. It allows a single soldier to carry a significantly higher volume of ammunition into an extended engagement without increasing their physical load, completely shifting sustained fire capabilities.
Exactly.
Moving to next chapter.
Chapter 13, Revision Module.
Right, so we are jumping straight into the foundational classifications of artillery today. And to set the baseline, we're starting strictly with infantry and artillery mortars.
Because, if you think about it, we have to look at the simplest application of artillery first, which is just taking advantage of a vertical impact trajectory.
Exactly. Mortars are defined entirely by their physical weight and their caliber dimensions, and they are engineered to exploit that high plunging arc.
Which is a huge advantage for you on the battlefield. Think about dropping a heavyweight straight down through a narrow opening like a chimney versus trying to throw it horizontally through a window from a mile away.
The physics of the horizontal throw are incredibly difficult, right? But dropping it straight down bypasses horizontal cover entirely. So the military strictly categorizes these into 3 tiers.
Okay, lay out the specific specs for those tiers.
First, you have your light mortars. These are systems with a caliber up to 60 millimeters, and the total system weight is capped at 18 kilograms.
So, highly portable, one person can easily move that.
Exactly. Then you scale up to the medium mortars. These sit right between 60 and 100 millimeters in caliber, and the weight jumps up significantly, falling anywhere between 34 and 68 kilograms.
Okay, so you need a dedicated crew for that, but it's still man-portable in pieces. And then the heavy tier.
Heavy mortars are strictly classified as anything over 100 millimeters. These are the massive systems engineered specifically to project munitions across ranges exceeding 6,000 meters.
Wow, okay. Over 6,000 meters. So regardless of the tier, the advantages remain the same, right? They have a very low production cost, you can deploy them rapidly, and you get that devastating vertical impact trajectory.
Yes, but you must know the physical disadvantages too. Because you are launching on such a steep, high-angle arc, mortars suffer from a severely limited overall range compared to standard flat trajectory artillery.
Right, because so much of the energy is just spent going straight up against gravity.
Precisely. Furthermore, that high arc dictates a very long time of flight. I mean, if a heavy mortar shell is in the air for 30 seconds, that gives a smart enemy time to react.
And another disadvantage is that you can't just drop the tube on the grass and immediately fire at maximum capacity, right? They require bedding in.
Bedding in is a strict mechanical requirement.
Yeah.
When you fire, the baseplate transfers all that extreme downward recoil directly into the dirt. The baseplate must physically displace and compact the earth beneath it to settle securely.
Because if the dirt is soft, it just sinks and your aim is ruined.
Right. Until that earth is fully compacted, the weapon lacks perfect stability. Now, to actually launch these shells, we have to transition into the chemical power of explosives and propellants.
Because we aren't just lighting a match here. We are manipulating severe thermodynamic events to generate force.
Exactly. You need to memorize the 3 strict classifications of reaction velocities. The first and lowest level is just burning, which is a slow oxidation.
Like a campfire, just slow ambient heat.
Yes. The second level is an explosion. This is rapid combustion, where expanding gases push outward at a velocity of anywhere from 3 to 300 meters per second.
Okay, so much faster. But the third one is the extreme one, right? Detonation.
Detonation is instantaneous molecular disintegration. It produces a supersonic shockwave traveling through the material at a staggering 2,000 to 9,000 meters per second.
That is insane. And to harness that push without just blowing the gun to pieces, the military relies on very specific propellant classes.
Right, and they are strictly formulated. You start with single-base propellant, which relies entirely on nitrocellulose.
But if you need to hit targets further away, you need more energy. So you step up to double-base propellant, which integrates nitrocellulose and nitroglycerin.
Correct. And then the most advanced is triple-base propellant. This uses nitrocellulose and nitroglycerin, but it introduces a third chemical element, which is picrite.
Now, wait, why add picrite? Does it just make the explosion bigger?
Actually, it does the exact opposite regarding heat. Picrite specifically lowers the burning temperature of the propellant. By dropping the ambient temperature of the reaction, you drastically reduce wear on the steel barrel.
Oh, that makes sense. Less heat melting the steel.
And crucially, it reduces the muzzle flash. If you have a massive fireball lighting up the night sky, your position is immediately compromised.
Right, you want to stay hidden. There is also a fourth class, right? Composite propellants, which just toss out that specific organic chemistry entirely.
Yes. Composites use a strictly measured fuel, an oxidizer to feed that fuel, and a chemical binder to hold the entire matrix together. But for any of these to be authorized, they must meet rigid military requirements.
They have to guarantee barrel protection, generate zero smoke and zero muzzle flash, and maintain total chemical stability during storage.
Yes, but the most critical internal requirement is that they must burn on all exposed surfaces simultaneously. This is governed by the burning laws.
Right, specifically Pyobert's law, which basically states that the ballistic size is strictly the least dimension thickness, and the rate of burning increases linearly with pressure.
Exactly, and this dictates the rate of burning, or ROB geometries.
Let me quickly clarify Pyobert's law for you with a geometry analogy, because it is vital. If you have a solid block-shaped piece of propellant, as it burns from the outside in, the surface area shrinks, right?
Yes, its surface area regresses.
And as it shrinks, there is less fuel exposed to the fire, so the pressure actually drops off while the shell is still in the barrel. That is a digressive rate of burning, which is terrible for artillery.
It is entirely inefficient, so engineers manipulate the geometry. Instead of a solid block, they shape the propellant into long or slotted tubes.
Because with a slotted tube, the fire burns on the inside of the slot too. As the inside hollows out, the internal surface area physically expands.
Precisely. That progressive geometry means more fuel is exposed as time goes on, ensuring a nearly constant or increasing rate of gas production to keep pushing the heavy projectile.
That is brilliant. Now, that is for the propellant pushing the shell. For the actual warhead at the destination, we use high explosives and demolitions, which rely on that third velocity detonation.
Right. They utilize rapid chemical decomposition for extreme pressure and temperature, and that shockwave is triggered by specific initiators. You will see materials like plastic PK1, solid powders, or ammonal.
An amoquinol is specifically applied when the explosive needs to seal tightly and withstand intense external pressure before going off, right?
Correct. So we have this massive supersonic chemical blast. Now we must examine the structural anatomy required to contain that blast. There are 9 major components to any artillery piece.
Okay, walk me through them.
First, the barrel ordnance, the breech mechanism to seal it, the firing mechanism, the sighting system, the superstructure, and the recoil system.
That is 6.
Then you have the aiming and laying apparatus, the ground contact stability, and finally, the prime mover connection.
Let me push back slightly on those last two. Ground contact stability and prime mover connection sound like, I don't know, accessories. Are they really as vital as the barrel itself?
They are absolutely as vital because they directly satisfy the 6 strict operating principles. If you lack ground contact stability, you completely fail principle number 5, which is stability on a stationary carriage.
Oh, meaning the propellant pressure would just flip the gun backward into the dirt.
Exactly. And the prime mover connection, hooking it to a truck, is required for the 4th principle, mobility. The other principles are containing propellant pressure, achieving muzzle velocity, obturation, and carriage alignment.
So configuration is basically defined by mounting that ground barrel ordnance onto the mobility carriage.
Right. And artillery roles are divided by this configuration. You have guns for low-angle fire, howitzers for higher angles, and mortars. But the universal goal is maximizing surface-to-surface missiles, or SSM, lethality, and precision.
And the most critical high-stress failure point of this entire anatomy is the breech. It is the back door where the explosion happens.
The breech mechanism has 3 distinct functions. It must carry the firing mechanism. In quick firing, or QF guns, it must support and extract the brass cartridge. And in breech loading, or BL guns, it must carry the obturation assembly.
And the military requirements here are non-negotiable. Absolute absolute safety, reliability, and mechanical simplicity for crews under fire.
Correct. To achieve this, there are two primary mechanisms. First is the sliding block mechanism, common in QF guns.
You can instantly visualize this like a massive bank vault door, specifically a deadbolt. The sliding block acts just like a steel deadbolt sliding across the back of the chamber.
Exactly. It can be horizontal, like in the 105mm light field gun, or vertical, as seen in the 100mm field gun. They use semi-automatic action upon recoil.
And to stop that deadbolt from blowing backward into the crew, it relies on intense mechanical locks, right?
Yes, specifically strut locks, or pass-dead center type locks. Now, the second type is the screw breach mechanism, common in BL ordnance.
Sticking with the vault analogy, this one is like the interlocking wheel on a bank vault.
Right. It relies on interrupted threads. The operator swings the breech shut on a carrier swing arm. With just a partial turn, the interrupted threads on the breech block interlock perfectly with the threads on the inner barrel.
And inside these breeches, you have the firing mechanisms to spark the propellant. You have percussion mechanisms, which use a physical strike from a pin or hammer.
Then you have electric mechanisms, which use heat from a localized current, or combination systems for redundancy.
But for the breech loading guns, because there is no brass cartridge casing to expand and seal the chamber, you mentioned they need obturation.
Obturation is the sealing of propellant gases. It uses a specialized ring assembly. When the pressure spikes, that ring is violently forced outward against the steel, perfectly sealing the gap to protect the crew from lethal gas blowback.
Okay, so the breech is locked, the obturation is sealed, and the chemical propellant expands. All that forward kinetic energy pushing the shell creates an equally violent backward force on the gun.
Which brings us to recoil systems and gun stability. This is founded purely on Newton's third law. The shock of discharge produces an equal and opposite reaction.
To manage that force, engineers have to balance 4 specific stability factors.
Right. You have the trunnion pull, which is the shear backward force. You have the trunnion height off the ground. You have the trail lengths, which are the rear legs pinning it to the earth, and the total weight of the gun.
And these plug into a strict stability formula. You calculate a correcting moment by multiplying the weight by the trail length, and you calculate a turning moment by multiplying the backward force by the trunnion height.
And for the gun to survive without flipping, the correcting moment must be greater than the turning moment.
Let me walk you through this with a playground seesaw analogy because it instantly visualizes the math. The trunnion is the pivot in the middle. The trunnion pull is like a heavy adult jumping onto the very short end of the seesaw.
Right. The short end represents the trunnion height.
To stop that adult from slamming the board into the ground, you need a child representing the weight of the gun, sitting all the way out at the far end of a much longer board, which is the trail length.
The longer the trail and the heavier the mass, the more leverage you generate. But you also rely on the recoil mechanism to absorb the raw energy.
That is a 2-part system, right? The buffer and the recuperator.
Yes. The buffer is an energy storage system that absorbs the rearward velocity over a fixed distance. Then the recuperator returns the heavy barrel smoothly forward to the runout position using mechanical springs, pneumatic compressed gas, or hydropneumatic oil and gas.
But if you aim the gun really high, like at a steep angle, and the barrel recoils straight back, the breech will smash into the ground.
Which is why they integrate cutoff gears. These are mechanical adjustments linked to the elevation. They dynamically shorten the recoil path when the barrel is elevated, stopping the breech just before it hits the dirt.
Okay, so the gun fires, the recoil is managed safely. Now we have to track the projectile's timeline, starting with the internal ballistics inside the bore.
The internal sequence is extremely fast. It begins with ignition. The pressure spikes until it physically overcomes the friction of the shell wedged in the rifling. That exact threshold is the shot start pressure.
Once it starts sliding, the gas catches up and hits Pmax, the absolute maximum pressure.
Right. The propellant then fully burns out at the all burnt point, or ABP. From the ABP onward, there's no more combustion. The shell is pushed the remaining length purely by adiabatic expansion of the trapped heat and gas.
Now, I want to emphasize the speed here because this is mind-boggling. This entire sequence from ignition to adiabatic expansion at the muzzle,
It takes only 15 to 25 milliseconds.
roughly 20 milliseconds. And in that fraction of a second, the internal temperature hits 2,000 degrees Celsius.
That intense 20 millisecond event strictly determines your final muzzle velocity, your overall efficiency, and your flash reduction. We visualize this using a PV curve, where a pressure line and velocity line strictly track the shots travel down the bore.
I just picture the whole thing like a car engine cylinder. The barrel is the cylinder, the heavy shell is the piston, and the propellant is the highly combustible fuel.
That is a highly accurate analogy. But once that piston exits the muzzle, external ballistics govern the flight. The projectile is immediately subjected to air resistance, stripping its velocity, and gravity pulling its mass downward.
Those external forces warp the perfect theoretical vacuum flight path into a parabolic arc, right? Resulting in a severely reduced range and height.
Correct. And to ensure that arc actually terminates on an enemy target, we rely on fuses and sighting systems.
The fuse is basically a mechanical brain triggering the projectile. They are classified either by their internal magazine filling or by their specific action.
Yes. And if you're using high explosive or HE shells, the fuse must contain a gain. A gain converts the initial small flash of the fuse into a massive detonation wave capable of shattering the thick steel body of the HE shell.
Now let me question this mechanical brain concept, because if it's just a timer ticking down inside the shell, that sounds incredibly dangerous. What if a soldier drops it?
A timer alone is completely insufficient. The safety and arming forces rely strictly on the extreme physical physics of launch. It requires setback forces.
Setback forces.
Yes, the violent physical shock of firing, which pulls up to 50,000 G-forces, must physically shear a heavy metal pin inside the fuse.
Yeah.
Without that 50,000 G-force shock, the fuse remains mechanically locked and totally safe.
Oh, wow. So you could literally drop it off a roof and it will not arm. Now, sighting relates the physical bore axis of the barrel to the line of sight, ensuring that arc intersects the target.
The strict terms you must know are line of sight, angle of sight, and trajectory. And laying the gun means mechanically setting the line, which is your horizontal azimuth, and the elevation, your vertical angle.
But targeting isn't just about angles. The computers have to calculate the projectile head, the specific ogive shape, the body friction, and the base drag.
Because external stability forces are constantly manipulating the shell. The rifling spin causes gyroscopic precession and drift, physically pulling it sideways. You must account for that drift, air density, and wind.
And in tactical firing, you always aim for maximum surprise and strictly avoid target fixation or survey errors. If your starting coordinates are wrong, you miss everything.
To eliminate survey errors, calibration utilizes advanced tools. tracking radars, DGPS positioning, real-time meteorology data for air density, and burst firing with cross-observation.
Okay, we have covered the blast, the flight, the targeting, but we have to conclude with how the barrel survives these forces in the first place through advanced barrel construction.
Right. The engineering goal here is to handle increasingly higher internal gas pressure without adding massive dead weight. If the barrel is too thick, you lose your mobility principle.
So they achieve this balance through pre-stressing, which conditions the inner layers of the steel. I want to elaborate on the tight compression vest analogy for pre-stressing because it makes it instantly understandable.
Okay.
If you take a deep breath, your ribs take all the outward strain. But if you wrap your torso in a really tight, heavy compression vest, it pushes inward constantly. So when you expand your chest, that outward lung pressure is completely canceled out by the inward pushing of the vest.
In metallurgy, we achieve that using a process called auto-frettage or self-hooping. During manufacturing, extreme hydraulic pressure is pumped into the bore until the inner layers stretch past their elastic limit.
Meaning they undergo plastic deformation, they're stretched permanently and won't shrink back.
Right, but the outer layers of the thick steel only expand within their elastic limit. So when the factory releases that hydraulic pressure, those outer layers try to shrink violently back to their original size.
But the inner layers are in the way because they are permanently stretched. So it creates this massive permanent state of residual compression. The barrel is constantly squeezing inward on itself.
Exactly. And engineers utilize 3 distinct construction forms: monoblock, which is a single piece; loose barrel, where a worn internal liner can be swapped out; and built-up barrel, where heated outer jackets are tightly shrunk onto inner tubes.
And they also bolt muzzle brakes to the end of these assemblies. Muzzle brakes use angled baffle plates and ports to catch the escaping gas and deflect it backward.
Which physically pulls the barrel forward to fight rearward recoil. Ultimately, the overarching barrel physics dictate that this massive tube must behave as an elastic body, adhering strictly to Hooke's law of stress and strain.
It has to handle radial compressive stress pushing outward and circumferential hoop stress trying to split it at the seams, right?
Yes. The thick steel acts as a continuous longitudinal girder, providing vital torsional strength against the twisting friction of the rifled shell.
And the absolute maximum limit of all this engineering is defined as the elastic strength pressure, or ESP.
ESP must be managed with a strict factor of safety of 1.5 against the permissible pressure. And that permissible pressure marks the exact yield point where the steel suffers a 0.2% permanent dimensional change.
Because if you cross that 0.2% threshold, the barrel is permanently warped and the next shell could jam and cause a catastrophic blowout.
Exactly. To guarantee it withstands the extreme proof gas pressure during factory testing, they rely on thicker breeches, papered muzzles, and outer jackets.
Moving to next chapter.
Chapter 14, Revision Module. Let's start.
Right, so we are jumping straight into the mathematics of location.
Yeah, specifically how artillery systems know exactly where they are without GPS, because, GPS is easily jammed.
Exactly. And the core of this is the artillery gun laying system, or AGLS.
And the AGLS basically uses an inertial navigation system, right? The INS.
Yes, the INS, paired with a fire control computer and a power unit.
And the physics here are super basic at the core, like it just relies on Newton's second law.
Right, force equals mass times acceleration.
Yeah.
So the INS uses these highly sensitive sensors. It has gyroscopes to measure angular velocity.
Like when the vehicle tilts or turns.
Yeah, exactly. And it uses accelerometers to measure linear acceleration.
Okay, so a quick analogy for you listening. Just imagine you are blindfolded in a field. If you know your exact starting point, your precise stride length, and the exact angles of your turns, you know your location without needing to see anything.
That is dead reckoning. And because it does all that math internally, there is absolutely zero time drift compared to satellite signals.
And it works continuously. You literally cannot jam it with electronic warfare.
Right, but the INS does have one vulnerability. Over a long period, microscopic friction causes the internal math to drift.
So what is the backup?
It uses the vehicle's odometer as a backup velocity sensor to cross-reference the physical tire rotation.
Got it. And all of this integrates into a hybrid system called line-apps, right?
Yes, line-apps. The advantages are huge. Continuous data, zero GPS reliance, and no manual surveying or pounding aiming posts into the dirt.
Plus it is retrofit ready, right? You can just bolt it onto older guns.
Yeah, which gives them super fast into-action times, instant 3D self-location, and full all-weather capability.
Okay, so that covers location. Let's move to next generation firepower. How are they shooting further and faster?
Well, it starts with propulsion. They are moving to liquid propellant guns, utilizing monopropellants and bipropellants.
But the real shift is the ignition, right? The electrothermal chemical ignition, or ETC.
Exactly. ETC uses a plasma cartridge instead of a regular primer. It creates this perfectly predictable propellant expansion every single time.
Which means predictable pressure and extreme accuracy. But what about totally replacing gunpowder? Like electromagnetic guns?
Oh yeah, using the Lorentz force. Railgun technology is wild. It uses massive electrical currents to shoot a solid metal slug at a muzzle velocity of Mach 6.
Wait, Mach 6.
Yeah, the kinetic energy alone provides completely devastating lethality. You don't even need explosives.
And the future versions, the electromagnetic railguns, or EMRG, they want to hit Mach 7 to 8 using pulse power systems.
But friction melts the rails at that speed, so engineers are pivoting to coil guns or Gauss guns.
Using electromagnetic coils instead of parallel rails to pull the projectile forward.
Right, which drastically reduces the rail wear.
Okay, what about the actual shells? We're looking at autonomous precision-guided munitions, or APGM.
Yeah, which drastically lowers logistics costs. You fire one smart shell with AI and sensors for self-target ID instead of 100 dumb ones.
Like the Excalibur M982. It uses GPS, deploys folding glide fins, and guarantees a 10-meter accuracy radius.
And we are seeing more smart projectiles that make mid-air trajectory adjustments using adaptive smart fuses.
But what if you just want to disable electronics without explosions?
Then you use a flux compression generator, or FCG. It creates an electromagnetic pulse.
So it is a non-kinetic disabling weapon.
Exactly. It induces massive electrical currents in circuit boards and just fries the enemy's electronics.
Okay, looking at general trends, calibers are hitting 155 millimeters or more.
Yeah, increased high explosive capacity, nuclear capability, and smart guidance sensors.
And for range extensions, they are using 45 and 52 caliber systems. That means barrels up to 8 meters long, right?
Right, and to keep the shell flying, they use base bleed technology to fill the low-pressure vacuum and reduce aerodynamic drag. drag.
Plus, rocket-assisted projectiles, or RAP, and traveling charges, but pushing that much weight creates massive recoil.
Huge recoil. So they use advanced metallurgy, plastics, and the soft recoil concept.
Oh, the soft recoil concept is fascinating. The barrel slides forward right before it fires.
Yeah, that initial forward movement absorbs the rearward blast, resulting in a 70% force reduction.
Which allows for lighter carriages. And for mobility, they are adding independent wheel assemblies and auxiliary power units, or APUs, for better traction.
Right. Now, as for the rate of fire, the burst goal is 3 rounds in 8 to 12 seconds.
Wait, only 3 rounds in 12 seconds. With all this automation, why is it so slow?
It is thermodynamics. Barrel overheating is the main limit. Plus, the ammo weight, the shells are nearly 100 pounds, and just general human fatigue.
Even with mechanized rammers, automatic breaches, and auto gun laying, reducing the crew to 4-man detachments.
Yeah, physics still dictates the limit.
Yeah.
If you need extreme volume, you use rocket artillery, like the Smerch 9K58.
Okay, let's ground this theory into actual systems. The M777 and the K9 Vajra.
Two completely different platforms. The M777 ultralight howitzer is built for shoot and scoot capability.
It is basically the ultralight sports car of artillery, made of titanium and aluminum alloys, weighing only 4,200 kilograms.
Which means it is air portable by helicopters. It has a super low silhouette of 1.3 meters and a 3-minute setup or ceasefire time.
And it uses the M777 gun management system, or GMS, so it has an inertial navigation unit, a distance transmission unit, and a detachment commander display terminal.
And a muzzle velocity radar. It is literally a sniper in a backpack.
Well, the K9 Vajra is a self-propelled track vehicle, a fortress on tracks.
Right, it has 14.5 millimeter armor-piercing protection, NBC protection, crew cooling, and a 1,000 horsepower engine.
Its armament is that huge 155 millimeter 52 caliber gun with automatic ammunition ramming, hitting a 38-kilometer maximum range.
And it is all managed by an automated fire control system, or AFCS, which networks the operator control computer, interface control computer, and direct fire sight.
But both the sports car and the Juggernaut use precision digital fire control with a ring laser gyro INU, same dead reckoning math.
Exactly, so that is ground bombardment. But air defense is completely changing because of the drone paradox.
Right, the terrifying math where you spend a $3 million missile to shoot down a $500 drone.
You bankrupt yourself defending your base. So tactical air defense needs high muzzle velocity guns, ballistic shell shapes, and HE content for lethal fragment clouds.
Missiles are still used for ballistic missile defense, or BMD, that is a 2-tiered system with a 5,000-kilometer range.
Yeah, the high layer uses the Prithvi air defense, or PAR. The low layer uses the advanced air defense, or AAD, relying on 3D phase array sensors and ultra-fast processing.
But down low, we are back to guns like the ZU-23, tow trailer, dual air and ground roll under 1 ton.
And completely dismantleable. It deploys in 30 seconds, uses manual telescopic sights, twin-barrel gas operation, and fires 2,000 rounds per minute.
And the bigger brother, the ZSU-23 Shilka, is self-propelled, tracked, with 4 barrels protecting moving columns.
It has full NBC protection and uses quad-barrel water cooling so it doesn't melt. The upgraded Shilka features a 3D active phased array radar,
which is specifically for multi-target and low RCS drone detection, plus an electro-optical suite with daylight TV, thermal imaging, and a laser rangefinder.
Then you have the 40mm L70 gun. It uses all-electric brushless motors for silent battery operation.
It uses an integrated optronic pedestal and a system management computer that is totally ECM resistant, plus its own INS.
Right. Engagement speed is 450 meters per second, max range of 12,600 meters, firing 300 rounds per minute at 1,000 meters per second muzzle velocity.
Which brings us back to the hard kill capability needed for that drone paradox. We need GPS-independent fiber optic control.
Because you can't jam a fiber optic cable. Operation Sindor proved that dense AD gun engagement curtains actually work against swarms.
But you need counter-UAS or CUAS technology, programmable airburst rounds, and advanced ballistic computers.
Specifically, pre-fragmented programmable control, or PFFC rounds. They use proximity fusing to detonate fragment clouds perfectly in the drone's path.
So the hard kill chain is rapid. The sensor detects, the computer classifies, calculates future position, computes ballistics, and engages.
Exactly, and you need AC radars and EO sensors for that automatic tracking to defeat swarms cost-effectively.
And looking ahead, future CUAS means remote weapon stations, hybrid RF jamming, Gatling platforms, and directed energy lasers.
Plus gun-launched guided projectiles with steerable fins and onboard seekers.
Oh, and EMP tech, using terawatt peak power from flux compression generators to cause magnetic field induction.
Right, the semiconductor fry effect. Non-kinetic internal disintegration for the whole swarm.
Okay, wrapping up with the final defense layers, let's look at mortars.
Modern mortars are highly specialized. 60mm at the company level, 81mm at the battalion level, and 120mm for specialized reconnaissance.
We have twin barrel systems for mechanized forces, and the STK 120mm on a 4x4 light vehicle for low recoil.
And smart mortar tech is crazy now. GPS and laser seekers, ballistic computers, digital add-ons.
They even have laser gyro INS, remote controls, rocket-assisted projectiles, and automated muzzle loading pushing ranges up to 17.5 kilometers.
So that is the precise close-in scalpel. Now for the strategic sledgehammer, the S-400 Triumph.
5-minute deployment time, targets 36 threats simultaneously with 384 missiles.
It uses a cold launch gas system and a strictly layered defense approach.
It uses the 9M96 missile with active radar homing and directed explosion warheads for high-altitude intercept.
And the 40N6 missile for long-range threats like cruise missile intercepts at 40 kilometers.
Moving to the next chapter.
Chapter 15. Smart munitions, mine warfare, small arms ammunition, mine detection, and breaching technologies. Let's start.
So when you picture modern warfare, you probably just imagine like chaotic, overwhelming destruction everywhere.
Right, just total chaos.
Exactly. But if you actually look at the mechanics today, the reality is this massive shift toward incredibly precise, high-stakes math.
Yeah, moving from the era of dumb ballistics to hyper-precision. So, I mean, how exactly do you put an explosive exactly where you want it without, hitting anything else?
Well, it all comes down to smart munitions. And the entire purpose here is twofold. First, minimize collateral damage. And second, allow the launch platform like a jet to stay safely outside the enemy's air defense envelope.
Okay, so they're using semi-active systems for this.
Right. And when we talk about that precision, we have to start with laser-guided bombs, or LGBs.
Because an LGB doesn't just guess where the target is.
No, not at all. It uses a precision guidance mechanism that requires an external designator pointing a laser at the target. The bomb itself has a photodiode seeker tuned to a specific PRF.
Pulse repetition frequency, right?
Exactly, PRF. That ensures the bomb only chases its specific laser, not just any random bright light on the battlefield.
And the flight happens in 3 distinct phases, doesn't it? You've got the ballistic phase right after dropping, then the transition phase where sensors acquire the laser, and finally the terminal phase where it steers into the target.
Spot on. But there's a huge vulnerability there. The pilot has to stay near the target to keep that laser painted on it.
Which means they rely on complex designation systems like Lantern and Lightning, but loitering in hostile airspace is just insanely dangerous.
Which is exactly why the military developed smart bombs like JDAM's Joint Direct Attack Munitions. A JDAM basically takes a standard dumb bomb and just slaps a tail section onto it with GPS guidance.
Right, so because it relies on GPS coordinates instead of a live laser, the pilot doesn't have to stick around. They can drop it and do an immediate maneuver to escape. Plus, they cost less, right?
They do, yeah. But you definitely trade accuracy for that safety. We measure that accuracy using CEP, or circular error probable. For LGB, the CEP is a razor-thin 3 meters.
Wow.
Yeah, but for JDAM relying on GPS, that CEP widens a lot, like 13 to 30 meters.
That's a big difference. But it's fascinating how ammunition is evolving. Like, you see self-steering munitions now, comm jammers built into shells, and even radar echo shells designed to spoof enemy defenses.
Oh, absolutely. And we're seeing shifts in materials, too, like the combustible cases used on systems like the Swedish FH-77B.
And the payloads are just shockingly destructive now.
I mean, we're talking about everything up to 2-kiloton tactical nuclear shells.
Yeah.
Even with conventional explosives, they're maximizing lethality with pre-notched casings.
Pre-notch, like the metal is physically scored before it's fired.
Exactly. It ensures the casing fractures into this mathematically perfect fragment size for maximum damage. You also have explosion-expulsion systems.
Right. Shells that don't just explode, but scatter smaller threats, like the M397 grenades or that 155mm Bofors shell that disperses 72 bomblets midair.
Yeah, or area denial systems like RAMS and ATOM, which essentially drop instant minefields. And these munitions are actively hunting now. Artillery fires rounds with advanced search systems like Krasnopol, SADARM, Bonus, and Staff.
They literally scan the ground as they fall, find a target, and hit it.
Yeah, but to deliver any of this, you need the artillery itself. And the whole philosophy boils down to first salvo effectiveness, FSE.
Because you need that initial burst accuracy, right? Total surprise.
Total surprise.
Right.
If you miss that first salvo, the enemy finds cover, or they calculate your position and launch a devastating retaliation.
Yeah.
So you have to perfectly calculate the FSE data triangle.
Okay, the FSE data triangle. That's target location, gun location, meteorological conditions, and internal muzzle velocity, right?
You got it. And gathering that data is a massive undertaking. For target location, you're using 1.50 thousand maps, PDS Mark III systems, laser rangefinders, and high-precision theodolites.
And then for meteorological data, because, wind and air density matter, they use microcora and digicora systems.
Exactly. And finally, internal ballistics rely on a DR-810 MV radar to check the exact muzzle velocity. All that feeds into weapons like the 155mm FH-77B02 Bofors, which has an autoloader, powered laying, and ballistic computers.
But what about range? I mean, we've got electromagnetic guns hitting 5,000 meters per second, ramjet technology pushing shells 40 to 70 kilometers.
Oh, and don't forget 120mm rifled mortars and highly mobile M30 Terriers. But for standard artillery, engineers use modifications like RIP rocket-assisted projectiles. They put a rocket motor on the back for a 25% range increase.
And then there's the base bleed technique. This one is crazy to me. So as a shell flies, it creates this vacuum of drag behind it that slows it down, right?
Right, base drag.
So base bleed basically burns a small gas generator at the rear just to fill that vacuum with gas. It's like, well, it's basically aerodynamic drafting, like a cyclist tucking in behind a truck to reduce wind drag. But the shell does it to itself.
That is a perfect analogy. And that simple trick gives a 15 to 30% range increase. Beyond that, you have structural streamlining, like ERFB extended range full bore, which uses a boat tail shape.
And ERSC, extended range subcaliber, which uses discarding sabot so a lighter projectile can achieve ultra-high velocity.
Right. But what if you need to artificially shorten a rocket's range? You can't just tell a solid rocket motor to stop burning.
So you have to physically slow it down using brake rings on the nose. Like take a standard 122mm rocket.
Yeah, with no ring, it flies 20,380 meters. Slap a small ring on it, range drops to 15,850 meters. Use a large ring, it plummets to 11,980 meters.
That's incredible. And when these land, the damage techs fall into grim categories. You've got anti-armor, APCBC for piercing steel, blast wave pressure converting potential to kinetic energy, splinters and fragments causing physical shock, and atmospheric concussion designed for severe psychological terror.
And broadly, ammo classes are just service for combat, blank or drill for training, and chemical. The bullets shift gears from macro to micro. Small arms ammunition.
Right, small arms. They're classified by projection like missiles, grenades, or BIMO deployment, or by filling like inert smoke and explosives.
The big trend here is the caliber shift. We went from the heavy 7.62mm down to the lighter 5.56mm, and the future is pushing toward 4.7mm. It's all about modularity, plastics, laser pointers, and burst fire now.
And the math on lethality is super strict here. It takes exactly 81 joules to incapacitate a human and 407 joules to defeat body armor.
Exactly. To guarantee hits, we see duplex and triplex rounds firing multiple bullets at once, though they have a strict 300-meter limit.
Looking to the future, you have Flechette's needle-like projectiles flying at 1,500 meters per second for a flat trajectory, plus electric or hydraulic firing mechanisms. But okay, wait. I have to push back on one future concept. Caseless ammunition.
Right. Caseless.
If the standard 70-30 cartridge brass case we use today is what provides the crucial gas and waterproof seal, how does going completely caseless not just, blow up in a soldier's face?
That is the exact engineering hurdle. To understand why it's so dangerous, you have to look at the firing sequence. First, small arms ammunition covers anything up to 1 inch, though mortar bombs are considered complete rounds too.
Right.
The bullet core is a lead ball or steel AP penetrator, which prevents setup and headspace issues. It's wrapped in a cupronickel or gilding metal envelope with an agavol nose and a boat-tailed base.
And the case holding it all is that 70-30 cartridge brass containing NC powder or cordite propellant with a primer cup, internal metal anvil, and fire holes at the base.
Right, so when you pull the trigger, the flash goes through the fire holes, creating explosive gas pressure. This forces the case neck to release the bullet.
And as it travels forward, the bullet mushrooms into the rifling grooves, creating a forward gas seal and engraving for SMIN, right?
Yes, but simultaneously, that that same gas pressure expand the walls of the brass case violently outward against the chamber, forming a perfect rearward gas seal.
So without that 70-30 brass expanding to plug the gap, the high-pressure gas just blows backward into the shooter's face.
Exactly why caseless is so hard to perfect. Now, sticking with infantry, grenades are divided into hand grenades with an average 32-meter range, and rifle or projector grenades launched via a discharger cup for explosive, smoke, or illumination rolls.
Which brings us to a totally different philosophy. Mine warfare. It's all about delay, disorganizing attacks, restricting maneuverability, and attrition.
And stopping power is an actual equation. Physical density of the field, plus the psychological deterrent, plus lethality.
And the sensitivity rules are strict. AP, or anti-personnel mines, require 8 to 50 kilograms of pressure. AT, or anti-tank mines, require 200 to 250 kilograms.
And engineers apply the rule of 1 to AT mines, calculating the density needed based on frontage and depth to guarantee a kill.
Right. And mines are classified by case material metal, ceramic, glass, wood, paper, or plastic. By content explosive, flame, or toxic. By purpose AT or AP, and by firing method contact, command, or influence sensors like magnetic, vibration, or sound.
But the internal firing chain is always a precise sequence. You start with the fuse as the brain, then a detonator, an intermediate booster bridge, and the main charge.
I always picture that like a line of dominoes where each falling piece is more violent. The fuse initiates a flame via chemical acid, friction, or electrical circuits. That first domino triggers the detonator,
which explodes just enough to ignite the booster, and the booster provides a massive shockwave to detonate the main charge.
And for mine laying, you have mechanical mine layers, MML, towed by vehicles but leaving visible furrows. So to fix that, you use the SPMB, the self-propelled mine barrier, which uses a conveyor belt.
If you need it instantly, you use RDMS remotely delivered mine systems via artillery or rockets, or VBMSS, vehicle-based mine scattering systems, which throw over 600 mines anywhere from 20 to 150 meters away.
And for massive coverage, the air volcano system from helicopters. So if mines are everywhere, how do you clear them? It's absolute brute force, right?
Air wave.
Like explosive breaching using CLMCs. The M58 MICLIC launches a 107-meter explosive hose across a minefield, clearing a 100 by 8-meter path. It's basically unrolling a massive explosive red carpet just to walk safely.
Pure brute force. For infantry, you have man-portable systems like APOBS-2 backpacks, 108 fragmentation grenades clearing a 45-meter path. The MPLC clears a smaller 25-meter footpath.
On the extreme end, the UR-83P uses 900 kilograms of plastic explosive for a 115 by 6-meter path. And now we even have robotic clearing like the GCS-200, which chews through 12,000 square meters a day.
And then there's mechanical breaching. The SMCS, Surface Mine Clearing System, attaches to the BMP-2, pushing surface mines aside for a 4.25-meter safe lane and 100% AT clearance.
You also have mechanical flails. The basic flail clears 90 meters in 4 minutes, but leaves the vehicle vulnerable to AT fire.
So they use the Hydrema 910 MCV2 at 72 chains spinning at 440 RPM to dig 40 centimeters deep into the earth.
Just violent destruction. And plows. The KMT6 clears 2.8-meter treadways at 2 to 3 kilometers per hour, but mines can roll back.
Yeah, so the full-width mine plow, FWMP, clears a 3.75-meter lane at 8 to 10 kilometers per hour in non-rocky ground. Plus, there are extended mine plows for 1.35-meter treadways.
Contrast that high-speed brute force with manual hand breaching. It's a soldier on their stomach with detectors and prodders under huge stress, clearing maybe 120 meters per night in a fire-free environment.
Terrifying reality. And if they find influence mines, they use rain remote actuator for influence mines to pre-detonate them safely.
To help with detection, we have GPR, ground-penetrating radar for plastic mines.
Combine that with metal detectors, and you get fusion technology, creating dual tech mine detectors that drastically reduce false alarms.
Plus, AIS, the Advanced Landmine Imaging System, actually displays visual shapes on a screen. And from the air, UAVs use IR and multispectral cameras.
And biologically, we rely on mine detection dogs and hero rats to smell trace explosive vapors.
Let's zoom in on a modern arsenal to see this in practice, specifically the Indian modern mine arsenal and smart mines. Starting with Indian AP mines, you've got the Nipun, which is a fragmentation type.
Right, and the Ulka, a directional frag mine with a 30-meter radius to 60-minute arming delay. It can be laid manually or mechanically.
Then there's the Parth, tripod mounted with 1,300 tungsten pellets, triggered by remote or tripwire. What about their anti-tank mines?
For AT, there's the Vibhav, a bar-shaped plastic mine with a built-in 120-day self-neutralization period. The Mishal is a full-width attack mine with electronic sensors.
And the Prechand uses an influence fuse for a shaped charge belly strike, aiming for total K-kill destruction.
Exactly. Finally, the Tandav uses magnetic, seismic, vibration, and heat sensors with remote arm and disarm capabilities.
Globally, the smart mine era is wild. You look at the PFM-1 butterfly mine, it's a scatterable liquid explosive that looks exactly like a toy. It's chilling. Which is why modern international standards now strictly demand safety timers, right?
Yes, self-neutralization and self-deactivation protocols are mandatory to prevent them from staying active for decades.
And mines actively hunt now, like top attack technology. Look at the PTK-M1R.
It fundamentally changes the rules. It has a 300-meter detection range. When a vehicle enters, the mine tilts and ejects a submunition into the air for a vulnerable roof strike.
It's actively hunting the weakest point of the vehicle.
Exactly. Other smart mines include the M21, which actually distinguishes target weights to only hit high-value armor, and the P13 Medallion, a bounding frag mine with self-righting feet and advanced seismic rod sensors that feel footsteps in the earth.
Moving to the next chapter.
Chapter 16, Revision Module. Let's start.
Right, so we are jumping straight into the basics. Push-button warfare.
Yeah, the concept where you just push a button and reaction motors achieve, supersonic speeds and global reach in a matter of minutes.
Exactly. But for your revision, you need to firmly separate a missile from a rocket. I mean, a missile is just the propelled object itself.
Right, while a rocket is specifically the gas ejection motor, it's just the thing providing the thrust.
Yeah, and you also have to contrast their flight paths. Visualize this so you don't forget it. A ballistic path is basically a free fall.
Like an arching rainbow curve.
Exactly. You blast it up, the engine cuts, and it just falls. But a cruise flight path is totally different. It maintains a constant height at a low altitude the entire way.
Okay, got it. Now, let's rapidly compare manned aircraft to guided missiles. Manned aircraft obviously require high manpower and total air superiority,
Right, and they are reusable, but they are hard capped by human G-force limits. You can only pull so many Gs.
whereas guided missiles, which are unmanned projectiles with control equipment, require very low manpower.
And they're disposable, which is huge. They easily bypass air defenses, have highly versatile launch platforms, and, incredibly high accuracy and hit probability.
Plus total weather immunity. And when you look at economic efficiency, they achieve way greater acceleration and just superior performance without a pilot holding them back.
Right. So moving to the physical system itself, the guided weapon system. Remember, the missile anatomy is like a human body.
Yeah, so the payload, which is nuclear, biological, or chemical, that's the fists.
The fuse is the intelligent trigger deciding when to punch.
And the guidance unit is the brain doing the signal processing, right?
Exactly. Then the control unit is the muscles moving the control surfaces, and the airframe is the structural skeleton holding it all together.
But the missile is useless without the launch infrastructure. So you have the launcher, which provides the rigid structure and transport.
Right, and then launch control. That involves computers, testing and repair teams, and crucially, survey GPS for launch point accuracy.
Because if your starting point is off by an inch, you miss by miles.
Exactly. And the last infrastructure piece is communications for command and control.
Okay, let's rattle out the 4 classification matrices. Matrix 1 is the propellant. That's solid fuel, liquid fuel, hybrid, or ramjet.
Matrix 2 is the payload, biological, nuclear, chemical.
Matrix 3 is the target, anti-satellite, anti-air, or anti-missile.
And Matrix 4 is basing, which is either silo-based or space-based.
Right, so moving on to ranges. You have to memorize these kilometer brackets. Battlefield is under 200 kilometers.
Tactical ballistic is 150 to 300 kilometers.
Theater ballistic covers 300 to 3,500 kilometers.
And short or medium range overlaps there, going up to 3,500 kilometers.
Then intermediate range takes over from 3,500 to 5,500 kilometers.
But anything over 5,500 kilometers is an intercontinental or ICBM.
Right, and don't forget the submarine-launched ones, the SLBMs.
Right, SLBMs. Now, within those ranges, SAM's surface-to-air missiles have entirely replaced traditional anti-aircraft guns.
Yeah, and the tactical missile classes operate in those shorter ranges to provide direct support, so they have to be light and rugged.
Exactly. But all of this relies on guidance, and the whole goal of guidance is increasing SSKP.
Single shot kill probability.
Right. And you have 2 main types here. Command guidance, where ground radar steers it, and beam riding.
Beam riding is like a laser pointer, right? The missile
Yeah.
just keeps itself centered in the directed energy beam.
Yeah, exactly. And for observation methods, they use JOT guidance on target, which is a closed loop system.
Like a thermostat constantly adjusting itself.
Right. Or they use Jolius guidance on location.
Okay, switching to payloads. Warhead requirements are strict. You need interchangeability, durability, and field readiness.
And the lethality types are highly specific. You've got shape charge, which is strictly for anti-armor.
Then kinetic energy, relying just on speed and mass.
Fragmentation for soft targets. Blascom earth shock.
Which is specifically for runway penetrators, right? It buries under the concrete to destroy the foundation.
Exactly. And finally, incendiary. But the fuse triggers these. You have impact, altitude, and proximity fuses.
But fuse safety is a massive deal. They have strict safety and arming mechanisms to guarantee a safe distance from the launcher.
Yeah, they use late arming, unarming capabilities, and self-destruction to prevent any collateral damage.
Looking at advanced warheads, we are seeing multi-warhead systems and terminally guided submunitions, or TGSM.
And terminal strikes use preset methods or dynamic tracking via quartz sensors.
Plus, modern trends rely on VHSIC, very high-speed integrated circuits, along with fiber optics and laser tech.
Yeah, and phased array antennas, plus a huge reliance on GPS for positioning.
So how do we push all this? Propulsion, Newton's laws, action and reaction generating acceleration and thrust.
Right, chamber reaction temperatures hit between 2,000 and 3,500 degrees Celsius using an igniter.
And engines fall into 2 categories. Non-air breathing includes solid fuel, hybrid, and liquid fuel, which uses complex pumps and tanks for regulated control.
And don't forget cryogenic technology here. They use supercooled oxygen and hydrogen, dropping it below minus 120 Kelvin.
Which is huge because it uses 30% less fuel volume, perfect for high-orbit satellites.
Exactly. Then you have air-breathing engines. Ramjets use ram rocket tech, balancing thrust against drag.
But wait, they require a boost to Mach 2 first because they have absolutely zero static thrust.
Right, they can't start from a standstill. And then you have scramjets, which go even faster.
So breaking down the domains, air propulsion balances a large mass at a small velocity against a small mass at a high velocity for high thrust.
Ground propulsion is usually wheels and axles, or maglev, magnetic levitation, which entirely eliminates friction for massive acceleration.
For marine propulsion, it's nuclear reactors for steam or LNG engines for low emissions.
And spacecraft use chemical rockets for launch, but switch to electric propulsion like ion and Hall effect thrusters for deep space.
Because they need that efficiency. For advanced atmospheric engines, subsonic combustion ramjets are basically stovepipe engines operating from Mach 3 to Mach 5.
Right, and supersonic combustion scramjets operate at Mach 5+, and they also strictly require a booster.
Okay, flight dynamics. Steering this mass requires 3-axis control. Pitch is for climb and dive. Yaw is for left and right.
And roll manages the longitudinal rotation. You use aerodynamic control surfaces for this.
Canards on the nose, moving wings in the middle, and tail surfaces at the rear.
But in a vacuum, those are useless. So you need reaction control systems.
Like gimbaling engines, flexible nozzle exhaust vanes, vernier rockets, or liquid fuel engines.
Exactly. And the system elements controlling those include an autopilot regulator acting with internal gyroscopes.
And the actuation power scaling up based on the missile size. You use pneumatic power for medium SAMs.
Hydraulic power for large tactical missiles.
And turbomechanical power for huge space boosters.
And the control logic making the decisions is either polar using angle and distance or Cartesian using an X and Y grid.
Which brings us to the absolute peak of this, hypersonic missile technology.
Right. These fly at low altitudes, strictly below 100,000 feet, and hit speeds over 6,000 kilometers per hour.
Because of that, they rely heavily on scramjet engines and possess extreme maneuverability.
To survive, they use stealth. specifically radar absorbent material, or RAM, and unique airframe shaping.
And the advanced guidance systems are DSMAC and Alarm, which literally provide vehicle identification and target prioritization dynamically at thousands of kilometers an hour.
Finally, to defend against this, militaries use ABMs, anti-ballistic missiles, for exo-atmospheric defense and warhead interception.
And on the ground, the ADAT system, it has anti-armor capabilities, pre-launch warhead selection, a regulated burn rate.
And it can actually loiter over the battlefield, plus it has enhanced safety protocols for the crew.
Got it. All facts logged. Moving to the next chapter. Chapter 17, Revision Module.
Let's get right to it.
We are beginning immediately with the operational pillar of survival, which is protection.
Right, and for your rapid-fire revision, remember that protection is an operational pillar, and its nature is the exact converse of lethality.
Yeah, so lethality projects force, and protection absorbs or avoids it. And the key fact here is that its true unpredictability is only proven in war.
Exactly. Simulations don't count until you're in it. Now, strategies are strictly divided into two categories, direct and indirect.
Right, so Radley's off. Direct protection is the post-engagement phase, right?
Yes, post-engagement, meaning you've been targeted and fired upon. It focuses strictly on surviving the impact.
So it relies entirely on a physical shield, armor, and just raw material strength.
That's right. You're bracing for the hit.
To use a lightning-fast analogy, direct protection is your bulletproof vest, whereas indirect protection is basically the ninja stealth suit.
That is the exact terminology you need, yeah. Indirect protection is the pre-engagement phase. It focuses on avoiding being hit in the first place.
Because if they don't see you, they can't shoot you.
Exactly. It relies on active measures and tactics. We're talking stealth, managing your signatures, camouflage, and using smoke screens.
And multispectral smoke screens, right? Just to counter specific threats in the modern surveillance environment.
Right. You are actively countering lasers and thermal optics, not just hiding from human eyes.
Okay, moving fast. Individual vehicle survival directly depends on moving from isolation to integration.
Which brings us directly to network-centric warfare, yeah.
The vehicle as a node. So the evolution shifted from a traditional platform-centric model, right, to a modern system of systems.
Right, and you have to know the difference. The traditional model is a self-contained fighting platform. It uses organic onboard sensors.
Which means it's limited to line-of-sight targeting, right?
Yeah, exactly. If you can't see it through your periscope, you can't hit it, resulting in a very slow sensor-to-shooter cycle.
But the modern model completely changes that. The vehicle is a network node now.
Yes, it uses distributed external sensors for beyond line-of-sight capability.
Meaning you achieve shared situational awareness and compressed response timelines.
Exactly, and that rests on the four network pillars. Do you have the list?
I do. Let's rattle them out for you. Distributed sensing, rapid information exchange, coordinated employment, and system integrations.
And for those integrations, you need to remember they include unmanned aerial systems.
So drones.
Right, drones. Also infantry battle management, artillery, aviation sensors, and massive command and control networks.
Okay, so the operational advantages there are obvious, right? Reduced sensor-to-shooter timelines, enhanced survivability via shared data, and early threat detection.
Absolutely massive advantages, but it introduces vulnerabilities.
Right, so let me ask a quick targeted pushback question here. Does transforming the vehicle into a network node essentially turn it into a high-value cyber target?
Yes, factually, yes it does. And that dictates incredibly strict modern design requirements for data security and network resilience.
Because if your network goes down, you're blind.
They're just a heavy metal box again.
Okay, so a network node is useless if it can't maneuver, which leads us directly to the physical foundations of vehicle mobility.
Right, we have to talk about how these things actually move, the conventional mechanical pillars of mobility.
Maximum speed, acceleration, power-to-weight ratio, and obstacle negotiation.
Those are the internal mechanical metrics, yes. And they build the traditional movement-centric mobility, which is based on a concept called the mobility factor block.
The mobility factor block. And that combines those internal mechanical metrics with external factors, right?
Exactly. External factors like terrain geometry and trafficability.
Which brings us to terra mechanics.
Right. Terra mechanics is the specific analysis method for soil properties, ground strength, and soil trafficability.
And it relies on selected measurements and statistical extension. So quick analogy to lock in the definition here for you. Go for it. Terra mechanics is basically analyzing how the vehicle's footwear interacts with the track using statistical extension.
That is the perfect way to visualize it, yeah. It's the shoe hitting the dirt, mathematically speaking.
Got it. And that runs parallel to terrain geometry.
Right, which evaluates the nature, the severity, the physical shape, and the frequency of obstacles.
And that directly impacts the design for crossing capabilities and overall operational functionality.
It forces the engineers to build the vehicle to survive whatever landscape they predict it will fight in.
Okay, but physical mobility isn't just mechanical anymore, is it? Modern movement and continuous network operation require massive, sustained power.
Which is the shift to energy-centric mobility. It extends way beyond traditional mechanical movement.
Right, let's rattle out the key technical elements here. Auxiliary power units, or APUs, advanced batteries, smart grid architectures, low signature operation, and overall survivability.
And all those elements form what we call the energy mobility triangle.
Wait, let me ask for a rapid clarification. So mobility in this context isn't just driving, right? It's the energy capacity to stay mobile and active in the digital and surveillance space without running out of power.
That is completely correct. It's digital mobility. And the operational significance of that energy mobility triangle includes extended surveillance, reduced detectability, networked operation support, and sustained combat effectiveness.
Because if you have to turn your massive diesel engine on just to run the computers, you're not stealthy anymore.
No, you're an acoustic and thermal beacon.
Okay, so combining mechanical mobility and energy brings us to executing actual cross-country operations.
Right, moving off the paved roads. And the cross-country challenges are driven by variable ground conditions.
So we're talking seasonal changes, weather impact, and vehicle traffic degradation, where the column just destroys the dirt as it drives.
Exactly. The soil turns to mud, which means the human factor plays a critical role here.
Right, it requires really high driver skill levels and intensive training to manage those complex technical requirements.
Because the environment is failing underneath them in real time.
So how do we evaluate that? We have 3 vehicle performance measures. Let's list them.
First is speed, which is evaluated by comparing cross-country routes versus paved roads.
Second is trafficability, which is the resistance to bogging down.
Yep. And third is obstacle negotiation, which is measured purely by the success rate.
And all of that has strict mechanical dependencies, right? Like the power-to-weight ratio, suspension system, running gear design, and the interaction of soil and gear within terra mechanics.
Everything we just covered covered, combined into one real-world performance metric. Exactly.
Okay, last major concept, night movement aids. We have a strict comparison to make here.
Right, driving cross-country in the dark. First, you have active IR aids,
which emits an actual infrared light beam. It's lower cost, but it's highly visible to enemy sensors, and it lacks depth perception.
Yeah, that lack of depth perception makes optical negotiation incredibly dangerous.
So just to ensure that active IR drawback is perfectly understood with a fast analogy, active IR is effectively turning on an invisible flashlight that the enemy can easily see if they have the right sensors.
Exactly. You are lighting yourself up for anyone with a thermal or IR optic.
Which is terrible for your indirect protection.
Right.
So what's the alternative?
Passive aids.
Passive aids, yes. This includes image intensification and low light level TV.
And the main benefit is that they are undetectable by the enemy, right? Because they don't emit any energy.
Right, they just amplify existing light.
Yeah.
But that comes at an incredibly high financial and technological cost.
Moving to next chapter.
Chapter 18, revision module. Start.
Right, let's get straight into the foundations of modern AFV subsystems.
We are drilling this for you, the listener, so you need to lock in. No fluff today. Let's establish the baseline systems of armored fighting vehicles, starting with protection and power. Give me the modern trend for protection.
The modern trend heavily emphasizes active protection. That's, moving away from just passive armor.
Got it. And on the power side, what is the specific disadvantage noted for gas turbines?
Well, gas turbines, they face major disadvantages. Primarily, they just aren't efficient enough for the new load requirements.
Good. Now, moving to fire control systems, or FCS. I need you to rattle off the 3 types of FCS errors. Go.
Okay, you've got 3. 1, permanent biases. 2, variable biases. And 3, random errors.
Let's break those down systematically.
Huh.
Define permanent biases and give the source text's example.
Permanent biases are design-related. The exact example you need to remember is gun sight displacement.
Because it's a physical permanent misalignment, right?
Well, exactly. It's built into the physical geometry of the vehicle.
Okay, number 2, variable biases. What are they? And what are the 2 specific environmental parameters the system measures?
They are environmental. And the 2 parameters you have to memorize are crosswind speed and charge temperature.
Wait, charge temperature?
Yes, charge temperature. The temperature of the actual ammunition charge dictates how fast it burns, which, changes the ballistic trajectory.
So crosswind speed and charge temperature. Got it. Number 3, random errors. What are they?
These are totally unpredictable. The text lists ammunition fluctuations and sensor biases as the primary parameters.
So if the listener gets a question on an unpredictable ammunition fluctuation, that's a random error.
Right, exactly.
Now, break down the exact sequence of how the SCS processes these errors. There's a specific 3-step loop. Rattle it out.
The loop is sense, calculate, predict.
Elaborate on that sequence quickly.
First, the sensors literally sense the biases. Then, the computer calculates the necessary corrections. Finally, it predicts the exact aiming point. Sense, calculate, predict.
I need the specific FCS systems listed in the module. I'm going to demand them, you list them. Start with the auto-tracking system.
That's a NIGHT system, KNIGHT.
Thermal upgrades.
The TISAS, TISAS.
And the simplified site. What is that one called?
That is the MSC2 site.
What are the other 2 mentioned?
You also have the dual axis DISTES and the Lancet-op.
And all of these, the Night TISAS, MSC2, what do they integrate with? What is the core brain?
They integrate directly with the ballistic computer system, the BCS, alongside a network of smart sensors.
Okay, structural recap for the listener. Protection trend is active protection. FCS loop is sense, calculate, predict. Systems feed into the BCS. Let's move to vision and navigation. What are the optics doing?
We're looking at combined day-night optics.
Give me the exact operational parameter for night vision.
Night vision operates up to 2,000 meters in total darkness.
2,000 meters.
Yeah.
And thermal imagers. What is their specific utility?
Thermal imagers detect heat, and their specific utility is to defeat camouflage and foliage.
Which enables a specific operational capability for the crew. What is it?
It allows for closed-down operations utilizing ergonomic cupolas.
So they fight without opening the hatches. What is the navigational aid they rely on when closed down?
That would be the Ferranti PS.
Break down the PS acronym.
Position and azimuth determination.
Okay, moving to ammunition and survival. The doctrine here is that ammo is designed to survive the fire zone. How are we mitigating the traditional metal casing explosion risks?
By replacing them. You use combustible or bag charges instead.
Why? What is the mechanical benefit?
Because they provide controlled burning. This drastically reduces the brew-up risk if the compartment is hit.
So no more metal shrapnel from the casings. Now drill the safe storage bins. There are 3 features to localize fires. What are they?
Compartmented stowage, pressure cooling, and automatic release.
And for active fire suppression?
You use localized splinter-triggered water jackets, along with pressurized cooling.
Splinter triggered meaning shrapnel sets them off instantly.
Exactly.
Unconventional survival. NBC protection. What form does it take?
It's liquid NBC protection.
What are the 2 specific components the listener needs to memorize?
Hydrogenous liners and direct plug suits.
Hydrogenous liners and direct plug suits. Got it. That concludes section 1. Moving to section 2. Modern and futuristic infantry combat vehicles, or ICVs. What is the massive doctrine shift here?
The shift is moving away from narrow, fixed roles. We are moving entirely to modular, reconfigurable vehicles.
What environments are driving this doctrine shift?
High-intensity and urban combat environments.
And how does that affect the crew layout?
It specifically modifies the traditional 3-man commander structure.
All right, let's drill the modern ICV specs. I'll prompt you answer. Weight parameter.
Increased from 16 to over 28 tons.
Armament.
A 30mm anti-ICV gun plus GPMG suppressive weapons.
Protection parameter.
It relies on 25 to 30mm of steel.
Mobility.
Reaches 70 kilometers per hour road speeds.
Okay, listener, lock those baseline specs in. 28 tons, 30mm gun, 25 to 30mm of steel, 70 kilometers an hour. Now, transition to the FICV, the futuristic models. What is the major upgrade in armament?
They're armed with CE 3rd and 4th gen ATGMs.
Break down ATGM.
Anti-tank guided missiles.
And how is this firepower managed?
It's managed by an integrated FCS brain, just like we discussed with the main tanks.
Drill the FICV situational awareness features. Rattle off the 3 specific technologies from the text.
First, you get a 360-degree view using mini UAVs.
What's the range on those UAVs?
10-kilometer range.
Yeah.
Second is plasma protection fields. Third is STA, which stands for see-through armor.
See-through armor, SDA. So what is the ultimate philosophy shift in signature management for the FICV?
You have to control visual, thermal, radar, and acoustic signatures simultaneously.
And the protection philosophy. It's not just 6 steel anymore. What is it?
The philosophy shifts to survivability via agility and crew augmentation.
Survivability via agility and crew augmentation. That is a critical phrase, listener. Which brings us perfectly to Section 3, Active Protection Systems. APS. What is the fundamental concept of APS?
It acts as a defensive bubble around the vehicle.
I need the 3 specific steps for how this bubble works. Drill them now.
Step 1, detection. Step 2, classification. Step 3, intercept.
Unpack detection. How is it achieved?
Through a 360-degree radar.
Classification.
That's threat identification. The system decides what the incoming object is.
And intercept.
Intercept is the deployment of countermeasures.
What are the 3 physical components that make up the APS?
The multi-role radar, the computer and control system, and the defensive ammunition.
And the text divides countermeasures into 2 categories, soft kill and hard kill. Define them.
Soft kill is electronic jamming. You confuse the threat. Hard kill is physical destruction. You break the threat.
All right, global systems drill. You need to know which country uses which system. Let's start with Israel. What is their system called?
It's called TOAHY.
And what specific mechanism does Trophy Y use for hostile fire detection?
It uses MEFP.
Unpack the acronym. Listener needs this.
Multiple explosively formed penetrators. MEFP.
Moving to the USA. What is their system?
The USA system is called Quick Kill.
What are its 2 defining features?
It features vertical launch missiles and a phased array radar.
Vertical launch and phased array. Now Russia. They have 2 systems listed.
Right, Arena and DRZD.
How do they function? It's mechanically different from the US and Israel.
Yeah, they utilize silo-launched rockets with a downward fragment spray.
Downward fragment spray. Got it. Now, what is the overarching technical challenge for all of these APS systems? The exact metric.
Achieving a 0.5 millisecond reaction time.
Half a millisecond. And what 2 environmental factors make that reaction time so difficult to achieve?
Battlefield clutter and electromagnetic interference.
Electromagnetic interference.
Yeah.
Because everyone's using soft kill jamming.
Exactly.
Yeah.
The spectrum is just flooded with noise.
Okay, quick recap of Section 3 for the listener. APS is a defensive bubble. Detection, classification, intercept. Israel uses Trophy with MEFP. USA uses Quick Kill with vertical launch. Russia uses Arena and DRZD with a downward fragment spray. Reaction time is 0.5 milliseconds. Let's push into Section 4. Advanced navigation and future MBTs. Give me the specific inertial navigation system mentioned.
It's the Celex Galileo FIN 3110 inertial navigation system.
How is situational awareness handled for 360-degree coverage? Rattle off the 3 components.
You've got thermal imaging, daylight and low light TV, and the DNVS.
DNVS stands for what?
Driver's night vision system.
And how are all these tactical operations managed centrally?
Via the integrated command and information system.
Let's talk about the future main battle tanks, the MBTs. The text mentions a specific material concept. What is it?
The plastic tank modifier.
The plastic tank modifier. And highlight the 2 specific future programs listed.
You have the Indigenous Sergeant Mark II and the FMBT, which is the future main battle tank.
There is a specific weight parameter target for the FMBT. What is it?
It targets a highly compact 50-ton weight limit.
A 50-ton limit. Now, stepping back, what is the overall evolution in warfare design that all these systems represent? Where did we start and where are we going?
We started with a platform-centric design that was all about standalone armor and firepower.
And we have shifted to what?
We've shifted to interconnected smart nodes within a system of systems.
I'm repeating that for the listener. Interconnected smart nodes within a system of systems. How is this network integration achieved physically?
It connects external sensors, drones, and joint forces via high-bandwidth communications.
But this massive digital integration creates a specific engineering problem. What is the demand?
A massive electrical demand. You need incredible amounts of power.
Break that down. Rattle off the 4 specific things that require this high electrical demand.
1, the active protection systems. 2, the electronic warfare, or EW suites. 3, the situational awareness sensors. And 4, sustained power for prolonged silent watch.
Prolonged silent watch, meaning systems are on, but the vehicle is hidden. But we have a constraint here, right? They have to generate all this electrical power without doing what?
Without compromising mobility. That is a hard rule.
Which means modern AFVs are no longer just tanks.
Yeah.
What is the exact phrase used to describe them now?
They function as power-managed digital hubs.
Power-managed digital hubs. This leads us directly into our final section, Section 5. AFE, power plant engineering, and efficiency. How do we power these hubs? What is the core engineering necessity?
Energy-centric mobility.
Energy-centric mobility. The module outlines 3 distinct reasons why this is absolutely essential. Drill them. Reason 1.
Space constraints. You just don't have room for massive traditional engines.
Reason 2.
The necessity for a low vehicle profile.
Why do you need a low profile?
To maximize armor protection.
And reason 3.
The need for a high power-to-weight ratio.
And what operational requirement dictates a high power-to-weight ratio?
Terrain geometry navigation. You have to be able to physically move the hub across broken ground.
So we have space constraints, low profile for armor, and power-to-weight for terrain geometry. How does engine performance enhancement actually solve this?
It requires a highly compact design. The goal is to get maximum output from a very small volume.
So they have to manage a trade-off. What is the trade-off between?
It's the trade-off between energy, so electrical power for the hub and movement.
And how do they physically accomplish this within a compact design? The text compares it to conventional supercharging. What are the 2 specific methods used?
By utilizing higher fuel combustion and increased air intake.
I want to repeat that so it's hammered home. Higher fuel combustion
Right.
and increased air intake.
Exactly. Compared to conventional supercharging, that's how they meet the demand.
Let's do a final rapid structural recap of the entire module for the listener. Protection trend.
Active protection.
FCS systems integrate into what?
The ballistic computer system, or BCS.
Safe storage bins use what 3 features?
Compartmented stowage, pressure cooling, automatic release.
ICV doctrine shift.
Modular, reconfigurable vehicles, modifying the 3-man commander structure.
FICV signature management philosophy.
Survivability via agility and crew augmentation.
APS technical challenge.
0.5 millisecond reaction time amidst clutter and EMI.
Future MBT design evolution.
Platform-centric shifting to interconnected smart nodes in a system of systems.
And finally, power plant engineering. The trade-off is between energy and movement, managed by what?
Compact design using higher fuel combustion and increased air intake.
Moving to the next chapter. Chapter 19, revision module. Automobile engineering, engine cycles, fuel systems, steering systems, and advanced vehicle technologies. let's begin.
Right, so jumping straight in, the best place to start is the very foundation of it all, which is the ICE, or internal combustion engine.
Okay, let's unpack this, because it's essentially, a harnessed explosion happening inside a metal tube, right?
Exactly. It burns fuel directly inside a sealed chamber. It applies direct physical force through intermittent cycles.
And that's totally different from, like, an external combustion engine.
Yeah, like an old steam engine.
Right, where you burn fuel outside the engine to heat a working fluid, like boiling water into steam, and the steam does the work. But the ICT brings the fire inside.
It does, and to contain that fire, you need very specific core components. So the combustion chamber is the cylinder.
Right.
And inside that cylinder, you have the piston, which is a solid metal component sliding up and down. But metal on metal isn't airtight.
You lose all the pressure.
Right, so we use piston rings. They sit in horizontal grooves on the piston to tightly seal the expanding gases above them.
So no pressure escapes into the engine block.
Yeah.
Got it. And to transfer that vertical motion, we use the gudgeon pin, right?
Yes, the gudgeon pin connects the piston to the connecting rod, allowing the rod to swing while the piston just moves up and down.
And for the measurements, we look at the bore, which is the inner cylinder diameter, and the stroke, which is the total distance the piston travels.
Exactly. Now, to turn that up and down motion into circular motion for the wheels, we use the crankshaft. It uses offset webs and crank pins to do that.
Like pedaling a bicycle.
Perfect analogy. But since combustion only powers a fraction of the cycle, we need a flywheel. It's a heavy, balanced wheel on the crankshaft that absorbs power variations.
So it uses its momentum to drive the engine through the dead points when no piston is firing.
You got it. Then you have valves. The intake valve lets in fuel and air, and the exhaust valve removes burnt gases.
Which completes the energy transformation. Chemical energy becomes heat, which becomes pressure, which becomes mechanical power.
Right. And in modern cars, this is the four-stroke cycle. Stage 1 is induction. Intake opens, piston moves down, creates a partial vacuum.
Sucking in the mixture.
Yep. Stage 2 is compression. Valves close, piston moves up, pressure builds.
That's stage 3. Combustion. Spark ignites it. Massive expansion of gases slams the piston down. That's the power stroke.
The only stroke that generates force. And finally, stage 4 is exhaust. Outlet opens, piston rises, pushes out the burnt gases.
Now contrast that with a two-stroke cycle, which does all of that in just one up and down movement.
Right, but those are mostly air-cooled and used for lighter applications.
Like chainsaws or dirt bikes.
Mhm.
Okay, here's where it gets really interesting. How we trigger that combustion gives us SI versus CI engines.
Spark ignition versus compression ignition.
Yeah, and your notes say CI engines hit 40% thermal efficiency. That's massive. Why don't we use them for everything?
It's all about the trade-offs. Weight, torque, construction. Let's look at the SI, the spark ignition engine first. Standard petrol cars.
Okay.
During induction, it draws in petrol and air at a strict 15-to-1 ratio. It uses a spark plug to ignite it, fed by older carburetors or modern fuel injectors.
And the compression ratio, the CR, sits between 5-to-1 and 9-to-1.
Right, so the pressure is moderate. It gets about 25% thermal efficiency.
But the upside is light construction, lower torque, great for light passenger cars.
Exactly. Now, the CI, compression ignition, is diesel. During the suction stroke, it only draws in air. No fuel.
Just air.
Just air. It compresses it so intensely that the heat of compression alone ignites the fuel the microsecond it's sprayed in by a fuel injection pump and injector.
So no spark plug. And the numbers here are insane.
Yeah.
CR is 14-to-1 up to 20-to-1.
Yeah.
It hits 40 bars of pressure and 550 degrees Celsius.
Yes.
Just from squeezing the air. How does the engine not explode?
Well, that's why we don't use them in everything. To survive 40 bars and 550 degrees, you need incredibly heavy construction. So high torque, heavy construction, perfect for freight trucks and trains, but terrible for sports cars.
Exactly. So moving to fuel systems, we've shifted from mechanical delivery to electronic management, like MPFI, multi-point fuel injection.
Using an ECU, right, the electronic control unit.
Right. It uses intake manifold sensors to fire individual electronic injectors. The huge advantage here is no vapor lock.
Oh, vapor lock, where the engine heat boils the liquid fuel in the lines, creates a vapor, and stalls the engine.
Right. MPFI makes that virtually impossible. Now for diesel, the standard is CRDI, common rail direct injection.
That's the one that's single shared rail, pressurized to, what, 29,000 psi?
Yes. An electronic management system controls the exact timing for the injectors, vastly reducing emissions.
Incredible. And if you want to push it further, you use forced induction. It's like giving the engine bionic lungs to breathe more oxygen and improve volumetric efficiency.
Well said. You have superchargers, which are mechanically driven by a belt, gear, or chain connected to the crankshaft.
So they steal a little power to make a lot of power. Exactly. Turbochargers fix that parasitic loss. They're driven by hot exhaust gases, spinning a turbine and compressor on a shared shaft.
But you need a wastegate for that, right? To bleed off excess pressure so the turbo doesn't spin infinitely and destroy the engine.
Right. Crucial component. And it's not just how we inject fuel, but what fuel, like CNG, compressed natural gas.
That needs a 200-bar cylinder, a pressure regulator, and a vapor bag.
Yes. And the benefits are huge. It has a high octane number of 130, meaning it resists premature detonation.
And there's no lubricant washdown on the cylinder walls because it's a dry gas.
Which means less friction and greatly increased engine life.
So we have this massive metal box generating huge power. We have to control it.
Yep.
Steering. We went from manual steering column to gear to linkage to wheels to HPS.
Hydraulic power steering. It uses an engine-driven pump for constant hydraulic boost. Very reliable, but it has a major flaw.
Constant power consumption even when driving straight.
Right, so we evolved to EVO, electronic variable orifice steering. It monitors a steering wheel rotation sensor and a vehicle speed sensor.
So the ECU adjusts an actuator-controlled orifice size, giving you high assistance below 10 miles per hour for easy parking, but normal road feel above 25 miles per hour.
So you don't overcorrect on the highway. And the peak of this is EPAS, electrical power assisted steering.
This replaces fluid with electronic maintenance.
Yeah.
Sensor data goes to the ECU, which commands an electric motor on the steering rack. True on-demand efficiency.
Exactly. Now, directing the car is one thing, taming the momentum is another.
Right, primary safety, physics, mass times velocity. Arresting that momentum safely is crazy. like the airbag system.
It's an active safety device, but it explicitly requires a seatbelt to work.
Yeah, behind the dash, there's a sensor accelerometer. It detects a crash profile and triggers a chemical inflation, sodium azide and potassium nitrate.
Right. It's a violent reaction. An electrical charge causes a phase change, generating nitrogen gas into a nylon bag in milliseconds.
Literally a controlled explosion to stop kinetic energy. Wild. Then there's ABS to prevent wheel lockup.
Anti-lock braking system. The ECU calculates data from wheel speed sensors and adjusts hydraulic pump valves.
And there's 3-channel, which shares the rear wheels, versus 4-channel, which has individual wheel control.
Right. Combine 4-channel ABS with traction control, and you get ESC, electronic stability control.
That uses a steering wheel angle sensor and a gyroscopic sensor. If where you want to go doesn't match where you are going, ESC brakes individual wheels to stop skidding.
Like braking the inside rear or outside front to correct yaw. And this active monitoring gives us AEB, auto emergency braking.
Right, an active loop that applies maximum braking force if the driver doesn't react.
Plus lane departure warning, lane keep assist, intelligent speed assist, and specialized protection like exit warning.
Oh, where rear radar locks the doors if a cyclist is coming. But none of this matters without grip. The tires.
Which is why we use radial tires with internal steel cord plies at a 90-degree angle to travel, giving better grip.
And for tactical applications, CTIS. Central Tire Inflation System, using standard components with rotary seals for real-time adjustments.
Low pressure for soft ground traction, high pressure for highway stability.
Right. Now, moving past the ICE, we're replacing it entirely. EVs, BEV, battery electric, and AEV, all electric. Zero tailpipe emissions, 125 to 400 kilometer range.
And FCEVs, fuel cell electric vehicles, converting hydrogen gas to electricity.
But the bridge right now is hybrids. EREVs, extended range, where the engine is just a generator, and PHEVs, plug-in hybrids.
Ranging from mild hybridization to full, and they can be parallel, driving the wheels together, or series, where the gas just feeds the generator.
And the military advantages for hybrids are huge. Silent operation for stealth, low thermal signatures, exportable electrical power, and enhanced fuel efficiency.
Exactly. Finally, autonomy. Level 0 is no automation. Level 5 is full automation, no steering wheel.
Levels 0 to 2 are human monitored. Levels 3 to 5, the system monitors, using radar, GPS, and computer vision.
Which requires 5G-powered V2I, vehicle to infrastructure, and V2X, vehicle to everything.
But the restraints are severe. The consumer cost burdens are huge, and the lack of cellular coverage outside cities makes rural V2X highly dangerous.
And internally, biometric tracking, facial recognition, security tracking, and car health monitoring are standard. It will alert you or take automatic action if you fall asleep.
Moving to the next chapter. But leave with this thought. As vehicles transition to 5G-connected, biometrically tracking autonomous pods, the definition of a car shifts entirely from a mechanical mode of transportation to a roaming data center, fundamentally changing our relationship with personal privacy while on the road. Chapter 20, Revision Module. CBRN operations, chemical warfare, biological warfare, aging characteristics, and delivery systems. Let's start.
Okay, so diving right into section 1. We're looking at CBRN operations, emergency response, and fundamentals. The very first key narrative to grasp is that the armed forces play a strictly reactive role here.
Right. I mean, they aren't initiating the attack, they are reacting to it. So it requires incredibly specialized training just to deal with the severe equipment limitations during rescue missions.
Exactly. You're essentially fighting the environment itself.
Yeah.
And the first link in that response chain is the QRT, the Quick Reaction Team.
They handle the initial agent detection, right?
Yeah, agent detection, radiation monitoring, and area decontamination.
Oh, and they also take care of immediate first aid and the actual casualty movement out of the hot zone.
Right, which leads us straight into the casualty workflow. And for this, you have to picture it as a strict one-way physical filter.
One way only.
Exactly. So you start in the dirty hazard zone.
Then you move into the Casualty Decontamination Center, right, the CDC. That acts as the physical filter.
Yep. And finally, you end up at the clean hospital. You never move backwards.
Got it. And the team running that CDC filter is the QRMT, the Quick Reaction Medical Team.
Right. They provide the specific agent treatment and handle the final evacuation. So they are managing the medical stores and all the specific antidotes.
And the logistics for this setup are incredibly rigid. I mean, you need a precise strength of exactly 100 personnel.
Yeah, plus you need additional co-opted troops specifically assigned for casualty movement and decontamination assistance.
Okay, so moving to atomic fundamentals really quickly. For the revision, the key terms to define are nucleus, the materials, nuclear reactions, yield, explosion metrics, and physical effects.
Right. And crucially, radiation dosimetry, which specifically focuses on fallout and half-life concepts.
Okay, fallout and half-life, got it. Now, what about the weather? We need to contrast atmospheric stability, so an inversion is stable, right?
Exactly. An inversion is stable, which actually means it's a low-level danger because the agent gets trapped close to the ground.
But a lapse is unstable, meaning you get rapid dispersal.
Yeah. And on a smaller scale, you have micrometeorology, so anabatic winds, which move upslope.
And katabatic winds, which move downslope.
Right. So wrapping up section 1, let's hit toxicology basics. The incubation period is simply defined as the time from the initial infection to the very first symptoms.
And for biological specifics, we categorize them into 3 things. Pathogens, which are disease-producing microorganisms. Toxins, which are poisonous, non-multiplying substances. And vectors, which are the organism carriers.
Okay, section 2. Tactical chemical attacks and engagement doctrine.
Right. So chemical warfare, CW, and biological warfare, BW, they utilize different physical states. Solid, liquid, vapor, and aerosols.
And we classify them by duration. So non-persistent agents provide a short hazard, like, G agents or hydrogen cyanide.
Right. And persistent agents provide a long hazard, like V agents and sulfur mustard.
Exactly. Now, when commanders plan these tactical attacks, they categorize their intended objectives using a very specific metric called the LD50 dose.
Oh, the LD50, that's the lethal dose for exactly 50% of the target population, right?
Yeah, exactly 50%. So looking at non-persistent tactics first, the main method is the surprise dosage attack.
And the whole objective there is maximum surprise.
Right. It relies on a highly restricted 30-second masked window to deliver the agent.
Wait, and that's explicitly to exploit the enemy's 10-second masking threshold, right? Like trying to hit them before they can put their respirators on.
Yeah, precisely.
But if a well-trained enemy can mask up in 10 seconds, how do you defeat that defensively?
Well, you change your offense entirely. You use the total dosage attack. This utilizes persistent tactics.
Oh, so it circumvents gas masks completely by using liquid agents.
Yeah, liquids like sulfur mustard or VX, because they penetrate the skin directly.
And they actively lower the enemy's cholinesterase levels over time, right?
Right, and they remain active in the area for days or even weeks, so a mask doesn't save you.
Wow. Okay, what about binary munitions?
Those are essentially two separate safe chemicals. They only mix together after firing, and they become completely lethal upon deployment.
And the dissemination forms for all these weapons can be liquid droplets, liquid aerosols, solid particles, or vapor and gas.
Right. Okay, moving to section 3. Specific chemical agent classification and their physiological effects.
Let's start with nerve agents. They basically inhibit acetylcholinesterase.
Yeah, which causes massive nervous system overstimulation.
Like severe muscle overdrive and intense convulsions.
Exactly. And we differentiate V agents like VX, which are a persistent oily liquid contact hazard.
From G agents, right? Like GB or sarin, which are a non-persistent vapor cloud inhalation hazard.
Right. Next up are blister agents. Let's highlight mustard, or HD.
Oh, mustard gas. That has the highly distinctive garlic odor.
Yeah, and the timeline of those symptoms is critical for this revision. Early on, you just get a smarting of the eyes and throat.
Then by 24 hours, you get large yellow blisters all over.
And by 48 hours, severe fever and bronchitis.
So protection against that requires a respirator immediately, plus personal decontamination drills using bleaching powder.
Exactly. Now, blood agents and choking agents. Blood agents act as internal cellular suffocators.
While choking agents like phosgene are lung attackers, and any delay in treatment there is highly dangerous.
Right. We also have incapacitating and riot agents. So psychochemical threats like BZ cause incapacitating mental effects.
And riot control agents like tear agents or CF gas cause rapid physical effects, but they feature a rapid recovery.
Yeah. Finally, for this section, the routes of entry. You have the digestive tract, direct contact with skin and eyes, and the breathing route.
And we absolutely have to emphasize the breathing route via aerosol delivery represents the highest threat, right? Because it has the most rapid onset.
Absolutely. Okay, section 4, biological warfare, logistics, and genetic engineering. Let's rattle off the biological classification.
Right, so you have bacteria, rickettsia, viruses, fungi, protozoa, and toxins.
And for the delivery systems, we're looking at explosive munitions, pressure generators, aircraft spray tanks, and biological vectors.
And actual deployment heavily prioritizes direct release or clandestine action using aerosol suspension.
Right. But the biological logistics behind all this are massive. It requires huge mass production and incredibly stable storage.
Like using liquid media or meticulously processed freeze-dried powder.
Yeah, and then you have to formulate the agent soup.
Oh, right, the agent soup.
Yeah.
That requires nutritional support, dehydration protection, and anti-foaming additives.
Exactly, just to ensure dissemination viability against harsh environmental factors.
And then there's the biotech and genetic engineering side, which is just terrifying.
Oh, completely. We're looking at a future of binary weapons, antibiotic resistance, and completely designer pathogens.
Plus food weapons and human genomics engineered specifically for ethnic-specific markers.
Yeah. So defense against this is broken into two distinct parts. Biological defense focuses on active surveillance, vaccinations, and laboratory confirmation.
Plus individual decontamination using massive amounts of soap and water, right?
Yes. Contrast that with community defense, which relies entirely on strict quarantine and isolation.
Okay, final section. Operational biology and CDC priorities.
Right, so we need to define the exact agent characteristics. First, infectivity. That's the ability to cause disease with only a small number of organisms.
Virulence is the severity of the disease and its acute symptoms.
Incubation period is the time to the first symptom, and for bioagents, this is usually over 24 hours.
Transmissibility is the person-to-person spread, so basically it's epidemic potential.
Right. Lethality differentiates killing versus simply disabling the target population.
And stability is its environmental survival against wind, sun, and humidity.
Exactly.
Wait, quick observation here. Most bioagents are highly sensitive to UV and heat, meaning they're non-persistent, right?
Yeah. That's exactly why nighttime deployment is specifically used by attackers to drastically increase that persistency.
But anthrax is the major exception to that rule. It's highly resistant and highly persistent.
Right, the spores are incredibly tough. So to manage all this, responders rely on CDC priority fundamentals.
And they classify agents based on availability, ease of production, health, impact, and engineering potential.
Yep. Starting with Category A, this is the absolute highest priority. It causes high mortality, mass panic, and massive disruption.
So examples of Category A would be anthrax, botulism, plague, and smallpox.
Right. Then Category B is the second priority. Moderate morbidity, but low mortality. It mostly requires enhanced surveillance.
Examples there are brucellosis, Q fever, ricin, and typhus.
And finally, Category C. These are emerging pathogens with future engineering potential, like Nipah virus and hantavirus.
Moving to next chapter. Chapter 21, revision module. Let's get right into it.
Okay, starting with the absolute basics, atomic structure, you have positive protons, neutral neutrons, and negative electrons.
Right, and the key players we need to know are the isotopes.
Exactly. Specifically, uranium-235, which is highly unstable and acts as the fuel, versus uranium-238, which is the stable one.
The text also makes a really strict distinction between chemical and nuclear reactions. I mean, chemical is just rearranging furniture, right? Just creating new bonds.
Yeah, while nuclear is literally tearing down the walls, like you are physically breaking the atoms apart and releasing all that raw binding energy.
Which ties directly into the mass energy rule.
Right, so a tiny fraction of the lost mass converts directly into like an astronomical amount of energy.
Okay, let's rattle off fission versus fusion.
So fission is splitting heavy nuclei. You take U-235 or plutonium-239, fire a free neutron into it, and it splits.
Releasing a massive amount of energy and more neutrons for a chain reaction.
Exactly. That's the mechanism behind Little Boy at Hiroshima and Fat Man at Nagasaki. Now, fusion is the opposite. It's joining light nuclei, specifically deuterium and tritium.
But that requires extreme heat and pressure to overcome the atomic repulsion.
Yeah. And when they fuse, they create a helium atom, giving you a way higher energy payoff than just fission.
So to actually build a weapon, you have to shift from a subcritical to a supercritical state.
Right, which depends entirely on mass and surface area. You have to rapidly compress the material to achieve critical mass.
And you surround the core with a tamper or reflector.
Yeah, to physically bounce escaping neutrons right back into the core.
Got it. Now for yield measurement, it's measured in TNT. A kiloton, or KT, is 1,000 tons of TNT. A megaton, or MT, is a million tons.
And a nominal yield is considered 20 kilotons.
Okay, let's hit the physical designs. Gun type first.
Gun type is really primitive. It uses a mechanical barrel to fire a subcritical bullet into a subcritical target. Very low efficiency.
Then the implosion type.
Much better efficiency. You surround a hollow sphere of plutonium or uranium with explosive lenses. They detonate simultaneously and just crush the core inward into a hyper-dense marble.
And thermonuclear weapons are a two-stage process.
Yeah, they use a primary fission explosion just as a trigger. It generates the extreme heat, and X-rays needed to ignite a secondary fusion reaction using a lithium deuteride fuel.
The module also talks about clean versus dirty weapons. Clean relies on fusion, leaving a helium byproduct and less radiation.
While a dirty weapon purposefully uses a U-238 tamper, the fast fission from that massively increases the yield, but produces hideous radioactive fallout.
Okay, let's list the universal characteristics of any blast.
Right, you always get a bright flash, a fireball, a thermal heat pulse, a pressure wave causing blast and shock, initial radiation, residual radiation, which is fallout, an EMP, tree, and a mushroom cloud.
Let's break down the burst altitudes. Exoatmospheric bursts happen above 30 kilometers. The ground blast and heat are negligible.
But the EMP threat is massive. Gamma rays hit the upper atmosphere, knock electrons loose, and those electrons spiral in the Earth's magnetic field,
causing a massive radio frequency pulse.
Exactly. It's totally harmless to human biology, but it causes catastrophic disruption to radar, wireless, and just fries modern infrastructure.
What about endoatmospheric bursts below 30 kilometers?
Well, an air burst causes maximum wide area blast and heat, but the fireball does not physically touch the ground.
But a surface burst does, which triggers the contact rule.
Right, the contact rule changes everything. The fireball touches the Earth, vaporizes dirt, and mixes it with highly radioactive weapon debris.
And that condenses into severe lethal fallout.
Exactly. Then you also have subsurface bursts causing ground shock and cratering, or underwater bursts creating massive radioactive gas bubbles.
Moving to the immediate reality for humans. The flash causes dazzle, or flash blindness.
Yeah, facing it in daylight blinds you for 2 minutes. Facing it at night is 10 minutes.
And even if you face away at night, the scattering light blinds you for 3 minutes. Plus, the retina burns have a 0.1% chance of permanent blindness.
Right. And for the thermal pulse, burn triage priorities are brutal. 18 to 60% burns are priority 1, needing urgent transfusion.
Under 18% is priority 2.
And over 60% is priority 3. They consider it likely fatal, so medical resources are completely diverted away from them.
The text notes that pale colors reflect heat, while dark colors absorb it and ignite.
Yeah, causing huge blow-up hazards for everyday things like paper, fabric, and vegetation.
Okay, the pressure wave has 3 components. Static overpressure, which is the crushing compressed air. Under pressure, which is the vacuum trough. And dynamic pressure.
The dynamic pressure is basically hyper-hurricane winds that collapse buildings and turn debris into lethal projectiles.
And hiding behind a hill doesn't save you from this.
No, because the blast wave behaves like a fluid. It diffracts over obstacles. A hill might shield you from the line-of-sight thermal flash, but that dynamic pressure just rolls right over the crest and hits you.
Wow. Okay, let's talk about the invisible aftermath. Residual radiation.
Right, delivered through fallout, deposition as particles settle, and rainout from weather patterns. It causes cumulative cellular damage over time.
And then there's tree. Transient radiation effects on electronics.
Yeah, this is an EMP. Tree is gamma rays physically penetrating solid materials and disrupting the atomic lattice of silicon semiconductors.
So it causes permanent performance loss in microchips.
Exactly. Now, to survive the radiation, you rely on the 3 pillars: time, distance, and shielding, like heavy concrete.
Let's run the math on that. The 7x10 rule for time.
A 7-fold increase in time results in a 10-fold decrease in radiation intensity.
So 100 centigrades per hour at hour 7 becomes just 10 centigrades per hour at hour 49.
Right. And distance follows the inverse square law. Doubling your distance from the source reduces your dose by a factor of 4.
To track this administratively, they use RES, the radiation exposure status.
And commanders use the OEG, Operational Exposure Guidance, as a decision tool to balance mission objectives against soldier health.
The risk categories are really specific. Under 3 centigrades is routine. Up to 70 centigrades is priority, causing fatigue and nausea.
Up to 100 is critical, and anything over 100 centigrades is very high risk.
Meaning severe radiation sickness and chromosomal damage.
Exactly. So to operate outside, troops use IPE, individual protective equipment.
But the manual explicitly states IPE offers no blast or shockwave protection. Only specialized shelters do that.
Right, IPE is just for the aftermath. They use full MOPP4 for skin contact hazards.
And for respirators, they use a HEPA filter for aerosols and fallout, plus a gas filter with activated charcoal for nerve agents.
They're heavily engineered, featuring a swivel drinking facility and an IHM, or integrated hood mask, to accommodate beards or severe facial injuries.
But they provide zero protection against carbon monoxide, and wearing them causes massive physiological stress.
Yeah, restricted breathing, overheating. So for simple alerts, they allow a facelet mask with lower stress.
For clothing, the permeable suit has a BTT, a breakthrough time, of 6 to 24 hours.
Right, it's a nylon outer layer, an activated charcoal middle layer, and a cotton inner layer.
Or they use impermeable items like heavy butyl rubber gloves and overboots.
And while wearing all this, you monitor dose, which is total accumulation, versus dose rate, which is the speed of absorption.
The gear list includes the RPL wristwatch dosimeter, pocket dosimeter, vehicle roentgenometer, portable dose rate meters, and gamma flash sensors.
For chemicals, they use the manual cam, residual vapor detection kits, automated alarms like the Akata GID3, or a portable gas chromatograph.
And the 3-color paper, which physically changes color if a liquid chemical agent touches it.
Yeah, true psychological horror right there. If exposed, medical kits are ready. Type A is 2 kilograms for 4 to 6 people.
Type B is 55 kilograms for 30 to 40 people.
Treatments include NAPS tablets for nerve agent pretreatment and autojet injectors. You literally stab it into your thigh to deliver atropine and oxime.
Brutal. Finally, decontamination. The PDKI kit uses Fuller's earth cloth pads to aggressively wipe agents off.
PDK2 is a puffer bottle to dust crevices, and RDP wet napkins physically wipe away radioactive dust.
Then there's the DS2 solution for larger gear. It scrubs off the agents, but the irony is staggering. The manual says DS2 is highly corrosive and harmful to skin and eyes.
Yeah, you're literally fighting poison by scrubbing your equipment with acid.
For larger units, mobile decontamination stations use a 3,000-liter high-pressure pre-wash, a chemical wash slurry, and a steam or shower post-wash.
It's just a jarring paradox. We figured out how to harness the fusion and fission of the stars themselves to make the bomb, but our ultimate survival protocol comes down to puffing Fuller's Earth from a plastic bottle, wearing activated charcoal, and scrubbing gear with corrosive acid.
That wraps the Chapter 21 revision module. Moving to the next chapter. Imagine you're a radar operator. You're sitting in a bunker, the screen is clear, everything's quiet.
Right, a totally normal shift.
Exactly. Then this single large blip appears. You start tracking it, getting ready to launch a standard anti-air missile. But suddenly, like within 3 seconds, that one blip fractures into 100 distinct threats.
All moving together.
Yeah, and this autonomous acrobatic hive mind. Your million-dollar defense system is just instantly paralyzed, totally overwhelmed by a swarm of drones that honestly cost less than a used car each.
It's terrifying. And the craziest part is this isn't some sci-fi concept for the next century. This is happening right now.
Welcome to a brand new deep dive. Today we are digging into some seriously dense military tech documents, specifically the Chapter 22 revision module.
A very detailed module, I might add.
Oh yeah. But our mission today is to trace the rapid, mind-bending evolution of unmanned aerial vehicles, or UAVs. We're going from, simple remote-controlled surveillance planes to these autonomous drone-launching motherships.
And interconnected swarms. It's a fundamental rewriting of the rules of engagement.
So by the end of this, you are going to understand exactly what it takes to deploy a flying aircraft carrier. Let's unpack this. Because before we get to the sci-fi swarm stuff, we have to talk about the physical setup on the ground.
Right, because none of this high-tech autonomy works without an incredibly robust physical infrastructure. The foundation of any unmanned mission is actually split into 2 parts.
Yeah, and this split fascinated me. It reminds me of the space mission. You have the ground control station, the GCS, and the launch and recovery station, the LKS.
Exactly.
It's like having mission control in Houston running a flight, while the launch pad crew down in Florida handles the actual rocket. But why separate them so completely?
Well, it really comes down to cognitive load and, physical safety. The LKS crew, your Florida team, they need to focus entirely on the raw physics of aviation.
So dealing with crosswinds, fueling, pre-flight checks.
Right. They're on a live tarmac, it's loud, it's dangerous. That's a totally different skill set from tactical execution. The GCS crew, on the other hand, they're the tacticians.
Managing the payloads and sensors.
Yeah, analyzing data, making strategic decisions. So you put the GCS physically separate, sometimes thousands of miles away in a sterile, safe bunker. That way they aren't distracted by, say, a mortar attack or a blown tire on the runway.
Okay, but if your pilot is in Nevada and the drone is taking off from a dirt strip across the world, the latency sounds like a nightmare. How do they maintain a real-time connection?
That is where the specialized drone satellite link comes in. It's the single most critical lifeline.
Because regular radio doesn't work.
Not at those distances. The Earth is curved, mountains get in the way. If a drone dips behind a ridge, your line-of-sight radio link is gone. So you have to bounce a highly compressed, encrypted data stream from the GCS up to a satellite in orbit and back down to the drone.
Which explains why every military is so obsessed with endurance and altitude ceilings. Like if we look at the history, you had platforms like the Searcher Mark I.
Right, a classic older model.
Yeah, and it gave operators, 8 to 10 hours of flight time?
Yeah.
And a 200-kilometer range, which is decent, but then you look at advanced platforms like the Heron, and it just blows those numbers out of the water.
Oh, absolutely. The Heron gives you 24 hours of endurance and a massive 30,000-foot ceiling.
That's a huge jump.
It's not just an upgrade, it changes military doctrine. With an 8-hour drone, a commander has to constantly cycle them in and out. You get gaps in surveillance.
But with 24 hours.
You get persistent overwatch. You just park the drone in the sky and watch the patterns of life unfold all day. And that 30,000-foot ceiling is really about survival.
Because you're above the weather.
Above the weather, and more importantly, out of range of ground-based small arms fire and most portable anti-air missiles. The drone becomes this untouchable eye in the sky.
Wow. And obviously, they didn't just want to watch targets, they wanted to strike them. So we saw specialized combat platforms emerge, like the Harpy and the Cutlass.
Right, integrating those kinetic strike capabilities.
And it's fascinating to track India's indigenous evolution here, too, with the Rustum series.
Yeah, very deliberate, iterative process.
Right, they started with the Rustum 1 as a baseline, then scaled it up to the Rustum H to refine the aerodynamics, and finally advanced to the Rustum 2.
Constantly pushing their manufacturing capability.
Exactly. But looking ahead, the focus is totally shifting towards stealth, like the IUASV programs, the GATOC, and the AURA. But wait, I have to ask. If a drone's whole purpose is to be invisible to radar, how can it constantly beam video up to a satellite? Doesn't that data link act like a glowing beacon?
You've hit on the exact paradox of modern stealth UAVs.
Okay, so how do they solve it?
Well, you can build a perfectly smooth airframe like the GATOC or AURA, right? But if it's blasting radio frequency emissions, the enemy just tracks the signal back to the source.
Right.
So the data link tech has to evolve with the aerodynamics. They use highly directional, low probability of intercept antennas.
Meaning they don't broadcast continuously.
Exactly. They use burst transmissions, they compress the data, fire it up to the satellite in a fraction of a second, and then go completely radio silent again.
Wow. Okay, so we've got these invisible, high-endurance drones. But a single drone can only carry so much. And this is where it gets really interesting, because the military realized they needed a way to project massive drone power deep into enemy territory.
Enter the mothership concept.
Yes, the flying aircraft carrier.
Small drones are tactically brilliant, but their range is terrible. They can't cross an ocean, so you turn a heavy lift aircraft into a mobile aerial base.
And historically, they tried modifying traditional planes for this, right? Like strapping drones to a C-130 Super Hercules or using naval battleships.
They did. But recovering a drone mid-air out the back of a cargo plane involves a drogue device.
Which sounds incredibly chaotic.
It's an aerodynamic nightmare. You're unspooling a hose with a basket, the drogue, and asking a tiny drone to fly perfectly into it while dealing with the massive weight turbulence of a 4-engine cargo plane.
Yeah, that sounds like a disaster waiting to happen. Which brings us to the Jewushin, or the Nine Heavens UAV. This isn't a modified passenger jet. This is the first dedicated mothership designed specifically for high-altitude long endurance, or HAL, operations.
It's a total game changer. The architecture is built purely to be a mobile logistics hub. We're talking about a 10-ton class aircraft. It has a 16.35-meter fuselage and a massive 25-meter wingspan.
Just to generate enough lift.
Exactly, for heavy payloads at high altitudes. And it features an H-shaped tail.
Wait, why an H-shaped tail specifically?
It's all about clearance. If you're dropping 100 drones out the back, a traditional vertical tail fin right in the middle is a massive collision hazard.
Oh, that makes sense. So they push the stabilizers out to the edges.
Right, creating a totally unobstructed drop zone behind the aircraft.
Brilliant. And to keep it flying, it uses a WS9 Krinling turbofan engine. Plus, it's got rugged tricycle landing gear and wing sponsons.
It's built to operate in less than ideal conditions, yeah.
And it has its own sensors, right? An EOIR, nose turret, electro-optical, and infrared, and a radome. But the coolest part is the modular mission bay. You called it hot swappable logistics. What does that actually mean?
It means speed. Usually, reconfiguring a plane takes days in a hangar. But a modular mission bay is basically a giant standardized cartridge. Tuesday, you slide in a disaster relief cartridge. Wednesday, you pull that out, slide in a drone deployment cartridge, and you're ready for a totally new mission in hours.
That's wild.
Yeah.
And the numbers on this thing. It's got a 6,000-kilogram payload capacity, a 15,000-meter ceiling, a 7,000-kilometer range, and 12 hours of endurance.
Don't forget the firepower. It carries standoff missiles and bombs on 8 external hardpoints.
Right. But the craziest capability can launch over 100 small drones at once.
But hold on, you just talked about the drogue device and the violent turbulence. Dropping 100 drones from a 10-ton aircraft sounds chaotic. How do they not instantly smash into each other?
Well, if the goal was to neatly recover all 100 drones, it would be impossible. But that's not the point.
So they're expendable.
Exactly.
Yeah.
The tactical genius here is about saturating defenses. Releasing 100 drones isn't a delicate maneuver. It's a brute force data attack on enemy radar. Modern systems track threats and assign interceptors, right? A good system might comfortably track 20 targets.
But suddenly, 100 distinct blips appear.
The radar's processing power just bottlenecks. The computers can't calculate 100 evasive trajectories, and the human operators are completely paralyzed by cognitive overload.
So the multi-million-dollar defense grid just freezes up.
Rendered useless, allowing the mothership or other assets to penetrate unhindered.
Okay, so if the Jushin is dropping massive payloads, what exactly operates alongside it? Like, what's falling out of the sky? This is where we get into modern UCAVs, unmanned combat aerial vehicles, and loitering munitions.
Right, so for the big stuff, you have HALE platforms like the MQ-9B Reaper, which boasts over 35 hours of endurance, or indigenous systems like the FWD-200B. But then you have loitering munitions. I like to think of them as a predator waiting in the grass.
Or suicide drones, as they're often called.
Yeah, and they follow this strict logic cycle: launch, loiter, strike, or recover. And they are runway independent, right? Using vertical takeoff and landing VTL and simple catapults.
Exactly. You can launch them from a pickup truck.
We're seeing systems like the Warmate, which is super portable, the Sky Striker, which has a 40-kilometer range. But the indigenous Nagastra really stood out to me.
Because of the parachute recovery system.
Yes, because normally if a suicide drone doesn't find a target, you just fly it into a hill so the enemy doesn't get the bomb.
It's a sunk cost.
Yeah.
But the Nagastra changes the economics entirely. If nothing happens, it disarms the warhead midair, cuts the engine, and parachutes safely back to friendly lines. You just swap the battery and launch it again.
That's brilliant. And then scaling down even further, for close-in work, you have mini RPAS and FPV's first-person view drones.
Like the Asteria AT-15.
Right, hybrid VTLs like that, or tactical hybrids like the Switch. These agile, low-cost assets.
The cost asymmetry is fascinating here. A low-cost FTV can paralyze a vastly more expensive military force.
Yeah, so picture the airspace. Right above the trees, cheap FTVs. A few thousand feet up, loitering munitions circling. Up at 15,000 meters, the Jushin mothership. And way up at the edge of space, 18 to 20 kilometers up, you have APS.
High-altitude pseudo-satellites. They fly in the stratosphere, conducting overwatch and acting as permanent communication relays.
Creating this layered, multi-dimensional theater of war.
Yeah.
But with all these assets in the air, how do human operators not just completely break down from information overload?
They divide the tasks strictly into a hunter-killer concept.
Right. Hunting is reconnaissance and tracking, and killing is the actual strike.
Exactly. And you can mix and match. You might pair a UAV hunter with a jet fighter killer, or a UAV hunter with a UCAV killer, or just use a UCAV hybrid that does both internally.
And this is mapped out in the triangle of action diagram.
The essential loop of modern warfare.
Yeah, so you have the command station, the human at the base. They're linked to the hunter, the sensor, and the killer, the effector, all connected via that critical data link.
The main benefits being zero human risk and a blisteringly fast detect-to-engage timeline.
But wait, so what does this all mean when we bring in swarm intelligence? Because we're moving past individual control now. A single operator has collective control, but the swarm conducts internal autonomous actions.
Right, resulting in what's called collective brain resilience.
Yeah, they share data midair, they act as mobile WLAN networks, they do synchronous ascents and acrobatic formations. It actually originated in U.S. anti-terrorism efforts. And the current record holder is the Aztec Hummingbird, which successfully deployed 60 systems simultaneously.
It's an incredible technical achievement.
But if the swarm has collective brain resilience, and they're sharing data midair, making adjustments in microseconds, is the human operator really flying anymore? Or are they just a manager suggesting goals to an autonomous hive mind?
Well, breaking down that triangle of action, the human operator is supposed to be the ethical and strategic anchor. But you're right. With mid-air data sharing and synchronous maneuvers, the swarm is essentially making localized tactical decisions faster than a human ever could.
It's wild to think about. Okay, we've covered a ton of ground today. We started at the standard ground control station, flew up to a 10-ton Jushin mothership, dropping 100 drones, and ended up inside the hive mind of an autonomous hunter-killer swarm, sharing data in midair.
And I want to leave you with a final thought to mull over. We define the triangle of action with the human safely at the base, directing the hunter and killer. But as swarm intelligence achieves true collective brain resilience capable of internal autonomous actions without human input, we have to ask, how long until the data link to the human becomes the slowest, most vulnerable part of the triangle? When the swarm starts thinking for itself, who is actually pulling the trigger?
Something to think about as we wrap up this deep dive. Thanks for listening. We'll catch you next time. Welcome to the Chapter 23 revision module. We have a ton of ground to cover on unmanned aerial systems and counter-UAS tactics, so let's just dive right in.
Right. The UAS ecosystem, it is a massive landscape combining basically medieval tactics with futuristic cyber warfare.
Exactly. So let's unpack this. What actually defines a UAS?
Basically, a UAS is a self-propelled aircraft. There's no human on board, and it's completely recoverable.
And we classify these threats by their operational range, right?
Yeah, exactly. You start at the low end with short-range systems, which operate up to about 20 kilometers.
Okay, and then it scales up to tactical RPAS.
Right. Remotely piloted aircraft systems, those can push out to 100 kilometers. Then you jump up to MALE, which is medium altitude long endurance, hitting around 350 kilometers.
Wow, 350. And then HAL is the absolute largest.
Yeah, high altitude long endurance. Those systems can operate up to 1,000 kilometers out.
Okay, so up to 1,000 kilometers away, but the critical thing for you to remember is the humans haven't left the loop. They're just on the ground.
Exactly. The drone is just one pillar. You also have the ground control station, the GCS.
And that's not just a guy with a joystick, right? It's a full crew.
Oh yeah, you have a mission commander calling the shots, an internal pilot actually flying the thing, a payload expert for the cameras, and an interpreter analyzing all the data.
And then the launch and recovery station, the LRS, is totally separate.
Right, manned by an external pilot.
Yeah.
For a short-range drone, they might literally just hand through it or, fire it from a catapult.
But for a massive AAL system,
You need a full runway landing or a localized parachute system.
got it. So once they're actually in the air, they fly in one of three modes. Mission mode is just a single drone doing a specific task.
Right, and relay mode uses the drone basically as a flying cell tower to bounce signals and extend the range.
And penetration mode is when it flies deep into hostile territory for autonomous data logging.
That's the one. But regardless of the mode, almost all of these systems share a massive vulnerability. They completely rely on the electromagnetic spectrum.
This is their invisible tether. I mean, they absolutely need GNSS satellites for PNT position, navigation, and timing data.
Yep, and they need telemetry links to broadcast their health and battery, plus command and control, or C2 using RF and S8 comm just to receive steering commands.
Okay, let's unpack this. I keep picturing a UAS as like a high-tech marionette puppet. The physical drone is just the wood and the string.
Yeah, that's a perfect analogy.
The crew in the GCS is the puppeteer, but the EM spectrum. Those are the invisible strings.
Right, which is exactly why this reliance is a critical flaw. Every piece of data keeping it in the sky travels over open airwaves.
So to destroy, you don't necessarily have to shoot the puppet, you just have to cut the strings.
Exactly. And that brings us to how we hunt them. The CUAS workflow is basically detect, track, identify, and interdict.
And we use a bunch of platforms for that. Ground-based fixed radars, ground-based mobile trucks, handheld units, and even UAS-based platforms.
Plus miscellaneous sensors all over the battlefield. Now for detection, you have active radars, which send out RF pulses.
But that's like shining a massive flashlight in a dark room. Everyone knows where you are.
Right, which is why passive techniques are so crucial. We use RF sensors to listen for those C2 links, acoustic sensors to hear the rotors, and EOIR sensors to see the heat signature.
Not to mention human air sentries just using binoculars.
Yeah.
But wait, hold on. I have to push back in the identification phase here.
Go for it.
The sky is incredibly cluttered. You've got birds, civilian planes, friendly drones. How do AI and sensor libraries actually prevent us from shooting down the wrong thing?
Well, what's fascinating here is that the AI doesn't look at the sky the way we do. It cross-references sensor data against massive libraries.
So radar isn't just seeing a solid block moving.
No, it detects a micro-Doppler signature. The AI mathematically knows the difference between the flap of a bird's wing and the exact RPM of a quadcopter blade.
Oh, wow. That's incredibly precise.
Yeah, and on the radio side, it reads the exact frequency hopping pattern to filter out noise. Plus, they use remote ID protocols to ping friendly craft automatically.
Okay, so once the AI tracks and identifies it as hostile, we move to interdiction, risk mitigation, and mission denial.
Right, and this splits into two categories, soft kill and hard kill. Soft kill is non-destructive, operating on the EM spectrum.
Like using radio and GNSS jammers to sever those puppet strings, or spoofing, which is deceptive jamming, and cyber takeovers to lock out the pilot.
Exactly, plus dazzlers to temporarily blind the optical sensors.
Here's where it gets really interesting, though. Soft kill isn't just electronic. There are physical non-EM soft kills.
Oh, absolutely.
We use drone capture nets and literal birds of prey, training eagles to take down drones. It feels crazy having falcons and cyber warfare on the same battlefield.
It does sound wild, but in dense urban areas, it's a necessity. You need to preserve forensic evidence, and you have to minimize collateral damage.
Right, you can't just fire missiles downtown because of the falling debris.
Exactly. That is why hard kill is reserved for long-range, high-threat scenarios where you need absolute precision.
And hard kill means destructive kinetic measures. Air defense missile systems, or throwing a wall of lead with ZU-23, Shilka, and L-70 gun systems.
Yeah, and drone-on-drone interceptors. Plus, directed energy weapons, or DWs, like high-energy lasers to melt the frame, and high-power microwaves to cook the circuits.
But, deploying lasers and eagles randomly would be total chaos.
Yeah.
CUAS requires massive strategic planning to actually work.
It relies heavily on the 5 principles of CUAS. Planning starts at the general staff level for the Corps, and is tactically integrated at the Joint AD Center, the JADC.
Their objectives are early detection, real-time info sharing, and a unified drone management system.
Right, balancing airspace management, like IFF integration at the airspace control centers, with operational space dynamics.
Meaning electronic warfare coordination, air mobility corridors, and maximizing kill areas. But the craziest part of this planning is whitelisting frequencies.
Whitelisting is essential. If you blast a huge jammer, you'll cause electronic fratricide and knock out your own drones.
So they literally have to carve out safe lanes in the radio spectrum for our own guys while flooding the rest with noise. It's an insane logistical dance.
It really is. And all this forms 3 protective layers. Layer 1 is the outer shield, relying on EW soft kill and long-range detection.
Like a moat. Then layer 2 is the intermediate shield, using AD hard kills for vital areas, the archers on the wall.
Exactly. And layer 3 is the inner shield, all arm self-protection up to 3 kilometers.
Just hand-to-hand combat where every rifle is pointing up.
Yeah. And commanders apply this via a multi-level response grid. Tier 1 is for border areas, activating all 3 layers.
Well, Tier 2 is further back in the operational depth, only using layers 2 and 3.
Right, and this maps directly to Army AD levels. Low level is up to 2 kilometers with light medium machine guns and 30mm cannons.
Medium level is up to 5 kilometers with AD guns and missiles. And deep level is over 30 kilometers, targeting hail and mail systems.
But as perfect as that sounds, the environment creates massive friction.
Right, plans fail. Detection is totally limited by radar line of sight. If a drone drops behind a hill, it's gone.
And EO sensors are blinded by fog and weather. Plus, if a drone isn't in your AI sensor library, you get false negatives.
Or false positives where you shoot at nothing. Not to mention the hazards of fratricide, falling debris, and radio interference from our own jammers.
Which is why procedural command and control is so rigid. The local air picture is managed by the Core Airspace Control Center, the CACC.
With the engagement chain flowing from air sentries up to the formation commander, who then authorizes the CUAS detachment.
But all of that procedural defense completely hits a wall against the ultimate threat, which is autonomous drones.
Okay, wait, I have to aggressively point out a massive loophole here.
Yeah, okay.
If an autonomous drone is on a pre-programmed flight path, it doesn't need a signal. Doesn't that render our entire Layer 1 electronic soft shield completely useless?
It absolutely does. You cannot jam a radio receiver that is turned off. When the EM spectrum fails us, layered defense proves its worth. Layer 2 hard kills and directed energy weapons become absolutely critical.
And that scales up terrifyingly with swarm dynamics, because swarms rely on specialization, constant communication, and collision avoidance, or flock centering protocols.
Right, they mimic a flock of birds. Defeating them requires wide area anti-swarm tech. Massive electronic EW fields, sweeping high-power microwaves, or kinetic barrages.
Which requires highly specialized systems, like the vehicle-mounted IEWS, giving us X-band radar out to 25 kilometers.
Or the drone jammer system that can spoof up to 50 kilometers and jam out to 10.
And drone spoofer systems reaching 80 kilometers. Then you have man-portable systems creating a 2-kilometer bubble for infantry.
Right, plus the integrated sea drone with a 5-kilometer soft kill and a 2-kilometer laser. And hybrid IDD and IS systems using passive RF, EOIR, and a 1-kilometer laser DEW.
But if drones bypass physical defenses by going autonomous, the final frontier really is the invisible war in cyberspace.
Exactly. The cyberspace domain has 3 layers: the physical hardware, the logical operating systems, and the cyber persona digital identity.
With interdiction focused on exploitation, like eavesdropping or destruction, just crashing the system.
They target the CIA triad confidentiality, integrity, and availability, using Trojans, hacking, DDoS jamming, and buffer overflow attacks.
But GNSS is the biggest vulnerability. It's so susceptible to interference. You can use brute force jamming like the Tobol M, blasting noise on L1 and L2 bands to cause loss of lock.
But spoofing is far more insidious. If we connect this to the bigger picture, spoofing isn't just blocking the drone, it's lying to its brain.
Feeding it fake navigation data, right?
Exactly. It uses simulation for record replay timing confusion. By altering the microseconds of satellite timestamps, it makes the drone think it's somewhere it isn't.
Incredible. So we've rapidly mapped everything from 20-kilometer short-range drones to massive 1,000-kilometer HALE systems and their EM reliance.
Down through the multi-layered response grids, all the way to GNSS spoofing and cyber exploitation.
It makes you wonder if we are rapidly approaching a future where human-in-the-loop ground control stations become entirely obsolete. The drones themselves become the puppeteers. Moving to the next chapter.
Chapter 24, Revision Module. Let's start this deep dive.
Right, so we're jumping straight into the cosmic stage. Like, our solar system resides within the Milky Way galaxy, right?
Yeah, so it consists of the Sun and the 8 planets. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Plus other bodies like satellites, asteroids, meteoroids, and comets. And, comets track these parabolic to elliptical paths specifically along the ecliptic plane.
Exactly. And to understand orbital dynamics, orbiting basically requires balancing gravitational attraction with inertia, which is what creates centripetal acceleration. Also, an altitude of exactly 500 kilometers is required just to reach negligible air density and entirely avoid atmospheric resistance.
Right, the 500-kilometer mark. I mean, this makes me think of Newton's mountain analogy for centripetal acceleration. Like, orbiting is basically having enough horizontal velocity to perpetually fall while perfectly matching the Earth's curvature.
Yeah, that perpetual fall perfectly follows the 3 laws of planetary motion. So the first law establishes conic sections for elliptical orbits or, hyperbolic paths.
Okay, well, the second law dictates equal areas and variable velocity, right? Like, meaning objects move faster when they're near the sun.
Right. And the third law states that the period of revolution is strictly proportional to the orbital axis.
Which all fundamentally relies on gravity, right? Gravity is directly proportional to mass, and its relationship to distance strictly follows the inverse square law. And that creates a gravity gradient, which is what forms gravity wells.
Yeah, and we have to separate mass versus weight here. I mean, mass remains constant everywhere, but weight is simply the force of gravity's pull, which varies depending on your location.
I really want to push back on the idea of zero gravity in space. Because of the 88% rule, like, gravity does not disappear. 88% of it is still fully present at orbital altitudes. So simulated weightlessness is just a perpetual freefall, right?
Yes, exactly. A natural spacecraft in orbit inherently creates microgravity, which is created by freefall mechanisms where centripetal acceleration perfectly balances gravity.
Okay, so let's rattle off launch mechanics and orbital insertion. Orbital velocity means you must reach 30,000 kilometers per hour to match the Earth's curve.
Right, and in that orbit, periapsis is the closest point, and apoapsis is the farthest point. For energy management, a minimum 150-kilometer altitude is mandatory, just to avoid frictional drag.
And for launch logistics, maximizing site efficiency is huge. Like, launching near the equator provides a free 1,650-kilometer-per-hour boost, which saves immense fuel and propellant.
Yeah, but you're still bound by launch windows, which are completely dependent on planetary alignment and, rendezvous timing.
It's like taking highway exits. Directional launches matter. If you take eastward launches, you target geostationary or equatorial orbits. That's used for communication and eavesdropping.
Right, whereas north or south launches target polar or figure-8 orbits, which are specifically used for spying and mapping since the Earth rotates right under them.
So once we're up there, we have altitude classifications. LEO, or low Earth orbit, is 100 to 2,000 kilometers, and it's a 90 to 120-minute period and is used for high-resolution imagery and manned flight.
Then you have MEO, medium Earth orbit, from 2,000 to 35,786 kilometers. That's primarily used for GPS navigation. And HEO, high Earth orbit, is anything above 35,786 kilometers, used for missile warning and intelligence gathering.
Got it. And for inclination angles, a polar orbit has a 90-degree inclination for total global coverage. A sun-synchronous orbit maintains consistent local solar time and consistent shadows, which is absolutely crucial to detect ground changes. And equatorial orbit perfectly aligns with the equator.
Exactly. And then there's eccentricity, or the shape. Closed or periodic orbits are circular, meaning zero eccentricity, or elliptic, which are oval-shaped. Open or escape orbits are parabolic or hyperbolic.
Wait, real quick clarification on eccentricity. How does an orbit go from closed, like elliptic, to an open hyperbolic shape?
Well, it happens when escape velocity is achieved. You pump in enough energy, and the closed loop essentially snaps open into a hyperbola, so the object escapes gravity.
Oh, wow, okay. And for synchronicity, we have asynchronous. Geosynchronous is a 1-to-1 ratio. Semisynchronous is a 1-to-2 ratio.
Right, and geostationary is a fixed point. Supersynchronous means the period is greater than 24 hours, and graveyard orbits specifically act as disposal zones.
So let's hit global and regional navigation satellite systems. INSAT, the Indian National Satellite System, provides broadcasting, data relay, and military surveillance.
And GPS from the USA uses 24 satellites. It provides latitude, longitude, and altitude data exclusively through trilateration.
And for augmentation, WAOS improved GPS accuracy from the original 100 meters down to 15 meters. Then DGPS, differential GPS, improves it further to 1 to 3 meters.
Right. Then there's NAVIC, or IRNSS, built by ISRO. It's a regional system covering India plus 1,500 kilometers. It uses a 7-satellite constellation, specifically 3 GEO and 4 GSO.
Its services include the Standard Positioning Service, or SPS, for the public, and Restricted Service for armed forces. It also features grid-based ionospheric corrections and a satellite integrity alert flag.
Exactly. And Gaggan is India's regional satellite-based augmentation system.
Other global competitors include GLONASS from Russia, with 24 satellites, Galileo from the EU, and BioU from China, which uses 35 satellites using mixed orbits.
And for regional boosters, there's Japan's QZSS.
I love QZSS. Using highly inclined elliptical orbits specifically for overhead coverage in mountains and cities is genius. Like, it literally peaks down into urban canyons.
Yeah, it's brilliant. Now, for space propulsion and cryogenics, spacecraft launch and maneuver capabilities rely heavily on these principles.
It's like lighting a firework versus starting a car engine, right? Solid propellant rockets deliver extremely high thrust, but have highly limited throttle control, like a firework.
Exactly, whereas liquid propellant rockets are like a car engine. They utilize either storable or supercooled cryogenic fuels, providing highly regulated and critically restartable thrust.
And solar energy systems function by harvesting solar radiation to generate electrical power and provide propulsion while in orbit.
Right, so that actually brings us to the future, like fifth dimension warfare to quantum comms. Military applications now categorize space as the fifth dimension of warfare. Primary roles are ISR intelligence, surveillance, reconnaissance, and communications.
And electronic and cyber warfare involves jamming, hacking, and cyber attacks. That directly necessitates advanced debris avoidance if things get destroyed.
Yeah. We also have human space stations. The International Space Station, ISS, and the Chinese space station, Tiangong, are designed for long-term habitation.
The scale of the miniaturization revolution is just wild compared to the massive footprint of the ISS. We have mini satellites weighing 100 to 500 kilograms, like the IMS-1 and IMS-2 workhorses.
And it gets smaller. Nanosatellites are scaled down to 1 to 10 kilograms by ISRO. They utilize silicon wafer construction, can be launched on demand, and operate in autonomous satellite swarms.
Wait, really? Swarms? The futuristic developments like space robotics and assembly processes are insane. And micropropulsion features rocket thrusters on a chip and solid rocket motor arrays.
Yeah, and finally, the Mission satellite represents a massive milestone in quantum communication.
Moving to the next chapter. Chapter 25, Revision Module. Let's begin.
Right, jumping straight into space observation, we're starting with deep space anomalies and then pulling back to Earth mapping.
Yeah, so starting with EXPOSAT, the X-ray polarimetry satellite, it basically addresses a missing dimension in space research that we've had since, well, the 1970s.
Exactly. It studies magnetic field strength, geometric anisotropies, and electron accelerators.
With the primary target being black holes and neutron stars.
I got it. For orbit and launch, it used the PSLV C-58 to get into a 350-kilometer circular orbit.
And it carries two main payloads. Payload 1 is POL-X, operating in the 8 to 30 kilo electron volt range, using Thomson scattering and an azimuthal modulator.
Yeah, and payload 2 is XBEX, which operates in the 0.8 to 15 kilo electron volt range. That one handles spectroscopic imaging and timing studies.
Wait, how does Thomson scattering actually capture this missing dimension with POL-X?
So it comes down to the physics of polarimetry. The way the X-rays scatter physically captures the geometric orientation of the light.
Oh, I see.
And then you contrast that deep space focus with NISAR, which is the NASA ISRO collaboration for advanced Earth imaging.
Right, NISAR is incredibly high frequency. It maps the Earth 4 to 6 times a month, studying ice sheet collapse, natural hazards, and monitoring the Earth's crust.
It's a massive shift in focus, from observing cosmic anomalies to tracking minute changes in our own crust.
So from scientific Earth observation with NISAR, we move directly to high penetration, tactical, military-grade imaging, Space 2.0.
Yes, Space 2.0. And the prime example here is TAT-1A, which is India's first private military-grade satellite.
Created by Tata Advanced Systems Limited, or TASL, and Satellogic. Launched April 7th, 2024 via a SpaceX Falcon 9 from the Kennedy Space Center.
Right, and the specs are super tight. It weighs just 50 kilograms, operates in low Earth orbit, or LEO, and provides sub-meter resolution with low latency delivery.
With a future goal of 25 satellites produced annually for a robust constellation, right? Mostly for armed forces and government agencies.
Exactly. Which brings us to hyperspectral imaging concepts. This technology processes the entire electromagnetic spectrum.
Capturing a spectral signature per pixel, it's like a chemical fingerprint scanner per pixel, plotted on a spectral reflectance, graph reflectance versus wavelength.
Yeah, that's a perfect analogy. It identifies material composition, detects camouflage equipment, and easily distinguishes between soil, water, and vegetation.
And then you pair that hyperspectral capability with RISAT spy satellites, which have active capability to penetrate cloud and smoke.
Right, so you get day and night border surveillance and real-time terrorist movement tracking.
So combining TSAT-1A's low latency with RISAT's cloud penetrating radar is what gives you that preemptive defense capability for national security.
Exactly. But to protect these advanced LEO defense satellites, we have to understand space weather and the legacy national satellite and launch systems.
Right, space weather and environmental challenges, driven primarily by solar flares and solar storms affecting LEO satellites and ground systems, which requires Earth's protection.
And looking back in the foundation, we had the INSAT system, established in 1983 as a joint venture. Its primary role was communication and broadcasting.
Followed by the IRS system, established 1988, managed by NNRMS, the National Natural Resources Management System.
Yeah, focusing on socioeconomic applications like land use and forest mapping.
And their sensors operate across ultraviolet, infrared, and microwave bands. But wait, with advanced active sensors on RISAT, why do systems like IRS still use passive sensors?
Well, it's about energy. Passive sensors rely on the sun as their primary energy source.
Oh, right.
Yeah, so for broad socioeconomic mapping across UV, IR, and microwave bands, it's much more efficient than draining the satellite's power with active radar.
Makes total sense. And for launch vehicles driving self-reliance, we have the PSLV for polar orbits, the GSLV for geosynchronous orbits, and the GSLV Mark III.
Right, the heavy lift GSLV Mark III or LVM3. Utilizing that takes our mission profile way beyond Earth orbit to the moon and interplanetary space.
Which brings us to Chandrayaan-4, a sample return primary mission to collect lunar regolith and return safely to Earth post-2028.
And we proved the tech for this with the Chandrayaan-3 Vikram lander hop test, which demonstrated lunar relaunch capabilities.
Because Chandrayaan-4 relies on a dual launch strategy. Launch 1 on the LVM-3 carries the propulsion, descender, and ascender modules.
Yeah, and Launch 2 uses a PSLV or GSLV to carry the transfer and reentry composite. So altogether, a 5-module spacecraft.
It's essentially a crew and robot analogy, right? Robotic arm collection, ascent from the lunar surface, docking in lunar orbit, sample transfer to the reentry capsule, and Earth touchdown.
Exactly, and that lunar docking phase requires flawless tracking support.
Like we saw with interplanetary and multi-wavelength missions, Mongolian focusing on Phobos and asteroids, and AstraSat handling multi-wavelength capabilities, including optical light.
All of which is supported by ISTRAC in Bengaluru and the Indian Deep Space Network, or IDSN, antenna at Bengaluru.
Okay, executing these multi-module missions requires a massive institutional framework. Let's rattle through the ISRO establishments.
So go for it.
Space Commission handles policy formulation and strategic direction. Department of Space, or DOS, handles execution and coordination. And ISRO handles technical implementation.
Right, and for key agencies, NRSA handles remote sensing data, located in Hyderabad for data distribution. And TRICHIX is the commercial wing, and PRL and NMRF are research labs.
Then the lead centers. VSSC in Thiruvananthapuram for launch vehicle development, ISAC in Bengaluru for satellite technology, and Shahar in Sriharikota for launch operations.
Propulsion is LPSC for liquid propulsion and cryogenic engines.
Applications and communication. SEC in Ahmedabad for R&D, DECU for educational communication, MCF in Hassan is the master control facility.
And for data, tracking, and research, you have ISTRAC for telemetry, IS for inertial sensors, and specialized labs for atmospheric radar.
It's a perfectly synthesized workflow pipeline from the Space Commission right down to the atmospheric radar labs.
And the ultimate culmination of this sprawling infrastructure and the human-rated LVM-3 rocket is putting astronauts into space.
The Gaganyaan mission, core goal being indigenous capability for human space exploration and microgravity experiments.
The mission profile is ambitious. A 3-day manned mission, 400-kilometer low Earth orbit, 3-member crew, all before 2026.
Using the human-rated LVM-3 rocket with solid, liquid, and cryogenic stages. How exactly is the orbital module broken down?
It's strictly divided into a crew module, which is the habitat, and a service module for support.
And safety systems include a crew escape system, or CES, a life support system, and built-in redundancies. Give me the testing parameters.
It's a rigorous testing phase. Integrated airdrop test, pad abort test vehicle flights in unmanned missions.
Demonstrating technology with a Viametra humanoid robot.
Exactly. You have to run those exhaustive safety tests like the airdrop and pad abort to safely shift from robotic Viametra tests to a human-rated orbital flight before 2026.
Moving to next chapter. Chapter 26, revision module. Let's begin. So we are starting right at sea level today. Mapping out the architecture of naval force vessels based entirely on their operational roles.
Right, and for this revision, you need to know the specific categories off the top of your head. We're looking at heavy hitters, multi-domain powerhouses, frigates, littoral combat ships, specialized and amphibious, and, well, support and miscellaneous.
Okay, to run through these fast, think of the fleet like a sports team.
Yeah.
Your heavy hitters, the aircraft carriers, are, the massive stadiums or the franchise players, right? They're literally floating air bases.
Yeah, floating air bases, exactly. But don't forget, heavy hitters also include submarines and guided missile cruisers.
Right, and the cruisers, they provide the air and missile defense.
Exactly, and you have to know the specific systems they use. Rattle these off: the NAG, BrahMos, and Barak 8 systems.
NAG, BrahMos, Barak 8. Got it. So back to the sports analogy. Your littoral combat ships are like the agile utility players, and support ships are the essential logistics crew keeping the game running.
That's a great way to memorize it. Now, stepping up to the multi-domain powerhouses, this strictly refers to destroyers.
Okay, destroyers.
Right, and the key example to remember is the INS Imphal. It has 2 vital capabilities you need to lock in. It features stealth characteristics and NBC warfare capability.
Wait, NBC, that's nuclear, biological, and chemical warfare, right?
Yes, exactly. It can fight through lethal environments. Moving down, we have frigates. The T word for frigates is coastal agility.
Coastal agility, right. And then we have those littoral combat ships, or LCS, the utility players.
Yeah, and their defining traits are reconfigurable missions and small crew efficiency. They swap modules depending on the job.
Oh, wow, okay. And for the specialized and amphibious category?
Those are for projecting power onto land. You have amphibious assault ships, amphibious transport docks, and dock landing ships.
Got it.
Yeah.
And finally, the support and miscellaneous category. I mean, they manage all the logistics, right? Like food, ammunition, repair parts.
Exactly. They sustain the fleet. And critically, this category includes hospital ships, which, provide medical facilities and disaster relief.
Right. Okay, so sinking beneath the surface vessels, let's look at Project 75I and the specific propulsion technologies.
Yeah, you have to distinguish between 2 submarine types here. Nuclear vessels versus those using air-independent propulsion or AIP technology.
And AIP is developed under Project 75I, right?
Yes, strictly under Project 75I. And the benefit of AIP is that it uses what we call open cycle advanced features.
Okay, so just for a quick point of clarification for your revision here, the core difference is it that AIP acts like a specialized scuba tank, allowing the sub to hold its breath far longer without coming up for air.
That breath-holding concept is spot on. But remember the exact terminology for the exam. It's nuclear versus air-independent propulsion, emphasizing those open cycle advanced features.
Okay, open cycle advanced features. And the actual operational advantage of that is it allows submarines to remain submerged for extended periods without surfacing for oxygen.
Precisely. They stay hidden longer. Now, shifting from underwater to aerial invisibility, we need to break down modern stealth technology.
All right, so the strict definition of stealth is minimizing active emitters and detection signatures through passive features.
Exactly. And the design considerations to achieve that are very specific. You're looking at unique shapes, split rudders, thrust management, and internal storage in weapon space.
Okay, but I have to push back here because there's this paradox of stealth, right? To make this aircraft invisible, you actually have to make it aerodynamically unstable, and you carry fewer weapons because of heat and payload limits. It's a massive design trade-off.
It is a massive trade-off. You absolutely nailed the limitations. Because of those split rudders and unique shapes, you get severe aerodynamic instability.
So it's hard to fly.
Yeah, which is why it absolutely requires fly-by-wire flight control. The computers fly the plane. And you mentioned thrust management. Managing heat versus speed inherently results in a reduced payload.
Right, so enter the HAL AMCA project, which balances all this.
Yes, the HAL AMCA. It's a fifth-generation aircraft developed in Mark I and Mark II phases.
And what are its specific design features to handle that stealth?
It uses a diamond-shaped wing and S-shaped air intakes. Those are crucial because they specifically reduce the radar cross-section.
Reduces rotor cross-section, got it. And what are the HAAMCA's capabilities?
You're looking at high-altitude capabilities, massive survivability, advanced avionics and targeting, and highly sophisticated weapon systems that must follow a strict operational sequence known as CONOPS.
CONOPS. Okay, so ascending from high-altitude stealth up into orbit, let's hit the final domain, space-based surveillance.
Right, the ultimate high ground. This starts with the SBS-3 project. It's a 5-year launch period, deploying 52 AI-powered satellites.
52 AI satellites, and they focus on regional security, right?
Exactly, regional security. But remember, they're joining existing veterans up there. You need to know RESAT, Cartosat, and GSAT-7.
RESAT, Cartosat, GSAT-7. And what exactly are all these spy satellites doing?
Well, their main tasks are monitoring and tracking, but there are 4 specific types of intelligence gathering.
Okay, rattle them off.
First, missile early warning. Then image intelligence, which is IN, signals intelligence, or SIGINT, and measurement and signature intelligence, known as MASINT.
SIGINT, MASINT. Okay, and regarding IMINT, there's a big tech comparison you need to know. Optical imaging versus radar imaging or SAR synthetic aperture radar.
Yes, and the distinction is critical.
So here's a quick analogy for the listener. Optical imaging is like looking out a window. It's great until it's cloudy. Radar, or SAR, is like an X-ray that sees through the clouds day or night.
That is exactly how you should remember it. Optical requires visible light and is blocked by clouds. SAR has absolute day and night capability and easily penetrates cloud cover.
Wow, okay, so with all these crucial assets in orbit, who protects them?
That is the mandate of the Sile Barker program. It's a joint mission you need to know.
Who runs it?
It's run by the U.S. Space Force and the Joint Mission Office. Their entire job is to monitor and defend these critical space assets from any threats.
Moving to next chapter. So when you picture a battlefield, it's almost instinct to think of it kind of like a chessboard. You have your pieces like troops, tanks, aircraft, and they're moving across this defined physical space. You can see the board, you know where the edges are, and you basically know the rules.
Yeah, which is a very classical Napoleonic view of conflict.
Yeah.
It's tangible. You occupy the high ground, you control the territory.
But the research stack we are diving into today for the Chapter 27 revision module completely shatters that chessboard.
Oh, absolutely.
Because the board isn't just the ground anymore.
Yeah.
It's the microscopic structure of a computer chip. Or the chaotic mathematical fluid dynamics of the atmosphere.
It's everywhere.
Right. It's the fundamental mind-bending laws of quantum physics. We are looking at a reality where forces are literally manipulating the weather, bending light to make tanks practically disappear, and waging cyber warfare using the actual fabric of reality.
Yeah. We are witnessing a total paradigm shift here. The boundaries between the natural environment, mechanical engineering, and digital infrastructure have entirely blurred. What we're unpacking today is the extreme, cutting-edge frontier of modern defense and technology.
So for you listening, whether you're catching up on emerging tech or just insanely curious about the future of global security, we are going to connect the dots between these incredibly microscopic innovations and the massive global threats they create.
Right, and it starts with the physical environment.
Exactly. From the dirt beneath our feet to the atmosphere above us. Basically, Mother Nature is being drafted into modern conflict. Let's start underground, subterranean combat.
Yeah, that has evolved dramatically. And the prime example we see in modern operational analysis is the Gaza Metro network.
Right.
We are talking about a tunnel network estimated at 500 kilometers long.
Which is, just for context, that is longer than the entire London Underground system.
Yep.
Just sitting right beneath a highly contested urban environment.
And it's not just, a series of dirt trenches. These structures are roughly 2 meters high by 1 meter wide. They are heavily reinforced with concrete, fully equipped with electricity.
Wow.
And even transit tracks for moving munitions. It operates as this invisible iron wall.
So if you're an advancing force, that completely neutralizes your traditional surface surveillance. You can't hit what you can't see, and you can't see through solid concrete and bedrock.
Right, which is exactly why the countermeasures are evolving so rapidly. You can't just send infantry down into a blind, booby-trapped maze. So today, forces are deploying drone-mounted ground-penetrating radar, or GPR.
Wait, how does that actually map a void in the earth, though? Because dirt and rock are incredibly dense.
Well, GPR sends high-frequency radio waves into the ground, and when those waves hit a boundary between different materials...
Like soil in a concrete wall.
Exactly, or soil and air in a tunnel. They bounce back. The drone captures that return signal. But here's the catch. A radar bounce is useless if you don't know exactly where on the Earth that bounce happened.
Right, in coordinates.
So these systems are tied to fiercely precise GNSS, which is the Global Navigation Satellite System. They synthesize orbital satellite alignments with subterranean radar returns.
To literally see through solid Earth and create a 3D map of the void?
You got it.
That's incredible. But weaponizing the dirt is one thing. If we move to the biological level, the environment becomes even more hostile. I have to be honest, reading the documentation on entomological warfare, or EW, was deeply unsettling.
It is a profound psychological and physical threat because entomological warfare is the weaponization of insects.
Oh.
Tactically, it's categorized into 3 distinct varieties. Variety 1 involves using insects as vectors.
So using them to carry disease, like literal biological delivery drones?
Exactly. You infect a population of insects with severe pathogens. Historical models look at things like plague or cholera, and you release them near a target population.
That is terrifying.
Then you have variety 2, which shifts the focus to an agricultural strike. Instead of targeting people directly, you use crop-destroying pests to sever supply lines.
Right, so you create an artificial famine to cripple an adversary's economy and logistics.
Yes, and Variety 3 is a direct attack on personnel in unconventional warfare. The truly insidious thing about EW is the plausible deniability.
Right, because how do you prove it wasn't just nature?
Exactly. It's incredibly difficult to prove whether a sudden swarm of locusts or a disease-carrying mosquito outbreak is a natural ecological disaster or a deliberate tactical strike. It exploits the murky legal and investigative waters of biological conflict.
I mean, how do you even begin to defend against weaponized mosquitoes? You can't shoot them out of the sky with traditional air defense.
No, you can't.
But insect swarms are localized. If you want to weaponize the environment on a macroscopic strategic scale, you have to look further up. You have to weaponize the weather itself.
Which brings us to meteorology and NWP, numerical weather prediction.
Right.
Historically, weather prediction was just about, knowing if you needed a rain jacket. Today, it is about taming atmospheric chaos using advanced fluid dynamics and thermodynamics.
Because the atmosphere is basically a giant, highly complex, nonlinear system, right? Like the butterfly effect. Small shifts in pressure can cascade into massive, unpredictable effects.
Precisely. And we face severe computational limits when trying to track a system that chaotic. The solution that modern meteorology relies on is standardized ensemble modeling.
Okay, what's that mean?
It's heavily guided by the WMO, the World Meteorological Organization. Instead of running one massive prediction equation and just hoping it's right, you run multiple models with slight variations in the starting data to reach a consensus.
Oh, so it crowdsources the math to tame the chaos.
Exactly. And that leads to precision meteorology. The source material highlights systems like Inuit. This isn't your local news weather forecast. Inuit provides 200-kilometer transborder coverage.
Right.
To map weather systems 200 kilometers across a hostile border, you have to synthesize global ocean coverage data, orbital satellites, and advanced Doppler radar.
Because Doppler tracks the exact speed and direction of the wind within a storm, right? Not just the rain.
Yes.
But why does a military command need to know the wind speed 200 kilometers away?
For artillery tempering. If you are firing an advanced munition over dozens of kilometers, a micro shift in wind speed or air density high up in the atmosphere will throw that munition completely off target.
Oh, wow. So high-level strategic decisions, from drone deployments to long-range artillery, rely entirely on this real-time meteorological data.
Absolutely.
So the physical environment is an active combatant. The dirt, the bugs, the wind. If the environment is this deadly and monitored, how do modern forces even move or exist without being wiped out?
They rely on unprecedented geospatial precision. Navigation on the modern battlefield is anchored by GNSS and the course network.
That's continuously operating reference stations, right?
Correct. And the accuracy here is mind-blowing. The documentation details RTK, or real-time kinematic positioning. For tracking assets like vehicles, RTK doesn't just tell you what road a tank is on. Right. It gives you 30 to 40 centimeter accuracy. You know exactly which tire track it's leaving.
That's wild. And when command needs to map out armed forces boundaries, they use DGNSS, or differential GNSS.
Yeah, because the challenge with satellite navigation is that when the signal travels through the Earth's ionosphere, it actually bends and slows down.
Which causes location errors.
Exactly. So DGNSS utilizes a network of fixed ground-based reference stations that already know their exact location. They measure the atmospheric delay in the satellite signal, calculate the correction, and broadcast that correction to the rover equipment on the ground.
So it's constantly double-checking the math against fixed landmarks.
Right.
But knowing exactly where you are is only useful if you can physically move efficiently. Which brings us to the mechanical innovations driving movement, specifically CVT, continuously variable transmission.
Yeah, this is a brilliant rethinking of fundamental mechanics. Traditional vehicles use fixed gears. You accelerate, the engine revs up, the gear shifts, the RPMs drop, and you accelerate again.
Right, it's quirky.
A CVT replaces those fixed gears with a system of belts and movable pulley halves.
The analogy for this really clicked for me in the reading. It's like walking up a smooth ramp instead of climbing a staircase. With a staircase, or traditional gears, you have to exert energy to lift yourself up each discrete step. But with a smooth ramp, the CVT, the ratio is infinitely variable.
That's a great way to put it. Because the pulley halves can slide closer together or further apart, the belt smoothly transitions to the exact optimal ratio for any given speed.
So the military advantage isn't just a smooth ride. It's vastly improved fuel economy and optimal engine efficiency.
Which is huge. When you are managing a logistical supply chain thousands of miles long, saving 10% on fuel across a fleet of vehicles is literally the difference between mission success and total failure.
And if a vehicle can move that efficiently, it needs a centralized brain to understand its surroundings. That's where presence technology comes in.
Presence technology turns a command center into a central nervous system. It provides real-time awareness by constantly tracking and identifying inputs. It tracks AI movement, identifies radiation emissions in the environment, and can even recognize voice and gesture commands from operators.
But here's the paradox. If you have all this presence technology and RTK satellite data pinpointing everyone to the centimeter, you have to find a way to hide.
You do.
Which leads to some of the most fascinating engineering we are looking at, advanced concealment technologies. Specifically, lenticular lenses. I actually had to read this section twice because it sounds like a literal sci-fi invisibility cloak.
Because it essentially is. A lenticular lens utilizes light refraction. If you place a specifically engineered array of these lenses in front of an object, they bend the ambient light around that object. They create what are called dead spots.
So if I am looking at a tank equipped with this, the lenses take the light from the background behind the tank and literally bend it around the tank to hit my eyes.
Correct. Your visual spectrum registers the background, rendering the physical asset virtually invisible to standard optical detection.
Bending light to hide a 60-ton vehicle is just wild. But of course, visual concealment is totally useless if you are screaming your location on a radio frequency.
Right, because everything modern emits an electronic signature. You have to hide digitally too.
Which is the domain of EMI, electromagnetic interference, and maintaining electromagnetic integrity.
Exactly. EMI defines the transfer of unwanted energy. We conceptualize this through the EMI triangle. You have a source of interference, a receiver that gets disrupted, and the coupling path between them.
And the source could be natural, like a solar flare, or artificial, like an enemy jamming device, right?
Yes.
And the ways that energy travels are highly classified. You have conducted interference, radiated interference, differential mode, and common mode. Can you break those down? Because it sounds like a lot of jargon.
It does. But it's actually quite intuitive once you see the mechanics. Conducted interference means the unwanted energy is literally traveling along physical wires, like a power cable. Radiated interference means it's traveling through open space as electromagnetic waves, like radio static.
Oh, like when your car radio buzzes because you drive right under a high voltage power line.
Perfect example.
Oh.
Then within the circuitry itself, you have differential mode, where the interference travels down the supply line and returns on the ground line in a loop. Common mode interference travels in the same direction on both lines simultaneously.
Got it. And if you don't control these modes of transfer, what happens?
The radar system on a ship could literally fry its own communication arrays.
Yikes. So how do they protect against it?
Through rigorous shielding mechanisms.
Huh.
Specifically, techniques like bonding, which provides a low impedance path for stray electrical currents to safely dissipate into the ground. This is critical not just for hiding from enemy detection, but for protecting your own highly sensitive gear.
Like life support medical devices and secure military communications. Okay, so we know how forces navigate, how they move smoothly, and how they hide from both light and electronic surveillance. But every single piece of tech we just talked about relies on physical computer chips.
Yes, the micro-level automation and material revolution making this all possible. The foundation of modern defense capability is microelectronics.
Right, and the manufacturing processes, like automation, patterning, and removal, are hyper-focused on two key metrics: line width and die shrink.
Basically, making the physical pathways on a microchip thinner and shrinking the overall size of the silicon die.
Why is smaller always better in this context?
Because distance equals time and heat. If electrons have to travel a shorter distance, the chip processes data faster and requires less power, which means it generates less heat.
And that microscopic processing power is what enables macro-level innovations like cobots.
Collaborative robots. These aren't your typical isolated factory arms in a cage. Cobots are designed with advanced sensors to work seamlessly alongside human personnel. They augment physical logistics and tactical operations without being a safety hazard.
And communicating with those cobots is where things get truly unbelievable. We need to talk about synthetic telepathy.
Oh, yes.
I honestly have to push back on this concept a little. Are we literally talking about reading a soldier's mind on the battlefield?
In a mechanical sense, yes. Synthetic telepathy relies on brain-computer interfaces, or BCIs. Typically, these are non-invasive devices like highly advanced EEG caps.
Okay.
When a human thinks about a command, the brain fires specific electrical signals. The BCI captures those brain waves, and an AI translates those neural patterns into digital code.
So you can send a command to a cobot or a message to your squad instantaneously without speaking a word or typing on a screen.
That is the ultimate goal. Silent, frictionless, instantaneous communication.
That perfectly encapsulates this entire field, just completely redefining physical limitations. And speaking of redefining physical materials, the evolution from 3D to 4D printing is a massive leap.
Huge leap.
3D printing or additive manufacturing is pretty common now. We use CAD models to lay down rigid polymers like PLA and ABS layer by layer. You print a drone propeller and it just sits there. It's a plastic propeller. But 4D printing adds the fourth dimension, which is time.
Right. 4D printing uses smart materials, primarily hydrogels. These are highly engineered materials designed to respond to specific environmental triggers, like a sudden change in heat, moisture, or light.
It's like the material literally wakes up. You could 3D print a completely flat sheet of hydrogel, which is incredibly cheap and takes up zero space to transport. You ship it to a forward operating base, and when they need it, they expose it to heat or water, and the material spontaneously folds itself into a complex structure.
Like a medical splint or an antenna casing, the logistical benefits are undeniable. The engineering challenges are immense.
Because it has to be perfect, right?
Yeah, exactly. The documentation highlights two massive hurdles. You need absolute perfection in the material's microstructure quality, and you need highly intense predictive software.
Which makes sense. If the mathematical model predicting the fold is off by even a millimeter, your hydrogel antenna casing doesn't lock into place, and the material is completely useless.
Right, the mathematics have to be flawless.
All right, let's take a breath. We've gone from mapping tunnels with radar to weaponizing the weather to invisibility cloaks and shapeshifting hydrogels. But the ultimate frontier isn't just manipulating materials or light, it's manipulating the fundamental laws of physics. Let's enter the quantum frontier.
Yeah, to understand this, we really have to contrast the first and second quantum revolutions.
Okay.
The first quantum revolution utilized macroscopic quantum effects. That era gave us semiconductors, lasers, and nuclear power. Incredible leaps, but fundamentally manageable.
Right. But the second quantum revolution basically throws the classical physics rulebook out the window. We are weaponizing concepts that shouldn't even make sense. Wave-particle duality, the uncertainty principle, the no-cloning theorem, and utilizing entanglement as a literal military force multiplier.
The most direct application here is quantum computing. A classical computer uses bits, which is information stored as either 1 or 0. A quantum computer uses qubits, processed by a QPU, a quantum processing unit.
And you can't just build a qubit out of silicon. The hardware implementations listed here sound like the inside of a particle accelerator. We're talking about superconducting circuits, trapped ions, photonic qubits, and neutral atoms.
Because to hold a piece of information in a quantum state, you have to isolate it from the rest of the universe. To truly grasp the power here, you have to look at the 4-step quantum computation flow.
Right, walk us through that.
First, you prepare superposition. This puts the qubit into a state where it represents both 1 and 0 simultaneously.
Okay, second is entanglement. You link the qubits together, so the state of one instantly dictates the state of the other, no matter the distance between them.
Third, you execute the algorithm using interference. You design the quantum gates so that the probabilities of the correct answers constructively interfere and multiply, while the wrong answers destructively interfere and cancel themselves out.
And finally,
you use amplification to extract the final correct result.
let me see if I have this analogy right, because I think it helps. If classical computing is like trying to solve a maze by walking down every single path one at a time until you find the exit, a quantum computer in superposition basically floods the entire maze with water, exploring every path simultaneously, and interference drains away the dead ends instantly.
That is a perfect visualization. And that flow allows for unimaginable processing speed. You can perform big data forecasting or instantaneously calculate global troop mobilization logistics. Problems that would take a classical supercomputer thousands of years take a quantum computer seconds.
But I want to inject some realism here for a second. The disadvantages are staggering. These QPUs generate massive heat, and they are so incredibly sensitive that a stray vibration or temperature shift causes decoherence.
Right, where the quantum state just collapses and you lose all the data.
Exactly. Don't these machines require absolute zero temperatures to function? How close are we really to seeing a quantum computer on an active battlefield?
Well, you likely won't see a quantum computer physically deployed on a front line anytime soon because of that exact fragility.
Mm.
But they don't need to be on the battlefield to control it.
Oh, interesting.
The strategic processing happens in heavily shielded, cryogenically cooled facilities, transmitting decisions globally. And the backing for this infrastructure is massive.
Who is driving this? Because building a cryogenically cooled quantum center isn't cheap.
Policy is being driven by heavy hitters like the NQM, the National Quantum Mission, and the NMQTA, the National Mission on Quantum Technologies and Applications. Development is supported by QCAL, a collaboration between the Ministry of Electronics and Information Technology, MAIDI, and Amazon Web Services.
Wow.
And on the defense side, you have the Armed Forces Center of Excellence at MCTE Mahou, the Military College of Telecommunication Engineering.
The military integration makes total sense when you look at quantum metrology and communication. They are exploiting entanglement to detect gravitational radiation. And quantum radar. This fascinated me. Classical radar can be jammed by flooding the receiver with noise, but quantum radar uses probe and idler modes.
Yes, you generate a pair of entangled photons, you keep one, the idler, and you send the other one out as a probe. When the probe bounces off a stealth jet and comes back, you compare it to the idler.
And because they are entangled, they share a unique correlation.
Exactly. If an enemy tries to spoof your radar by sending fake photons back at you, those fake photons won't be entangled with your idler. The system instantly recognizes the spoof and ignores it. It is essentially unjammable.
That is absolutely brilliant. And you apply that same logic to quantum communication. You use photons as information carriers. For short distances, you send them through optic fiber. For long distances, you use free space transmission, bouncing photons off satellites and drones. It even opens the door for quantum teleportation.
Though, to be clear, we are talking about the teleportation of quantum states and information, not physical matter. But it is instantaneous and fundamentally uninterceptable.
Which naturally brings us to the most terrifying, urgent part of this entire deep dive, the quantum threat and future cryptography. If a quantum computer can solve complex math instantly, what happens to all our classical passwords, our encrypted banking data, our secure military networks?
They are completely obsolete. We are facing a strategy employed by adversaries known as harvest now, decrypt later.
This gave me chills. The listener really needs to understand this. The hack has already happened. Adversaries have already breached servers and stolen massive vaults of heavily encrypted data. They can't read it today. But they know that once quantum algorithms, specifically Shor's and Grover's algorithms, come fully online, they will slice through classical encryption like butter.
Right. They already have the locked vault. They're just waiting for the quantum key to be forged.
It is a ticking time bomb for global security. That is why quantum defense is split into an urgent race between two methodologies, hardware and software.
Let's look at the hardware side first, QKD, or quantum key distribution.
Okay.
QKD relies on the fundamental laws of physics. It uses protocols like BB84, which is a prepare and measure protocol using polarized photons, and B91, which relies on entanglement. If an eavesdropper tries to intercept the photon key, the very act of observing it changes its quantum state.
Oh. So the system instantly knows it's being watched.
Exactly. It provides physics-proof security, but it requires highly specialized, incredibly expensive photon-emitting hardware.
Which is why we need the software side, PQC, or post-quantum cryptography.
Right. PQC doesn't require quantum hardware. It involves creating entirely new, incredibly complex mathematical algorithms that even a quantum computer would choke on. We're talking about standardizing algorithms like MLChem to protect confidentiality via key encapsulation.
And algorithms like MLDSA for secure digital signatures, Falcon for data integrity, and Spin's Sixius plus Coffee, which uses complex hash-based signatures.
The massive advantage of PQC is that it is media agnostic. You can deploy these software algorithms on the classical servers and networks we already have right now.
And when you synthesize both approaches, you get QRNG, quantum random number generators. Classical computers use mathematical formulas to generate random numbers, which means a powerful enough quantum computer can eventually spot the pattern and predict the numbers.
Right, they aren't truly random.
Exactly, but QRNG uses the non-deterministic paths of single photons to generate true randomness. A photon hitting a beam splitter and taking one path over another is fundamentally unpredictable by the laws of physics. It makes cryptographic keys completely resistant to prediction attacks.
It is the ultimate defense against the ultimate weapon.
It is just staggering to look at the sheer scale of what we've unpacked today. I mean, we started in the grit of a 500-kilometer concrete tunnel network under the Earth, and we ended up assessing non-deterministic photon paths, protecting our data from futuristic quantum algorithms.
It perfectly illustrates that the modern environment is one where the microscopic dictates the macroscopic. A micro shift in atmospheric data redirects artillery. A shift in a hydrogel's chemical makeup unfolds a shelter. A change in a photon's quantum state secures global communications.
So what does this all mean for you, the listener? I want to leave you with this final thought. If 4D printing means physical materials can independently wake up and change their shape over time and harvest now, decrypt later means devastating cyber weapons are currently sitting on servers just waiting for a future quantum key to detonate.
Yeah.
Are we entering an era where the wars of tomorrow are actually already deployed today, simply lying dormant all around us? We'll be moving to the next chapter next time, so until then, keep exploring.